This is day 3 of the Advanced Sensors and Instrumentation Annual Review webinar. I appreciate your participation for day 3. Today, the session topic of discussion is on instrumentation for radiation experiments. It will be moderated by Austin Fleming. But before the session, we have a special presentation, and Patrick will be introducing the presenter here shortly.
Thank you, Dan. Good morning, everyone. I see that people are still coming into the meeting. In line with the topic of the meeting today, which is instrumentation for irradiation experiments, we will have a brief presentation by Sacit Cetiner, who has now joined my department at the Idaho National Laboratory, Measurement Sciences. He's a joint appointee with MIT, and the conversation we will be having is the first time we will introduce, or he will introduce, the Center for Reactor Instrumentation and Sensor Physics. That's CRISP in short. And this is a collaborative effort between MIT and INL on utilizing, at best, optimizing the use of the research reactor at MIT, the MITR. You've heard already frequently mentioned the MITR as part of the presentations, as part of the general topic of using material test reactors to improve and bring sensor performance towards demonstration and a higher maturity. So this is the area or alignment with this conversation is where we're introducing CRISP. Again, this is the first time we discuss CRISP, so you will see a presentation that is in its making, essentially. This is, again, will be given by Sacit Cetiner. Some of you, or a lot of you will probably know Sacit. He's an expert in INC. He's been working on it for probably his whole professional career. And most recently, he was in charge of the INC for the BTR project. And he continues to do so, of course, pending the faith and the planning and the future of the BTR project. But for now, Sacit will introduce CRISP, and I'll leave the floor to him. Sacit, are you ready?
Thank you for the introduction, Patrick. I'm Sacit Cetiner. I'm a senior researcher in the Measurement Sciences Department at INL. And in this presentation, I will introduce the new center that we are establishing jointly between Idaho National Laboratory and Massachusetts Institute of Technology, Center for Reactor Instrumentation and Sensor Physics. I am leading this organization as a joint appointee between INL and MIT. So I would like to say that I enjoyed the broad topics and where needed technically deep conversations in the last 2 days, very technically stimulating conversations. And I am looking forward to hearing more on these interesting topics, which are critical in advancing the state of the art of nuclear instrumentation and controls. It's becoming more and more clear that the long neglected area of instrumentation and controls appears to be getting the recognition that it is an enabling technology for making the nuclear industry, nuclear enterprise, a cost competitive operation again. If you look at the reports published by many independent non-governmental organizations, that analysis after analysis, we see that the current operating fleet, the plants, they are facing a major stress, not because of their capital burdens, but because of the sheer cost of operating and maintaining the plants. And of course, operating is a more general term here. It includes operating the main control room, the field operators, the maintenance activities, as well as physical security of the plant. And it's obvious that when we look at the US average, we are not faring well with our greatest competitor, natural gas being the one right now in the face of these economic realities. So even if with the current fleet, if we did a hypothetical exercise, very non-scientific, statistically non-realistic, what if we could, by magic, reduce the maintenance and operating costs by half? You can easily see that even within the current paradigm, it is possible to reach solvency, reach economic viability by just doing that. But this is not a magic touch. It requires coordinated, well-funded activities with a dedicated mission to achieving these objectives. And of course, these examples are from the current fleet, which we have and which we have the data for. We don't have any data for small modular reactors, especially for microreactors or fission batteries. But many independent analyses confirm that these systems can only be viable only if the operations can be realized with minimal to and sometimes no operator involvement in the plant. So what I would like to talk about a little bit is take a tour in our brother sister industries and how they do it. So I would like to ask this question: can we get there? Is this achievable? If we had asked that question 15 years ago, the answer might have been different. We could probably argue philosophically around what is achievable, what is not achievable. But as you can see from the examples, only in the last decade, we've accomplished so much. And some of the technologies that we deem enabling or critical technologies, they become just common things. We don't get surprised anymore when we see a car driving by itself on the road or self-parking, or you can summon your Tesla, it comes to you. It's not science fiction anymore. It is pure science and technology. And you can also see, of course, the self-driving example is a convenience. But when it comes to mission criticality, like on the right-hand side, there are applications that we cannot afford to have humans in the loop. The decisions have to be made on the fly with all the potential paths, all the potential options that can be foreseen, must be handled by a control system. So you probably see certain individuals, CEOs of these companies, make claims that they accomplished a lot. They are they incredibly advanced the state of the technology to the levels that we enjoy today. That is actually not the case. The original investments to self-driving technologies go back to the 1970s, and in fact, the very first self-driving car ever driven was in mid-80s on the German autobahns. But it required installation of a supercomputer on the back of a van with a diesel generator to be able to accomplish very basic image processing algorithms. Image processing is not the whole thing of autonomy, but it's an enabling technology. Today, Tesla can achieve that, or any self-driving car can achieve that with just a small FPGA box. Of course, we get there, and the Brookings Institution, their figures estimate that the total government funding on the enabling technologies is about $80 to $100 billion over the last 30 years combined. And globally, it is much, much more than that. So let's look at a more recent example from the beautiful, successful descent and landing of the Mars rover, Perseverance. It's the round trip time between Earth and Mars changed between 5 minutes to 10 minutes communication time. And the entire descent from the second the capsule enters the Mars atmosphere until it lands is 5 minutes. So by the time you interject, you're already on the floor. You're already on the ground. You're too late. So it's fully autonomous control is not an entertainment here. It is a mission requirement. And I think that particular statement resonates very well with many of the things that we hear when we study, especially perform economic studies on small reactors, especially microreactors. Autonomy, at least at the minimum, semi-autonomous control and potentially full autonomy is required. But we don't need to limit ourselves to terrestrial applications. For future extraterrestrial applications, full autonomy will probably be a requirement for surface power surface power systems. So I want to make a point on this. Here's an excerpt from the Perseverance website, and you will see in the video. You can if you watch the video, you will see the cheer by the NASA engineers and scientists on the mission control system control side, that when they announced that this particular system, Terrain Relative Navigation System, TRN, as part of the landing vision system, when they announced that it converged to an acceptable solution, you can hear the people cheer. That is the mission critical technology. That's what makes the Perseverance, what sets it apart, Perseverance mission from the earlier missions. What it is basically the scientists, mostly geoscientists, they wanted to land on a very questionable, risky area. And to accomplish that, the system by itself had to identify the least risky location, given all the previous data collected, maps collected, and identify a landing pattern and divert the rover, the capsule, properly, autonomously, with no input whatsoever from the Earth's control system, mission control system. And this is the decision making. This is what makes this mission a very successful mission, and what sets it apart from earlier robotic missions in NASA history. So I especially wanted to point this out for a reason, because to identify what is that critical thing that we need to accomplish to make this mission successful is the question we should be asking ourselves. And I'm not sure if we fully identified the problem statement of autonomy. And that's what I would like to discuss in a little bit here. So, to no surprise, our power plants actually are well automated. And especially those plants that went through digital feed water control system upgrades, they can go through the entire cycle, entire mode transition, all the way from hot standby to full power with no operator input. With just a switch of a button, it has its internal gain scheduling algorithms. It changes its set points depending on the operating regime, and it provides incredibly successful bumpless transfers, especially one of the analog systems. What they suffered was when they switch over from the auxiliary feed water system to full feed water system, general feed water system. There is a bump, and sometimes it causes trips and premature trips, and those trips are reportable events, and that causes delays in the startup procedures. So without an argument, this is a mature technology. We can already do a lot. So this is automation. We have a good handle on that. But what do we mean when we say autonomy? I think what sets it apart, and you can go through the literature in successful implementations of autonomy, like DARPA's what led to the Google self-driving car Stanley implementation. It is the decision-making capabilities. It is somewhat related to the cognitive abilities of human being. And these kinds of things, capabilities, begin to make sense when when the plant undergoes major operational swings. What are we talking about? Mode transitions, going from hot standby to low power to mid power, and you're transitioning from one instrument to another. Your set points change, as well as unexpected transients due to equipment performance degradation or unexpected failure of non-critical components. For example, a component in a feed water system. You have redundancy, but you have to act on time so that the entire heat rejection path keeps functioning. So, in my opinion, what makes autonomous control argument a critical argument for these smaller reactors is their deployment scenarios. They will most likely be in a more, what we expect is in the future grid, more transactional mode, where you will have frequent maneuvers for load following, for other purposes, and then these frequent maneuvers, unless addressed with engineering features, they will lead to faster equipment wear, especially in rotating equipment, and inevitably higher frequency of failure. So you will have a broad range of uncertainties and prognostics distributions that cannot be handled by a feedback control system or simple state machines. You need to have the human in the loop, and which is something that we say we cannot avoid. We cannot afford. In my opinion, this is the core statement. It is because of these complex combinatorial effects with large uncertainties do we need what's called in the literature sequential decision-making functionality to achieve autonomous and or semi-autonomous control capabilities. So I think this is existential, and I would like to give an example from a totally different industry that went through this existential threat in the late 70s and early 80s. Sematech was funded by DARPA, Defense Advanced Reactors Advanced Research Projects Agency, and it's a nonprofit organization founded as a centralized technology development hub to make the U.S. industry more economically viable and reduce the operating cost significantly. What did that mean? It meant developing new metrology methods, and that went to the implementation and adoption of many analytical equipments that we enjoy today. For example, secondary ion mass spectroscopy was largely adopted during the Sematech initial Sematech times to improve the quality assurance and quality control practices in wafer fabrication and then dopant distributions. And as you can see, prior to its foundation, the US market share in the global integrated circuit sales was precipitously going down. But soon after, the Semitech was founded, and with, of course, giving time for market penetration, this led to the recovery of the US innovation and US competitiveness. And since then, United States leads the IC market in the design as the total share of global sales. And as you can see, this is kind of consistent with the Moore's law, but before the Semitech organization was founded, there was a departure from the Moore's law where the bit prices, and this is on the log scale, if you can see, bit prices, production costs started to went up. But after its foundation and competitiveness, introduction of competitiveness through factory floor automation, as well as new metrology methods, the overall, this is global, bit pricing started to conform to what's known as the Moore's law. So I intended to use that example as a reminder that when we centralize these activities to allow for coordination of mission critical tasks, what can be accomplished. And this was actually recognized earlier by Department of Energy in 1985, and that is correct, 1985, almost 4 decades ago. The US Department of Energy established a task force to determine the need for, assess the feasibility of, and recommend an approach to the introduction of advanced control into the nuclear power industry. This article, this particular sentence comes from a publication by a colleague of mine, Dr. Sid Ball from Oak Ridge National Laboratory, whom I had the pleasure of working with. And here a couple of additional things that I would like to share with my colleagues here. The goal is to provide a national center of excellence in research, development, and testing of nuclear control systems, employing the latest advances in automation, artificial intelligence, expert systems, hierarchical computer architectures, and optimal control. In 4 decades after this publication, we are talking about the same things. We haven't made much progress. Unfortunately, it shows. Nuclear industry, nuclear technology used to be the leader in overall world technology. We are not even following. If you go to the control rooms of our facilities, you will see that. A more recent attempt was in 2008. So here's a publication, a roadmap report from 2007, which recommended to DOE and NRC that a centralized platform be established to investigate the possibility of building a center. But this was more along the lines of the active conversations at that time regarding digital instrumentation and control systems and their penetrations in nuclear systems, and mostly had a regulatory flavor. So CRISP, Center for Reactor Instrumentation and Sensor Physics, has this vision, combining all these lessons learned and establishing a common platform to provide a centralized technology hub to attack these mission critical problems, first identify and attack in a systematic manner, a scientifically robust manner, to advance the state of the art of monitoring and controls of future nuclear systems. And mission is obvious. We have to excel in the technology development. So developed technologies can be transferred over to private partners, industry, and so we can enable a transformation in operational paradigms in nuclear systems. When we talk about, of course, controls, it includes the entire measurement loop, all the way from sensing to instrumenting, the whole measurement loop, signal processing, taking advantage of more statistical signal processing methods, and to advanced controls and decision sciences. So CRISP is funded by Idaho National Laboratory. It's located at MIT, and the location at MIT offers some advantages. MIT has centers, labs, and departments that provide enormous capabilities in these mission critical areas, such as robotics, electronics fabrication. One example I would like to share with you, for example, since I started here about a couple of months ago, we started interacting with other laboratories within MIT and centers to establish strategic partnerships. One example is Draper, and we have an NDA, and we're working towards a strategic partnership to allow exchange of infrastructure, use rights of infrastructure between MIT and theirs. Similarly, we are pursuing Lincoln, CSAIL, but they are a little bit behind on that. So this is our initial organizational structure. When I reached out to the faculty, starting from the Nuclear Science and Engineering department at MIT, and slowly reaching out to the other departments, I had a very enthusiastic participation from the faculty. And of course, we are pursuing adding other faculty members from related departments, such as electronics and computational sciences. Aeroastro is important because they work, MIT Aeroastro has significant expertise on robotics. Right now, we are funding 2 PhD students, one from the starting history with the versatile test reactor, and the other one with Professor Haishang Kim with Professor Bucci, and Zhang Jiang with Professor Julie, both from Nuclear Science and Engineering department. So with this, I would like to stop here, and I would be happy to entertain any questions or conversations around the center.
Thanks, Sacit. I think this will be a topic that will, I'll say, be discussed a lot more in the future, and so it will generate a lot of discussion, a lot of questions. I'm not sure that now it's the time to entertain, but I don't see any questions in the panel so far. So again, I'm sure this was the first time people have heard about it, so we will have to go through and provide more details of what we want to do with CRISP, I think, before a discussion can be generated. I will just pause one more second to see if there's any question coming through, or if Dan has any comments at this point, but otherwise we'll just move on to the start of session 3. I found very interesting to see this previous documents or attempts to establish a very similar effort. It's always good to look back at history. I like in particular to see the 2008 report. Part of the discussion to me here would be to discuss whether the focus on human, basically the interaction with the operator, ended up damaging the field of controls, because it really became focused on that human controls or the human aspects of it, which is important for operating plants, but is not as important for advanced reactor, right? So that's
exactly right, Patrick. It goes back to the NRC rule following the 3 Mile Island accident, 2 articles on that, and of course that is a requirement for current reactors, given the tight margins of operation around operating conditions.
Right.
But hopefully the advanced reactors will provide the flexibility based on physics and their construction
Correct.
to allow.
So that's the conversation we're having with NRC, but you can also see it reflected in organizations' internal structure. You know, at INL, that was the time in which we were pushing a lot for HSSL and, you know, the establishment of the human factors as a science, if you want, in relation to nuclear. And I think we're beyond that time now, and it's time to create or to bring out controls now from an independent perspective, you know, fully separated from human factors, and apply them to advanced reactor where the issues, as you mentioned, are different, and the licensing process will have to be different. So that's a very interesting aspect, and to me, in parts, explain why we're still stuck here talking about instrumentation and control with some uncertainty of what really the scope of the work is, still so many years after the nuclear has started operating as their first plant. So it's a good conversation to bring about, but now we need to focus on the irradiation experiments as the means to provide maturity, to bring maturity to the I portion of the IMC. So I will thank you again, Sacit, and look forward to continuing.
Thank you. Thanks for the opportunity.
Leave the floor to Austin. Go ahead, Austin. Thank you.
Thanks, Patrick, and thanks, Sacit, for your presentation. That is really good, really excellent to tie all those technologies together and provide a big picture. Today, I'll be talking about radiation experiments and specifically instrumentation that goes in them. In a couple of different angles with it, hopefully I can get across. I think it actually resonates pretty well with what Sacit was saying about times of past, and you know, instruments for these types of experiments have been developed previously, and some of them have been lost, and we've redeveloped some new technologies and whatnot. So there's common themes across the board. I'll go ahead and get started here. So for instrumentation goals for irradiation experiments are a little bit different than, you know, maybe an instrument for an advanced reactor, for example. You know, but the big goal for any of these is to develop and test qualify sensors to a maturity level that a customer adopts technology to a level significant enough to sustain the sensor technology. So what that means for different sensors varies quite a bit. So you could imagine for advanced reactors, if a manufacturer were to adopt it as part of the control system, or they need it as part of their design qualification, they would maintain that technology for long term and probably improve upon it significantly. If it was developed for radiation experiments for research objectives, such as nuclear fuels and materials testing, is a small piece of that. You can imagine programs adopting it, or other funding structures needing it as part of their core mission could also make adopt the technology and help improve it and long-term sustainability of the technology. The gold standard in this case is to take the technology that you've developed and it be commercialized. That a company out there sees a market for it, and they will sell it, make a profit, and continually improve the technology because they're making a profit on it. But not all sensor technologies developed will be commercially viable, so there's kind of a gray area there of where you can consider success, where it's making an impact, it's meeting mission needs for the nuclear energy, and whether it's a commercially viable product. So it's kind of a multifaceted thing here. And then I'd like to talk about the valley of death for sensor success. Right? So there's many ideas of sensors, and many of those are demonstrated at a lab, benchtop scale. And I have the TRL scale here at the bottom. And moving across that, right, commercialization and customer adoption is basically at the far right, and the idea is at the far left of this TRL. And we're trying to get these sensors across this valley of death. Most of them get demonstrated and then fizzle out before the end customer adopts them, whether that be advanced reactors or some irradiation experiment program or some commercial industry. So how to get them across that is a little bit of where I see these irradiation experiments for research applications or material and fuels qualifications. And ASI can help provide the bridge to in conjunction with these radiation experiments to get them to the finish line, so to say. So instruments and material test reactors are very different depending on what facility you're using. And then just to be clear here, I'm not talking about controls for the reactors or instruments for the reactor themselves. It's a device that goes into the reactor that we're trying to get some data objective or some control objective out of. And there's a huge variety of customers who do irradiation experiments. Many of you know all of these, and so I'll go through them pretty quick, but you know, any university's idea for an NSUF irradiation, right? Just it's wide open there. And then programs like AFC or NEAMS looking at fuel qualification or code validation, verification, and advanced reactor demonstrations. A lot of these companies are putting, either components or small sections of reactors into these test reactors, or maybe their fuel or some other material. There's defense applications and a bunch of others that I'm not listing here. And they have a huge range of measurement needs. So it's crazy, some of the stuff. Anything you can imagine, basically, somebody at some points wanted to measure in a reactor. Whether they've done it or not is a different story, but it's pretty cool, the range. And then I list a few of the usual suspects here. There's a ton of other ones. I didn't list most of the university reactors that are NSUF partners that are and then some that are not, that are very good irradiation facilities also. But I show pictures here of TREAT and ATR. They're the two that I've worked the most with, being at INL. But HIFER similarly does many high flux irradiations. So what role does ASI play? So at this point, you should be asking yourself, like, why is he talking about other people's stuff, like irradiations of other things? Like, this is an ASI webinar here. So, the one of the points that I'd like to make is you can, the integration and implementation of a sensor into the prototypic environment has as much to do with sensor performance as the sensor itself. And the example I like to give always is you can have the most qualified thermocouple. And if you want to measure a surface temperature, but you don't put that thermocouple in good thermal contact with that surface, let's say it's cladding and it's in a water-cooled environment, and it's in the water and not attached to the cladding, you will measure the water temperature phenomenally well, but you're not getting good data on what you wanted. So that having an eye towards that end goal, where it's going to be needed and used, is really important, because that implementation and integration into the device, whatever it is super important. And then deploying sensors in irradiation experiments provides an opportunity to test your sensors. A lot of these for advanced reactors and whatnot, they haven't built these advanced reactors, most of them, right? So they haven't tested, they're not using these sensors in prototypic environments because the prototypic environment doesn't exist yet. but you can create these types of environments in these test reactors, smaller scale and whatnot, but you can have the temperatures, the neutrons, the, everything. So by putting your sensors in these prototypic environments, these test experiments, you can test the sensor. Ideally, these sensors are mature enough to provide value for the experiments, and they'll want to pay for it themselves. And then often there's things like what people refer to as supplemental instrumentation, where the experimenter will have a spot that they could put a sensor. They don't need that data, but it might be nice for them to have, and so they'll go along with it and let you put a sensor in there to test the sensor performance. And then I think this last point is pretty important, that establishing other stakeholders in the sensor improves the long-term viability of the technology. So the more people you have interested in it, the more ideas it'll generate, the more opportunities to deploy that sensor will occur. And I'm sure I'm not any different from anybody else here, but every time I've put a sensor into an experiment or a reactor, I have learned something about that sensor. Even if it performed well, there's something a little different. Maybe you manufactured a little bit of a different way. You learned something about, the wiring, or the lead outs, the feed throughs, or something. Every time I've learned something new. And so even if it's not your end goal in sight, by deploying it in different environments and for different purposes is super helpful for the qualification. This is a slide about the instrument qualification. I kind of show it as these three angles here. So you can start with the top of, if you have an instrument, you've done some testing and you think it's ready to go. You still need to do the experimental integration, make sure it fits where it goes, it's compatible neutronically and thermally and chemically with the environment. And you can do out of pile characterization with your sensor in those types of environments, and then ideally you do an in pile characterization, make sure that the radiation effects on the sensor do not degrade the performance, or you quantify that degradation, because the end goal is, no sensor is perfect, so it's all about the uncertainty. It's how good is your sensor under the prototypic conditions. How well does it measure what you think it's measuring? And these three thrusts, if you will, really work towards defining that. So I will give two detailed examples of some irradiation experiments. Both happen to be transient testing. It's in our treat reactor at INL. I'm mainly giving those because I'm very familiar with them and I've been involved with them. But it's similar for other experiments in ATR or HIFER. You would have a similar, a customer who has some objective, either controls or measurement, and trying to meet those. So I put some pictures of experiments that I've been involved with here, and you can see lots of wires and optical fibers coming out of them. And I won't go through all of them in detail, but they're all pretty fun experiments. The first one that I'll go through here is the critical heat flux experiment. This was an LDRD at INL, in which to measure basically the boiling behavior, the transient boiling behavior, because it's pretty important for field performance. Key safety limits rely on this, or I guess avoiding critical heat flux. So there's quite a bit of uncertainty in it, actually, in a transient regime, with the radiation effects also. It's not as well understood as we would hope. And so you can imagine in a boiling experiment, things that are going to be very important to the customer are qualifying the thermal hydraulic conditions, so the temperatures, water conditions, and such. And so this was a pretty extensive instrumentation package. We had 2 pyrometers on the inside of this rodlet, which was a borated stainless steel. So we used the boron N alpha heating to provide the heat source, and we had these boiling detectors shown here in red, which measure basically the capacitance of the water in between them, which is dependent on void formation, so the steam. And then we had 4 rod thermocouples. We had a water-based thermocouple here to measure the water temperature. And then we also had what we called an N alpha thermometer to measure the power coupling factor between the reactor and the borated stainless steel piece. In this, we had a little piece of the same material with a thermocouple in it, and then try to insulate it well so it provides a good measurement, basically calorimetry of the system. So here's a couple pictures of the assembled experiment. I won't go through everything here, just to save some time, but it's quite extensive. And then here's some of the data, and so I just like to point out a few things here. We have this pyrometry data, and this over here is that boiling detector. These are pretty innovative sensors for these types of applications. The re-wetting here you can see dropping down, corresponding with kind of the boiling behavior. You still have some voids that are still in the water, but the surface of the rod is cooling down, quenching, basically re-wetting. And you can dig into this quite a bit. These thermocouples over here, you can see some neutron gamma heating and then cooling down, dumping the heat back to the water, and then slowly heating back up. There's all kinds of detail in here that's of a lot of value, even if you're just looking at it from a sensor performance standpoint. And is a pretty fun experiment to be involved with. So the other one I'd like to talk about is the drift experiment. So this was basically an experiment to benchmark NEAMS codes, cracking behavior in the NEAMS package. So in this is cracking due to thermal, temperature profile, basically. So in this, the design engineers came up with, instead of doing an actively cooled system to get the profile they wanted, they could use a heat sink to reject heat and get a temperature distribution in the sample that way. So in this case, you can imagine the thermometry package is super important. That's the whole thing, is creating a temperature profile. So in that, there was 2 pyrometers that were viewing the sample surface. We had 3 thermocouples located out in the heat sink, 2 in the heat sink and then 1 on top of the specimen. Then we had a distributed optical fiber that you can see in this little, looks like a black wire here, that was routed throughout the heat sink, and then a cable heater to get initial temperature conditions prior to the irradiation. So this is some pictures from the assembly. You can see here the distributed optical fiber here. These 2 larger optical fibers are for the pyrometry. Here's the thermocouples, one going in here, and the cable heater wrapped around the heat sink here to get the initial temperature distribution. And these pyrometers were viewing the specimen surface sideways, basically at the center. And here's a little bit of an overview of the data. It's really pretty exciting. So these are from the distributed temperature sensor. Highlighted these locations here. So the higher temperatures observed by the more inner one. These are center line axially in the heat sink. And on the right, we have the 2 pyrometers measuring the surface of the specimen temperature. and then thermocouples out in the heat sink further. This is just from one of the runs. There was I think we had 5 capsules in this irradiation series. So there's 5 other sets of data that are very similar to this. And then I'd like to focus on this distributed temperature sensor because it was something that was developed under ASI. So you can see initially here, this is the depth from the top of the heat sink to the bottom, the x-axis, and then temperature. So it's preheated up. It's at time 0, so before the reactor started. And then you can see these different traces of temperature in these different holes. So pretty quickly, you see the inner 3 profiles jump up because that heat's distributing out radially, and it's a good flat profile. So this is providing a lot of data on this thermal state of the whole experiment to validate these NIEMS codes. So you can see, yeah, we have pretty uniform, linear generation, by this flat top, and then at later times, basically that goes away and it is all diffusing out and kind of going out radially then. So you can see these different heat transfer regimes just from this one sensor. So it's pretty exciting. And then coupling that with this whole sensor package really gets you a lot of information about the thermal state of the experiments. It's a pretty cool results actually. So I'll wrap up here. So I gave those 2 examples, but the correct implementation of the deployment of a sensor is important as a qualification, and that's I think that's under recognized. I think a lot of people spend time testing in the lab or testing in very well controlled conditions in a reactor and lose sight of the end goal, their end prototype or their end customer. And basically I'm encouraging people to try to get sensors under development into irradiation experiments to help get across the valley of death, having an eye towards the end customer, and basically by establishing these other stakeholders to improve your long-term viability. And specifically, even if the irradiation experiment is not the end goal for your sensor, it can really help develop it and qualify it for the end goal or the end user customer. So I'd highly encourage that. I have my contact information here if anybody wants to contact me after. And then I think at this time I can take some questions.
Yes, Austin, I'll act as moderator for your presentation. I'll let you do that through the rest of the day. But there's a question from Chris. I have elevated him, Chris Petrie from Oak Ridge, as panelist like in the last 2 days, since he does ask a lot of questions and contributes to the discussion significantly. The question specifically here is for the use of N-alpha thermocouples and whether you're relying on a thermal finite element model to relate energy deposition in a transient to temperature increase, how they're validated, and if you compare them with SPNDs and fission chambers. I know the answer is yes to everything, so I don't know, maybe I encourage you guys maybe to have a private chat on the way that we design and run and then analyze treats experiment. I think Chris is missing out on the fun here, and you guys probably need to talk more, but go ahead.
Yeah, I'll answer it quickly. The N-alpha, so it's the same borated concentration as the rod that was up in the heated section of the specimen. So the neutronics was a little bit interesting because you have this water-filled capsule inside of a graphite moderated reactor. So you're getting a little bit of a different neutronics profile. We have spectrum. We have SPNDs located just outside the experiment, so we get a neutron flux there. And we did all the MCMP modeling to predict what our heat generation should be. considering reactor power. So using X-core detectors and then translating that to what should be deposited. And they ended up being pretty close. I'm trying to remember exactly what our predictions were off by. But there's some uncertainty in honestly the reactor power of treat. Sometimes I've heard them referred to as treat megawatts because of the uncertainty in the heat balance. So we suspect that's a source of uncertainty. But in this case, the real thing we were after is how much energy was deposited in the specimen. We don't particularly care about the actual value of neutrons because we just don't care in that it was a thermal test. So by measuring that deposition of energy is really the key piece, and decoupling that from the thermal hydraulics, and that's why it was insulated. So that was kind of the dancing between the two problems, the neutronics problem, getting prototypic profile, and making the thermal hydraulics problem easier.
That's cool. Thanks, Austin.
Okay. Yeah, in general, I think you will hear more about this. If you recall, Chris, yesterday, Richard also, or Monday, showed this direct junction TC. That has been a fun conversation to have, also between the measurements from the pyrometer and this on cladding temperature and what happens during a transient. And so the pyrometer has provided a significant change in how we have this conversation with treat between the analysis and the measurements, because it has provided a new dimension of measurement that is a lot more accurate when it works. So when it's deployable, let's say. So that is something we haven't really discussed. At a certain point, we probably want to have a more like a coordinated discussion on that. It's an interesting development.
Yeah, and in that experiment is pretty interesting. Also, we had those pyrometers on the inside looking at the surface of that the borated staying still, and then those integral junction thermocouples on the outside. So you basically are getting a temperature measurement on each side of that wall, which was pretty unique. I hadn't seen that done before.
So I'll put down a note here to have this presentation discussion on surface temperature measurement in transients. I think is interesting to a lot of folks. I don't see more questions. The timing is right for you, Austin, to take on and introduce the next speakers and then move on with the agenda. Thank you.
Okay, so I believe I stopped sharing my screen. Yep, okay, perfect. And then our next speaker will be discussing an ultrasonic sensor for treat field condition measurement and monitoring from PNNL, Andrew Casella. We can see your desktop here, it looks like.
All right, working on it. You see a presentation?
Yep.
All right.
Just drop that into the full screen.
Yeah. See what happens here.
If you can switch under display settings to the swap screens or whatever.
Did I get it there?
Perfect. That's perfect. I think you're ready to go.
All right. Thanks for the navigation there. Okay. So I'm Andy Casella, and the talk here is about our project that just ended actually on trying to develop an ultrasonic sensor for treat, specifically to measure the change in the diameter of a fuel rod during a transient test. This project had been going on and reporting over to treat under Colby Jensen, and got switched over to ASI here under Patrick just a few months ago. So this is really a project summary presentation more than an update. So Yeah, so the original goal here, like I just stated, it was that we wanted to be able to come up with a way to measure the radial expansion of a fuel rod being tested in the treat facility. And we were looking at an ultrasonic sensor to be able to do that. And so overall, you see objectives there. We wanted to design that, fabricate that, and test that so that we would be able to measure rapid non-contact in situ measurements. And so these measurements were intended to be under water conditions, to be prototypic of what the fuel rod would see in a light water reactor. And we wanted this thing not to be touching the fuel pin, but backed off a bit. And you know, a transient test and treat's going to be pretty rapid. So we just wanted to be able to pull out that change in radius during that test. And so some of the parameters here are, we wanted this thing to function hopefully up to 600 C to pull out as much data as we can as that transient increases in temperature. We wanted to directly measure the changes in the fuel rod diameter. And yeah, this needed to be quick. So the ultimate goal was to come up with a sensor that we could actually deploy to the treat facility. Schedule here is the project started in FY18, was supposed to finish in FY20, was extended for a year because of the shutdown. And at P&L here, it was myself, Matt Perwan, Chris Hutchison, and Morris Good were the main people working on this throughout the entire project. There were several others, and then we had Pradeep over at Oak Ridge. He started the project here as the PI and moved over to Oak Ridge and stayed involved throughout the project. And then Josh Dahl at Idaho was there the whole time. So jumping in, I know you've seen a lot of stuff about treat already, but the purpose here is I just wanted to drill down so you can see some of the engineering constraints we were working with. So just treat there in the middle and going to the right. So really right there in the center there, we're going to have an assembly like you see right there in the middle of Buster assembly, and inside of that there's a Seth capsule of the separate effects test. I forgot the H already, but anyway, you just saw that on the previous presentation. Holder, separate effects test holder. This was the same holder that was being discussed previously, and really I just move on. So drilling down in, so that middle picture there of the assembly, now we're just drilling down into it, so you see where the sensor is actually going to sit. So with that assembly there on the left side of the image there, moving toward the right, you see that there's the module inside the assembly, and then there's the capsule, which is a lower part of the module there, and then the capsule lid unit, and then you see the blown up picture over on the right. So if you look at that central part of the lid section there, that's where the fuel pin would sit. And what we're trying to do here is come up with a configuration of ultrasonic sensors, one or multiple, that could fit in there inside that ring between where the fuel pin is and where you see the rings around it. So that's the space we have, which is really constrained. Our ultrasonic sensors that we typically have are much larger than that. And so what this is going to end up being is come up with a configuration that allows us to measure the radial expansion, B, test it and see if it works, C, try to figure out a new configuration that will fit in here, and D, what are materials that will function under these conditions to allow the sensor to survive to get the signal out that we're trying to see. So that was the beginning part of the project, actually, was looking at the constraints and figuring out what might be possible. So the next step there was to look at potential materials. If you look there at materials considered, the lead zirconate titanate, the PZT, is what a lot of our existing sensors have, are used as an element. So that's where we're starting. We know that won't work. That won't go to a high enough temperature. And we also know that the sensor that's built around that element won't work because the bonding epoxy that's used will fail below 300 degrees. So we know we're starting from a condition that isn't feasible, but we know that these following four, or we think these following four materials, aluminum nitride, bismuth titanate, lead metaniobate, and langasite, would work. We ended up focusing on the two there, aluminum nitride and bismuth titanate, and ultimately most on bismuth titanate. And then moving on from there, this is where Morris Good really came in. I'm showing you snippets of the project. He went through a slew of sensor arrangements and measurement types and came up with the best option that we have. You see right there in the top in the middle was two sensors just in opposition to one another on either side of the fuel pen. What you see there is he's testing this in air, but we knew it would be in a water environment. So he just put water bladders on the end of the sensor moving up to the pen to simulate being in a water environment at this time. And right there, he took a large number of pins with differing diameters, and he put them in there, and he measured them multiple times. He'd set it up and measure it, set it up and measure it, to figure out how accurately it could measure the diameter to begin with, and what the uncertainty on that measurement was, just having a statistical sample of measurements. It ended up needing to have two of them there instead of one because movement of the pen would cause it to be an increase in the uncertainty. So finding out that we have two, and this configuration allowed us to get measurements like you see on the right of the image there, where he had multiple pins like I see each of those dots. So the x-axis there is the diameter of the tube he's looking at, and the y-axis is the measured diameter. You can see there's a one-to-one fit with uncertainty that's pretty tight. So this was the configuration we wanted to go with for the design to start with. And if you look down at the bottom, we went to a dynamic test here where we have that same setup. And if you look, you can see that based on the previous slides I showed you, this configuration of the sensor. Okay, so the configuration in the sense of two sensors opposed to one another is the configuration we want. But then if you look at an individual sensor where you have the element and the backing and the cabling coming out the back, that's definitely not going to fit in this Seth capsule. So right now we're just testing this particular configuration to be able to measure that diameter real time. If we set this up on a frame where we're going to internally pressurize that rod and measure it with digital image correlation and correlate that to the ability of these sensors to track the expansion real time. And when you see over on the right there, we were able to do that. There are two digital image correlation tracks, the top and the bottom track there. The one's purplish and one's red. But the one right in the middle, the blue, is the sensor signal. So we're tracking it well. You have the green and the red dots. Those are the measured diameter pre and post test. So this gave us an indication that this configuration could measure the rod diameter accurately, and B, it could measure it real time as the rod expanded. So now we started moving into the phase where we're trying to reconstruct it out of these sensors out of new materials in a different configuration that would fit in the Seth capsule and function the way we would like it to. So this slide is kind of all over the map. I have an idea in my head when I put it together, and then it changes when I get to this point. So we'll walk through it. Up on the top left, there's the 3D printed Seth capsule, which gives us an idea of just playing around what we could fit in there. And we knew if you bounce over all the way to the right, if you look at the top picture there, you see a full round. That's a bismuth-titanate element. It's a half inch in diameter, and in this particular case, we had this laser cut into 2 millimeter squares because one, we wanted to test other elements of this size, but two, we had a feeling we're going to have to shrink that sensor down in order to actually fit it down into the capsule where the test would happen. So if you look at the bottom middle, those are sensor prototypes based on what we could just build for an ultrasonic sensor with a full half-inch element, shrinking it down as much as possible, thinking that the leads would come out upward in a perpendicular direction, and we could fit it down in that capsule. But if you look just above it, you see a miniaturized sensor that uses a smaller piece, a 2 millimeter or 4 millimeter square that we cut. Well, most of it's round there. The actual element itself is square, and we'll get back to that sensor later. That's one of the later iterations. So it became a game of what you could fit in there. The smaller the sensor, the weaker the signal, but the larger the sensor, the less focused it is on the target because it's right up close to it. And so we're trying to get something that A, functions, and then B, we're going to test that at temperature and in water to make sure it holds up. So this is just a list of questions. I don't need to spend a whole lot of time on this, but if you look at each of these bullets, these are pieces of a sensor when put together, like the one I was showing you that we were testing in static and dynamic conditions. You have the element itself, and then you have a faceplate on the front, you have casing that it's wrapped in, you have backing to dampen ringing, and you have leads coming out of it for the signal. And each of these has to be bound together in some way to hold the thing together. If you want it to be a part of the sensor that is actually transmitting electrical signal, then you need that binding material to be electrically conductive. And if you want to not transmit the signal, you need it to be electrically insulating, and you need to match the coefficient of thermal expansion between the bonding agents and the components. And so really, when we started, we wanted to minimize the number of elements we actually had. Do we even need all of these? And so that was a way to minimize A, the size, and B, the matching of components. And you'll see this as we step through what we ended up looking at. So I have this broken down into prototypes. Each prototype actually represents a large number of experiments. And so, you know, each of these had presentations throughout the project. So keep in mind that I'm showing you representative pieces of steps through the project. When I have a prototype here, we started off by looking for bonding materials that were advertised to work at elevated conditions and were supposed to be water resistant or compatible in water environments. And not all of them had all of the properties we wanted, but we found a graphite adhesive that was electrically conductive to very high temperatures, and we used it first. We tested it, and that's what you actually see in the signal underneath it. That one failed pretty quickly. It wasn't a huge surprise, but what you're seeing there, each of those rows of signal is at a different temperature. When we use the graphite to bond the element to the backing, we got a fairly good signal. This is totally unoptimized sensor, so we're just looking for a response. We got a good signal at room temperature, but it failed really quickly as we heated it up. And this is just the graphite was not bonding, holding its bond over temperature to the pieces of the sensor. So we had a zirconia adhesive that we knew bound these materials better but it was electrically insulating, so it wouldn't transmit the signal that we wanted. So we started coming up with mixtures of the two to try to come up with a bond that was appropriately conductive and appropriately adhesive. And that led to an entire section of the experiment of the project of coming up with different recipes. And ultimately, we came up with a recipe that was roughly 60% zirconia and 40% graphite that was functioning well in tests, enough to move over to the right there, the prototype number 2. So all that sensor is, you see on the left side there, that's actually the bismuth titanate element itself exposed. And then it is connected to backing inside there with that 60 to 40 mixture of zirconia to graphite adhesives. And then the whole sensor was just coated in that zirconia adhesive. So that zirconia adhesive is functioning as an insulating boundary. You see the leads coming up out of it in a way that would fit down in the Seth capsule. And you see the face there of the sensor. It's not, again, not totally optimal. We would have, if this functions well, do some adjustments to it, but this is what the prototype looks like at this time. And if you look down beneath it, you can see that we put this thing in water, and on the left, we put a fuel pin in the water, or just a tube, a cladding tube in the water, and we got a good signal. We could see it. And we took it out, and when we ramped it up in temperature, I think this one went to 500 degrees, and we soaked it for a few hours and brought it back down, and we put it back in water, and we got the signal over on the right. So this thing worked very well when exposed to high temperatures. But then, you know, the next step here was we wanted to ship this off to Idaho, to Josh, to do tests in an autoclave to see if we could take it up to temperature and pressure with water, something that this treat capsule would see for the first part of a transient test. So the next step was just to let it soak in water and see how resistant it was to water. And unfortunately, leaving it for several hours in water, the sensor fell apart. So these components, well, we thought we were close. It wasn't water resistant enough to move forward. So moving to this third prototype, what we did was we introduced a casing with a steel cylinder to provide additional water resistance. And we used our combinations there of zirconia and graphite in different mixtures to try to control bonding and electrical signal as discussed previously. And we were getting good responses again, but it turned out that the bonding agents were even less resistant to water than we had hoped, because while it held up for a while, you can see right there, they actually started to erode away. And so you see the square element there completely exposed, where the bonding agent around it had corroded away or just dissolved into the water. So that put us up against another realization that this, you know, we had additional water problems to work on, which led to prototype 4 there on the right, which now we're backing back up. There's a couple issues we're having trying to bond very small pieces. So we moved back up first to a full 1 centimeter, half-inch element, the circle there. And now we're trying to expand that casing to a partial faceplate, so it's bent around the front of the element there. So now we're trying to get to where the water contacts as little of the bonding agent as possible. So we're still using these bonding agents, these two mixtures of these two that I mentioned previously, but we're hoping that we can minimize the water effect with this particular design, and, you know, if this works, continue the design in this path. And beneath it, you can see that the response before heating was good. In water, the response was good. But for some reason, this particular configuration failed repeatedly on heating. And so now it's becoming an issue of, is the heating causing cracking between of the bonding agent between the elements that were between the pieces of the sensor. Is it now a difference in the coefficient of thermal expansion that's causing it, as opposed to the water? It's constrained in a different way now, and so now we're looking at heat is the problem with this particular prototype. And so moving forward from that, and this slide got kind of discombobulated. The actual picture of prototype 5 is down at the bottom in the middle, and this is one that I showed on a previous slide. So at this point, we started making some fairly substantial changes to the material construction. Now we're shrinking it back down again. We're going to 4mm bismuth titanate element using that magic mixture there to attach the element to the backing. But now we're trying to paint a new type of bonding material on the front as a faceplate that's been shown to be more resistant to water. It's a stainless steel infused adhesive. And for additional pieces of the sensor, we're using another adhesive, which is a nanoparticle alumina adhesive, which is not electrically conductive and shows better water resistance. And so this one showed promise as well, but ultimately testing it through thermal cycling and water exposure, the signal degraded over time. And so we started to see that we needed to try some more investigation into what's causing it to fail, because at this point it's not entirely clear. Is it just water that's going through? Is it the heat that's causing bonding to fall apart? So on this last prototype over here, 6, at this point we realized that when we started looking at it, that the initial electrode that had been sprayed onto the back of these elements looked like it was starting to flake off itself. So we started to wonder, is it actually the bonding agent, or is it the actual manufacturer provided element that may be starting to fall apart at a temperature that it wasn't designed to function at? And so we started looking at different tests here, where we used, on the left there you see what we've done is we've sanded off the electrode that's on the back, and we've attached an electrode with a silver bond that we've had good success with in the past. And the same thing on the right there, but now we're using that zirconia to graphite mixture as the bond. So now we're testing sensors that have the original electrode taken off the back of the element and put in our own. And those signals you see at the bottom for each of those two, before and after heating and soaking, you see that the silver didn't work so well. But in this case, we're getting better responses with the zirconia graphite mixture. It's still degrading, but it's not degrading as much, and it's holding in there. So it's giving us some feedback that maybe this is an improvement that we can start building off of. And so this brings me to where we ended up. So the last thing that we tried was a different approach to the entire sensor itself. We took the larger 1/2-inch element, and we attached it to backing with our mixture of graphite and zirconia there. Part of the reason we're looking at this, even though I've showed you several times that this doesn't hold up in water, is that we weren't sure if it was an effect of trying to bond it to smaller pieces, and maybe if we're bonding it with larger pieces, we're going to get a better performance. But also we wanted to test this new approach here, where we were looking at trying to optimize these sensor sizes and distances to look at it the way I had showed you previously with the static test. Now, if we try to build something that is larger, and we're looking at multiple signals, the first reflection off the tube, the second reflection off the tube, and the reflection off what here is a plate for a test, but in the design would be the other piezo sensor on the other side of the tube. Can we use that signal to potentially look at the change, all of that holistic signal to look at the change. And so this test, we 3D printed a little holder there where we could put this sensor up against the tube at a distance that we expected it to be in the sensor, and we put it in a little tub of water, and you can see beneath it that this thing looked like it was working really well, but as expected, you know, it did hold up to water a lot better, but you know, 3 days, 72 hours in water, it started to fall apart. So this is where we ran out of funding. We had gone through a lot of iterations and saw some things. This was promising in the sense that now we saw something that was behaving better and better and better, but we never came up with a combination of components that functioned well enough in temperature and water exposure to move to the next test, which was the autoclave tests at Idaho, and then that would have been the gateway to potentially testing and treat, and that's the path this project took. That's my presentation.
Thank you for your presentation there. We'll take any questions, but I'd like to comment first that I can certainly sympathize with the environmental challenges. Water is certainly one of the best solvents there is, and can destroy a lot of good materials, especially at high temperatures and pressure. So it's a real challenge. Do you? I don't see any questions in the pane here, but I've got one. For future work, do you see a potential path forward for materials or packaging that it could be feasible in a water environment, or would it have to be? I mean, what would you try differently if you're given another go? Would you try to remove the problem by design, or how would you go about it?
Yeah, this thing had questions all along, all the way up to this, from could we just move it to air, which people said yes, but then that changes the medium through which the sound is transmitted, which changes the whole sensor. So people had designs in that pathway. They had all kinds of ideas to try within the water realm. This last design we showed, we believe you could get that full round in there and get a signal that you could see, which opens up a whole new set of ideas of, you know, if we know that our bonding material that we've come up with, this mixture, can hold the backing to the element, and we have this size that can work, that gives us some space to go in and put some electrodes and put a casing and faceplate around it and encapsulate it all. Now it's just coming down to the question of where you seal the casing and where you seal where the leads come out. Those are now the design questions. What do you use as an appropriate sealant? And I think that what we're seeing here on this last slide shows us that we're pretty close right there to being able to get something that would work, or at least test. And now we're just worried about how long do those internal components stay together if they're all potentially expanding at different rates as they heat up. So that's yeah, I mean, if we could continue, I think, you know, we would have 3 or 4 new iterations right here built off this last design that we would all believe, would hope would work. And I don't know, there's no way to know until you try it.
Yeah, I totally understand that. Well, I think it's time to go to our next presenter here.
Okay, thank you.
Our next presenter is Malvina from Idaho National Laboratory, and she'll be discussing the use of dimensional change as an interrogation method for silicon carbide monitors. Malvina, can you just put your presentation in presentation mode? Perfect, that looks great. And you can take it away.
Perfect, can you hear me just fine?
Yep, that's perfect.
Excellent. Go back. Thanks, Austin. So my name is Malvina Wilding. I am a nuclear instrumentation engineer at Idaho National Laboratory. And today my presentation is on the status of using the optical dilatometer method of evaluating the peak irradiation temperatures of silicon carbide passive monitors. So I'll jump right into the project overview, and I guess with the objectives. Your passive temperature monitors are really needed for when your real-time sensors are not practical or just too expensive to install in a radiation test. And the main purpose is to really provide a practical and reliable approach to estimate peak irradiation temperatures during your post-radiation examination for direct integration in radiation test designs. So commonly we have melt wire packages and silicon carbide monitors that go together. I will be focusing on the silicon carbide today. I'm sure Kiyo Fujimoto later today, she will talk more about the melt wires that we also work on. The participants for this work package, we have all from Idaho National Lab. I was the PI and also the work package manager. We have Austin Fleming, the technical point of contact, which he's also your moderator for today's session. We have also Kurt Davis, supporting engineer. He was mostly working on the resistivity method. I focus more on the optical dilatometry method. We also have Ashley Lemson and Corey Manning as our supporting technicians. Schedule-wise, we had a level 3 milestone that was completed by September of 2021. That was the deadline, and we created we had a summary report as an outcome from this that was titled Perform Comparative Assessment of Optical and Resistivity Measurement Methods for the Evaluation of Silicon Carbide Peak Temperature Monitors. So now I'll talk a little bit, I guess, background, what the difference between the resistivity method and the optical dilatometry methods are. So resistivity method is really as an accepted, a very robust measurement technique that's been used for a very long time, and the results are usually within the accuracies of 20 degrees Celsius. Your typical resistivity response is shown on the right-hand side top graph, where you have resistivity versus temperature. And as you have these samples cooked in the furnace, so this is shown on the resistivity method setup, bottom right picture, you have a furnace, there's controls for the furnace, and the spring-loaded sample fixture is right next to it. That's where you place your samples inside that to measure your resistivity. So every time you have to heat up your sample, place it into that fixture in order to measure your measurement for the resistivity, and that is plotted on that top graph, and each point, that's what's represented by that. And you create a band of minimum and maximum, and once you reach your data points for the resistivity reaches outside that band, that's the first data point represents your peak radiation temperature. So in this graph, it's shown that 320 was the 320 degrees Celsius was your peak radiation temperature. I guess some drawbacks for this method is the way we use it, at least at INL, is that this is a very time and labor intensive process, and it requires almost a near constant attention from trained staff. For example, it takes anywhere from 1 whole week to almost 3 weeks to analyze one of the samples. And this accounts for having technicians, engineer, RadCon, and also admin as the support for every single time we run these samples. So that's where most of the time and labor comes from. It also adds a lot of potential sources of measurement errors. So as the very first one is the potential result in oxidization of the silicon carbide temperature monitors. This is why sometimes it can take 3 weeks for us to analyze a sample, and that's because if our sample oxidizes during the measurement methods, we do have to send it back to get it deoxidized in order to finish the analysis. So that's another huge drawback. Also, another measurement errors that we get is usually due to the repeatedly transferring back and forth between this furnace and the test fixture, the sample, and I kind of talked about that. That's shown on the bottom right hand side, and also how you place your sample. So the samples that we work with is shown on the bottom right hand side. The only one that this method can analyze at this time is the rod, which is 12.5 millimeters long, and this rod is placed into that spring-loaded sample fixture, which is right the picture right next to that. And sometimes it's not easy just because it's so small. So you have to align it right. So I guess there's a lot of measuring errors that can come up during this measurement method. So those are some of the drawbacks. And obviously the last one is we have a, I guess, inventory of silicon carbide monitors that is shown on the bottom picture. We have 3mm disc and a 5mm disc and the 12.5mm rod. This method currently can only process the rod. So that's another huge drawback that this method has. And now I'm going to jump into the optical dilatometer method. So this method is very automated process. It requires very minimal setup time, and the dilatometer that we have set up in our lab is shown on the top right hand side picture. This is what we focus in FY20 of really purchasing, getting it set up and having it running. And you have the dilatometer on the top right hand side that sits on a floating bench top to minimize any type of measurement errors. That's mostly just the surrounding areas, any type of noise and vibrations. We want to minimize that from the dilatometer itself. Then you have on the left hand side the computer that also runs the software, and you have the gas box that sits under that controls our vacuum or inner gas controls. And then on the bottom right hand side, self-circulating cooling unit, and then on the bottom left hand side, that's where the vacuum pump sits. So very easy setup. It has everything it needs connected directly to the dilatometer locally there. And the biggest advantage here that the dilatometer can run under vacuum or inner gas. Actually, we've been running all of our samples under vacuum, and that's a key requirement for avoiding any oxidation issues that we have with the previous method for the silicon carbide temperature monitors. So that's a huge advantage. The machine itself is capable of operating all the way to 1400 degrees Celsius with the resolution of 0.1 degrees Celsius. However, our silicon carbide passive monitors are made to usually run anywhere from 2 to 800 degrees Celsius. That's the recommended temperature range. And the sensitivities for this method are anywhere from plus or minus 20 degrees Celsius. So again, very comparable to what the previous method has to offer regarding the sensitivities. And now another advantage is that this is a reduced time expense. As I mentioned, the previous method, we can take anywhere from 1 to 3 weeks. Here we're talking anywhere from 2 to 3 days. So that's a huge time reduction right there. And it's literally, since it's an automated system, you don't have to have a constant staff. You literally have your sample set up, you run the specific program, you leave it running for however long it needs to be run, and then you come back, turn everything off, and save your data. I mean, it's very automated, simple process. So why I say 2 to 3 days, and that's because it just depends on your target temperature. Obviously, the higher target temperature, the longer it takes to anneal your sample. And I'll talk a little bit more of that in the results section. Another bonus, I guess, or benefit is that it has a contactless dilatometric measurement system. So this is shown in the middle picture on the right-hand side. The dilatometer, the furnace itself, this is how small the furnace is too, which that's probably why it's so much easier to control the vacuum and have your oxygen minimized in there. And your samples sit on a little ceramic plate. There's no forces or any adjustments. You literally place your sample on top of that ceramic plate, and the green is represented by the green laser that uses the optically to measure your dimensional changes of your sample. So again, this system allows your samples to freely expand and shrink during your heating and cooling without any interference from mechanical contacts. That's another drawback we had with the previous method that is resolved using this machine. And finally, the last one is that we can process all of our silicon carbide temperature monitors, not just the one we have in stock, which are shown again on the bottom right-hand side. Those are the 3 ones that we offer. They all fit in there. However, we can look into using any other ones if we ever have to in the future. The dimensions for that, you can go as little as 0.3 millimeters to 30 millimeters in length with a maximum height of 10 millimeters. So that gives us, again, a much broader range for measuring our silicon carbide temperature monitors, either currently or in the future. now I will jump right into the technology impacts. So I've mentioned some of this already before, but passive monitors really provide an easy, practical, and robust approach to measure your radiation peak temperatures during your post-radiation examination while requiring no feed-throughs, leads that are much more complex to the current more complex real-time temperature sensors. So they're just very easy, and our silicon carbide temperatures are easy to use because we have them already in an inventory. We literally pick specific geometry and size. We have them cleaned, packaged up, and you can literally put it the next day into your experiment. So they're very easy to use. And then we obviously wait till they're irradiated for our analysis to give you the right temperature, peak temperature measurements. They also been chosen because they have a very proven history for use by stakeholders for deployment, requiring continuing deployment and characterization to assure successful integration with program schedules and objectives. They have been used for a long time. I guess silicon carbide monitors are well known and well established technology. It's just, I guess, the way you analyze it is the only more innovative ways of improving your process. Further developed the temperature passive monitor capability for your wider range of temperatures, geometries, and neutron damage. So this is really where the optical dilatometry comes in, being able to expand all of those capabilities even further to what the resistivity method had limitations on. And finally, it facilitates the development of advanced sensors and instrumentation with cross-cutting technology development to support the existing fleet, advanced reactor technology, and advancing your fuel cycle technology development. Obviously, temperature is a critical measurement that pretty much all experiments require in some shape or form. So having passive silicon carbide monitors is critical for that mission. So now, before I guess share my accomplishments and results, I wanted to talk about the issues, or I guess difficulties we encountered this year. So we've worked with NSUF, that's our biggest client, I guess, or needed of silicon carbide monitors. We had a plan to have them provide us 10 silicon carbide temperature monitors. We have 2 different experiments that they told us that they would use these silicon carbides from, and we have BSU 8242 that had 3 silicon carbide monitors available, and where they placed each of them per each of their capsules for a total of 7 capsules, and they were all located in the middle of the capsule. We also have the GE Hitachi experiment that had 3 silicon carbide rods, and all of those 3 were placed into one capsule where they were located in the bottom, middle, and top of the capsule. So that was the original plan. However, we ran into multiple delays throughout the whole entire fiscal year. So first it started with even acquiring the samples. So I guess since those experiments were done a few years ago, they had to first even be able to find all the samples, deassemble the capsules, and be able to have them shipped at MFC to ATR, where we do our cleaning. So shipping, again, shipping anything that's radioactive, that always takes longer than anything else. So that was another delays in that. And finally, the cleaning. So cleaning, this is the biggest issue, or I guess we try to decontaminate and also deoxidize anything on the surface of the silicon carbide temperature monitors. So this is where we do the HF wash at ATR. And that's where currently most of the silicon carbide monitors are still at as we speak. And we only received 1 of them out of the 10 initially planned for in the fiscal year. One highlight, I guess, the only one that we received was the very first silicon carbide temperature monitors that was actually cleaned to a point of free release. So there was no radiation detected above the background. So we could handle it just like any other silicon carbide we have in our inventory, which made shipping from ATR to us and handling it much easier without extra, I guess, cost and time to process that. So that did help towards the end of the fiscal year. And now I'll hop into the our optical dilatometer results. So since we only had one silicon carbide monitor, we chose to obviously use the optical dilatometer instead of using the resistivity. We've used the resistivity for many, many years, so we know how it works. but we really wanted to see how the optical dilatometer does with an actual silicon carbide radiated temperature monitor. So this one's NSGF sample was from BSU 8242 experiment. Their target temperature was 300 degrees Celsius with an exposure of 1 dPa. The sample ID was KGT3357, and that's how all of my graphs will be numbered to, just for that specific sample. So as I say, how we handle our samples. So anytime an experiment needs silicon carbide monitors, so we clean them and we measure them and we record all that before we send it over to the experiment. So the measurements before the radiation were that the diameter was 0.98 millimeters and the length was 12.5 millimeters measured of the rod. We also, since this is an NSGF project, they commonly ask for silicon carbide and traditional melt wire packages to put together into their capsules. So we had another reference how we could at least look into is the evaluated melt wire packages, and their results showed that this specific experiment had a temperature range between 238.6 degrees Celsius all the way to 271.5 degrees Celsius. I guess if some of you are not aware how traditional melt wire works, you pretty much have 3 bulk materials and you look which one melted at what temperature, and this is why you have a range instead of a specific peak radiation temperature, because you can only tell if either the material melted or not. So that's the only, I guess, drawback for traditional melt wires. You get a range versus a specific peak radiation temperature. Either way, this was very helpful for us to at least know what the temperatures we're looking for besides just the target temperature of 300 degrees Celsius, because you can see that the temperature achieved was much lower than the 300, and that's usually the case, but sometimes you can have that it overshoots. So this is where it brings me into the dilatometer program. The way we run it, we usually use the target temperature and add additional 300 degrees Celsius to that, and that's just to make sure we don't miss anything in case if your experiment does overshoot for some odd reason. I mean, things happen all the time, so you want to make sure you anneal that accordingly to the full range. So in this case, since our target temperature was 300 degrees Celsius, we ran the dilatometer all the way to 600 degrees Celsius with the heating rate of 1 Celsius per minute. We held it there for 5 minutes at 600 degrees Celsius and then slowly cooled it down at 2.5 Celsius per minute as the cooling rate. The graph on the right hand side, it shows you the temperature profile for this program, and we have temperature versus time. The red line is representing what the sample temperature measured versus your black line, what was the furnace temperature. And we want to make sure that they're both almost identical. And in this case, you can actually see that the lines overlap, they're linear. There's no abnormal behavior within the heating or cooling, which is exactly what we wanted to see. Very plain, linear, and simple. And now, I guess what I'm going to talk about different methods. Since this was the very first silicon carbide monitor that we really investigated with the optical dilatometry, we wanted to investigate different methods and see which one will be the main method that we will use forward for all of the samples. So this is where we look at the change in length. So this is how the optical dilatometer works. It pretty much measures any changes in your volume. So in this case, since we're using a rod, we were interested only in the change in length. So this graph represents change in length over initial length, pretty much strain of your sample over temperature of the sample. And red, it represents the heating rate. You have blue represents the cooling rate. And then the black one is where you have the delta. It's the heating minus cooling. And that line is actually what we'll be using for the following 2 other methods. It's just the black line. Also, if you can see, maybe yellow is probably hard to see, but we have a yellow dot. So that dot represents the maximum length of change during your heating process, and the temperature of that one was 264.3 degrees Celsius. So we believe with this method, we can estimate that the peak radiation temperature was around 264 degrees Celsius. That still falls within the melt wire temperature range. So we confirm that indeed this measured an accurate temperature. And another thing, I guess, with the lengths, because we can measure the change in volume of your samples, we can also discover how the whole sample changes before radiation all the way to post annealing. So as I mentioned, we measured our silicon carbide monitor right before we sent it off to the experiment. So once we received it from the radiation, the length has changed, and we measured it with the dilatometer. We read it as 12.6081 millimeters. So we did see quite a bit of swelling, I guess, from the radiation, and that's something that we were expected. Obviously, the volume change of about 108 millimeters, that again. But then after we anneal it, because we're annealing it past the radiation temperatures, a lot of the point defects that you originally have created in a reactor actually anneal out in the furnace. So that's where you have some shrinkage. And in this case, we did see that past, once we anneal it in the dilatometer, it did shrink by 0.027 millimeters. So it's kind of nice to have that tool, I guess, is available to you to also investigate how your sample behaves in different stages throughout the whole, I guess, process. Now I'm going to talk about method 2. So this one requires fitting 2 different lines with our data point. Again, we're focusing using just the black line here, that's what we're using for these following methods. So the first line that we fitted was right below the radiation temperature, and that one is shown in the black dotted line. That represents the fit line, the first fit line that we had to create. The second fit line we do is right after your radiation temperature, which is shown in dotted orange line. And pretty much the intersection between both lines is the estimated radiation temperature, which is represented by a black dot, and it was 265.5 degrees Celsius. Again, very close to the previous method, and it agrees with the evaluated melt wire temperature range, which wasn't anywhere below or outside of that range, which is great. And finally, the third method is a little bit more advanced, I guess, more advanced compared to the other two, because you have to fit 3 lines versus just 2 lines. So in this graph, we have a line first fitted that we center at the design temperature. So this is the target temperature that the experiment gives you, which we use as a 300 degrees Celsius. That temperature is marked with the red dot, and the actual fitted line that's centered around that temperature is shown in black dotted line. Then we also fit the line again before the radiation temperature. That one is shown in the orange dotted line. And another line that we fit is right where the data begins to curve downwards after your flat line initially in the graph, and that is shown in the green dotted line. And now we're going to do 2 different intersections. The first intersection of your black dotted and orange dotted lines represents the peak temperature, peak radiation temperature of 266.7 degrees Celsius. That's marked with the yellow square. And then the second intersection is between the green and orange dotted lines. That represents where the radiation actually started, which was at 240 degrees Celsius. And if you can look, this is very close to what the melt wire temperature range actually has, which is not surprising. So this method gives you much better understanding and I guess better estimated full temperature range where your radiation starts versus where it actually peaks. And I guess this is kind of a recap again of all the different accomplishments and the results we did. So we chose only to do optical dilatometry using that one annealed sample, KGT3357. We had ran it without any issues or errors. Also, both the furnace and sample annealing temperature profiles showed that they are linear, very similar behavior. And we had all 3 methods for identifying peak radiation temperatures. They all fall within the evaluated melt wire temperature range between 238 and 272. So the first method gives you the peak radiation temperature of 264.3. Second is 265.5. And finally, the third gives you an actual range where your initial radiation started at 240 and it peaked at 266.7. So we are going to be using probably the third method as the most accurate and giving you an actual temperature range for future analysis. And we're also planning to use the remaining 9 to finalize all of the information, I guess, for process, how much process time, cost, and accuracy, kind of just to dial it down for the optical dilatometry method. And that brings me to conclusions for my whole entire talk. So initially, we plan to conduct a comparative assessment between the optical dilatometer method as well as the resistivity method using all 10 NSUF silicon carbide temperature monitors. However, unfortunately, we encountered multiple delays from acquiring, shipping, and all the way to cleaning of the silicon carbide monitors, that this project was only able to process one silicon carbide temperature monitor at this time. And the optical dilatometer measurements indicated that indeed the silicon carbide temperature monitor peaked. The radiation temperature started at 240 and it peaked at 267 degrees Celsius. And again, the sensitivities are approximately plus or minus 20 degrees Celsius. Additionally, this temperature again falls with our evaluated melt wire temperature range, which was great. And we still are going to focus now on the remaining 6 silicon carbide temperature monitors from the BSU 8242 experiment, and also 3 from the General Electric Hitachi experiment that will be used in the future work to further validate the optical dilatometer method for measuring silicon carbide peak radiation temperatures. And that will bring me to my conclusions. There's my contact information and any references or my references that I use for this talk, and I'll take questions.
Thank you, Malvina. That was an excellent presentation. It looks like we've already got some questions coming in here. So Oronel has spent many decades evaluating how to best process dilatometry data and determine that instantaneous coefficient of thermal expansion is much more effective compared to just looking at the length change. Have you tried this approach?
We tried, however, we're still trying to fully understand what our optical dilatometer actually measures for the, I guess it's called alpha in that case. That's why we only focus on the change in length initially, just to start basic and then work from there. We liked simple methods, I guess, more versus more complicated. I know Oak Ridge has done a lot of statistical and modeling based on that. We're not there yet. We're still starting initially with just the change in length. But yes, we did look into that. We just haven't gotten to the results we wanted to in order to share that.
For your answer, that was an excellent question from our audience. I actually had a question on your method 3, I believe it was, on slide 10. The process seems to be dependent on inputs from the design.
Yes.
Can you comment on maybe errors that would be encountered if those were incorrect, or if you think that other methods would be better suited if you got some deviation or something?
That is a valid question. So we obviously have a design temperature and it never is close to that in a lot of the experiments. So in that case, instead of using the design temperature, I would often use it from the first method, that temperature as the design, because that would be much more accurate representation. And we did think about using that in the future in case if the design temperature seems a little odd or off or maybe incorrect. But you're right, that would introduce quite a bit of an error into this measurement.
Okay, perfect, thank you, appreciate it. I think we're about ready to move on to our next presentation. I'd like to thank Malvina again for her presentation.
Thank you.
Next up, we have Ahmad Al-Rashdan from Idaho National Laboratory, and he will also be talking about silicon carbide monitors, specifically a 2-cycle automated approach to electrical resistivity measurement of silicon carbide monitors for peak irradiation temperature. And we can see your PowerPoint. Can you just throw it in? Yep. Perfect. Looks great, Ahmad.
And can you hear me, Austin?
Yep. You sound great.
Great. Thank you. Good morning, everyone. Thank you, Austin, for the introduction and for the program for inviting me to this talk. The topic of my discussion is a continuation on what Malvina was talking about, which is the use of silicon carbide monitors for peak radiation temperature. However, in this presentation, we will be talking about a different approach. So we're using electrical resistivity measurement, and the aim of this effort was to develop an automated way to extract these measurements to enable us to extract the peak radiation temperature from the silicon carbide monitors. So to start with, I know Malvina touched on some of this, but just in case you just joined in, what we're doing here, we're using silicon carbide in the form of a sensor for measuring peak radiation temperatures. And I'm showing you here, let's see if I can find my mouse, there it is. I'm showing you here some example of the monitors or the sensors that are used in these experiments. Usually these experiments are capsule type. So we place this in, and when the silicon carbide is experiencing radiation, is being irradiated, it would experience some radiation damage. That radiation damage would change its physical properties. And the idea here is that if we anneal these samples beyond the temperature at which these at which the radiation damage occurred, then we would remove these damages, and then we would end up with a change of behavior that we can use to extract the peak radiation temperature. So in terms of electrical resistivity, which is one of the characteristics of the silicon carbide, or one of the ways we extract this peak radiation temperature, we have been doing historically is we would measure the electrical resistance for the monitor, just like I'm showing you here in this curve in the red dots. And then we would start annealing the samples, and every time we anneal it, we increase the temperature of the annealing, the maximum annealing temperature, and then take it back to the normal room environment temperature, and then measure the resistance. So if the concept here is that if you haven't reached your radiation temperature, then you will always have the same temperature, the same baseline temperature, because of the fact that you haven't annealed anything out from the monitor or the sample. Once you hit that peak radiation temperature, then you will see a departure from the typical resistance you see, just like we're showing you here, and that departure is used for to extract what is the peak radiation temperature. So that's a concept that's been typically used to extract the peak radiation temperature using electrical resistivity from silicon carbide monitors. The process, as Malvina mentioned in her presentation, is manual and it's time consuming. So every one of these dots is actually a complete cycle. What that means is you would place the monitor in a furnace, you would heat it up to that specific temperature, and then you would take it out, put it in a control chamber with a device like this one, and measure the resistance of the electrical resistance of the silicon carbide at controlled temperature and environment to build basically this curve. And then once you see the departure, you can start basically changing the increments of temperature to get to confirm that this is actually a departure, and then you extract the temperature. So what we wanted to do here is we wanted to automate this, and the reason we wanted to do that is, of course, there's efficiency. We don't think we need all these cycles to get there, or that was the hypothesis. Do we actually need all these cycles to get there? Can we just run the whole process at once, just anneal it to the maximum temperature we expect, for example, 500 degrees, and go back down at once, so we can have one cycle or maybe just a couple of cycles and get the same information that we got here. And also the other benefit of this is that this is, even though this is a kind of a continuous process, I mean, we are incrementing over a continuous range of temperatures, we're still discretizing it. So we are moving in increments here, and we design these increments to be a certain difference of temperature. That could be 10 degrees, 20 degrees. It depends on how close you think you would be to the peak radiation temperature. So we're kind of discretizing this, which kind of it's a compromise on the accuracy side. So in 2007, we started this effort, and the aim was, could we first of all automate this process? So we designed a platform to do exactly that, and the idea here is that we would have a controllable furnace that we can control the heat rate of the furnace, and we can measure the temperature feedback from our furnace and from our experiment with the silicon carbide, and then use that to further control the furnace to make sure we're following a certain profile. So we developed this setup, and then created a software. What the software does is you can feed in a plan, and you can say, I want to follow a certain temperature profile in Excel, and then the experiment will follow. One of the things we did at that time is we didn't really spend much time on the sample holder. So we wanted just initially to get the automation part done. So we built something quick and dirty, and then we had to, once we got it running and we got the measurements, we realized that there are a lot of issues with the holder. So we spent a lot of time on designing the proper holder to do that. And then once we did that, we started qualifying the process. So we ran experiments. We looked at some issues that I will touch on in the next slides. I'm showing here one of the issues, which is the thermal transient effect of the furnace. And then once it's done, we qualified it. We were confident we're getting good results. We moved the setup into a radiation controlled environment, and then actually performed the experiments using 9 radiated silicon carbide monitors, got the data, and then had to spend some time excuse me, analyzing the data and getting the results out. And as this process has spanned over a few years, there were a lot of people involved and contributed significantly to this effort, and I'm listing here the names of the R&D team. Also, this effort started as an NSUF-funded effort and then evolved into an ASI effort. And I would like to acknowledge all the contributors. So the topic of my presentation here is going to be mostly on the lower part of this figure. So the holder design and how we reduce the effects of uncertainty within the experiment itself, and then what kind of how did we apply it, what kind of data we got, and how did we apply the analysis. To start with, looking at the holder design, I'm gonna talk about the holder first, and then I'll explain to you why we ended up with this design based on some of the challenges we faced from the previous holder. And actually, this design came after several iterations. It was just it took us almost a year to get there. If you look at this holder design, it has basically 2 parts. There's a lower part and a top part. And the top part would actually lie on the lower part on 3 contact points, which I'm marking here as 1, 2, and 3. Now, points 2 and 3 that you see here, you can actually look at these in a zoomed in format with a monitor here, and this figure here are meant to make sure that the weight of the top part is pushing against the monitor, and we would establish 4 points of contact like I'm showing you here. So this is the ideal case. We would have at 8 mm, we'd have the bottom peripherals and the top ones at 10 mm. And then what we would do is we can add weights on top of the top part, and this is aimed to put more pressure on the monitor to make sure the contact is established and it doesn't move. Now, why did we do this? So when we started looking at the monitors, one of the challenges was contact resistance, because contact resistance is first of all it's pressure dependent, and it's temperature dependent. And when we thought about using some form of springs, but the problem is that stiffness of the spring itself is also temperature dependent. So when we started experimenting with that, we realized that we're actually measuring the stiffness change of the spring rather than measuring actually the silicon carbide monitor resistance. So And the other challenge with the springs is that they lose their stiffness when they're heated, especially that we're talking about going up to 800 degrees Celsius. So we wanted to find a different force that can still sustain enough pressure to reduce the contact resistance to the point where we have valid resistance measurements for the silicon carbide monitors. And that's why we leveraged weights, and we established this concept that we would have 3 points of contact, and the weight would be almost more than half of the weight would be actually on the sample, and we can increase the weight as much as we want to get the contact we're looking for. So once we did this, we conducted some results, and with the fact that we have 4 points of contact on the monitor, we could actually calculate the contact resistance. and we found that within 100 to 150 degrees Celsius, in this case we drop enough. It drops enough to become basically noise, and we can live with it. The other aspect of the holder that we had to look at is the thermal expansion, because of the fact that the holder is going to have to withstand temperatures up to 800 degrees Celsius. So there will be, it has to be metallic, and and metal will expand. So there will be movement, and that will impact also our measurements. So we ended up designing what I'm showing you here. So what this is, it's a 3D printed peripheral that is that's connected to the setup through ceramic bolts and nuts. And we designed it in a way that when the holder is actually expanding due to temperature, the impacts on the movement of these parts is minimal. So that took care of the thermal expansion side. The third source of uncertainty was thermal transients. So I'm showing you here a curve of two thermocouples for the same experiment. So one thermocouple was in the furnace, and the other one was very close to the holder. So actually we got it through this hole here to be really close to the experiment. And as you can see, if we really increase the rate of our heating, and this is just an experimental case, we ramped it up as fast as we can, and you can see that the difference between the temperature in the holder and the setup is significant. So we kept reducing it to the point where these curves were within 10 degrees difference. So we really shrank that difference significantly and by controlling the heating rate. And finally, oxidation. And in this case, I don't mean the silicon carbide oxidation. We also had a problem with the peripherals oxidizing because they are also heated. So we had to coat them with platinum, and that once we did all these, we actually ran a few experiments using non-radiated silicon carbide monitors to test that the process is repeatable and we're getting consistent results, and it looks like it's working just fine before we move to the next part, which is the analysis. So when we looked at the measurements and thought about initially before we actually ran this, where's my mouse? Yeah, there it is. Before we ran this, we thought about what is the ideal case? What are we gonna see if we insert a monitor, a silicon carbide monitor, and we anneal it all the way up to a certain temperature, and in this case we were aiming for 450 degrees Celsius as the max, and drop back down. What kind of behavior we would see? And this is what we envisioned. And what I'm showing you here are two curves. One would be the ideal case, which is this dashed line. Excuse me. And in that dashed line, this is just the case when you don't have any irradiation damage. This is your pre-radiation sample. And then because of the fact that you irradiated the monitor, you'll have some swelling with the sample. Your resistance is going to go down, and you'll see something similar to this. It's going to be lower, and then as you anneal it down, and as soon as you approach that peak irradiation temperature, you're going to start annealing these damages out from the silicon carbide. And then when that happens, the curves are going to start converging. So you will end up, once you pass your annealing temperature, you're going to end up with the same behavior that you would expect for a pre-annealed sample. Now, and this is basically what I'm showing you here in formula. So I'm saying when you approach the radiation temperature, your RA, which is your annealing resistance, is going to match your baseline resistance, which is the dashed line. And once you exceed it, you're basically going into an identical shape. So that's what's happening here. Then when we thought about it more, and this was also when we started conducting some experiments, we realized that this is not the case. Things are going to move. I just showed you in the previous slide multiple uncertainty sources. So things are going to move. It's not going to be an ideal case. We might end up with something similar to this. These offsets and change in slope could be because of an offset because of a movement of a sample. The change with the slope could be because of the transients, the thermal transients that you're experiencing. So you might end up with something similar to this. That's the more realistic case. So when you get to the TR, you might not, RA might not approach RB. And going beyond that, RA might not equals RB. And again, RA is the annealing resistance, so annealing curve, and RB is the baseline, which is the pre-annealing, pre-radiation behavior. So when we actually ran this, we ended up with something similar to this. So what I'm showing here is it wasn't easy for us to see all the differences we were expecting to see. Everything was really close. So none of the expectations were seen. However, we still thought the concept behind this is valid, and we just had to create a way to magnify these shapes that we expected to see. And to do that, what we ended up doing is we ran 2 cycles, and I'm showing you here R1 heating, R1 cooling, R2 heating, R2 cooling. So 2 cycles, each has a heating and a cooling curve. And then we decided out of these 4 different curves we ended up with, we are going to use the first one as our annealing curve. So that's going to be our, because it's the first time you're annealing the sample. So that should be your annealing curve. And all the other ones would be used to create a baseline. And of course, you could think about the fact that, well, we can just run one and use the first one as annealing and the second one as base. That is correct, but we realized that with the experiments that we need more curves to reduce the uncertainty, because if the more you do this, I mean, we're calling this 2 cycles, so you're actually running it 2 times, but if you do it even more, you have a better RB, you can get maybe even better results. It goes into a compromise between how much time you want to spend on this versus the accuracy you want to end up with. So if we do this and we start comparing RA to RB, and the way we did it, we actually subtracted the base from the annealing curve, we can magnify these shapes and find something more similar. And this is what I'm showing you here. So this is the formula, and let me talk about this figure specifically. So the red line here is our RA when RA was selected to be R1H. And if I go back, this is what I'm showing here. So R1 heating, the first cycle heating, is our baseline. Now, in theory, we wanted to validate that this curve that I just showed you is valid. So what we did is we actually moved RA instead of just being R1H. In one case, we did it this way. In the other case, we moved it to R1C, R2H, R2C. So we moved RA to the different curves and we converted to the rest as a baseline. So, and this is what I'm showing you here. So in this case, RA was R1H. In this case, RA was R1C, and so on. And when we do that with the R1H, we ended up with this curve that I'm showing you here. And what this showed us is there was a point in the measurement that it went from dropping, the resistance difference went from dropping to increasing. There was a sudden change. If you think about it, this is similar to what we expected here. Now, to get to this shape, we had to add some mathematical adjustments. We added the alpha, which is an offset, because this is we had to plot this on a log scale. I should have mentioned that. Once we had the difference, we had to plot it on a log scale to be able to magnify the differences. And we had the alpha as an offset to make sure we don't fall in the negative range, so that because we can't find, there is no log for a negative. And also we realized that because of the offset, this here doesn't have to be always the case. I mean, I'm showed you here that we started at a lower than initial resistance. In others, we could start actually at higher because things might have moved. So we needed to align that, and that's why we used the sign as at 0 point to make sure that it is in the positive side, because we are actually using a minimum function. So once we apply this and we apply a minimum function, we can find this point. And this, it would be the point, it's an estimation of the point of change of direction between the difference of the resistance. So I'm showing you here to the right the table of the results. I have plots for all the different monitors, but I decided not to include them today in the presentation because it's going to take us a lot of time to go through them all. But instead, I'm just showing you the table of what we got. So this is the first sample. This is the name of the sample. This column here is if it's describing if this sample was actually previously annealed. And I'll come to that in a minute. Why do I have this? This is the dose that this sample experienced. This is what we expected. So TE is expected, meaning when we got these monitors or these samples from the research reactor that irradiated these, they gave us these temperatures as what we should get, more or less. Now, when we applied this method, as you can see, this is got us 306.5. Converted to 310, we were really accurate. We also converted to the manual method. So this set of samples, and I have 9 of them here, we split them into A and B. A were manually, the peak radiation temperature was manually extracted. The This is what I was talking about, the manual approach of heating and cooling earlier, and what Malvina also talked about. The B was the samples we were playing with, or experimenting with, I shouldn't say playing. When we convert this to the manual, we were always getting better results. So I'm showing you here this case, but the interesting thing is that these samples here were already annealed by the manual approach. So we started with these and we were playing, I keep saying playing, so I apologize, experimenting with them. And we wanted to test the approach first using them. But the interesting thing is that we found out that there's enough residual defects from the radiation that was not annealed out that we actually got some measurements. So if you look at this sample, this was already annealed and it actually was annealed to 380 degrees previously using the manual approach that got us the temperature of 320, and we still got 312 when we applied this. So we were really close. Same thing here. This was annealed to 390 and we still got the temperature out. So we could still apply this and get relatively comparable results, or sometimes more accurate results. I know I just saw something on my screen. I hope it's not going to freeze. My point here is, even though these were annealed, we still ended up getting comparable results. And there was two exceptions to this. The first is there are a couple of samples that were previously annealed to 490 degrees, and they had low dose. They had 0.5 dPa dose. Okay, I don't know what happened. Okay, I expected this to happen. Sorry, this thing popped up, and I think it caused the whole machine to freeze. Can you guys hear me?
Yeah, we can hear you.
So I apologize. I heard this, but apparently micro break is forcing me to take a break. So I'm just going to continue with the presentation as is, and I don't know how to kill this. Maybe I just do this. Sorry about that.
Apparently you're working too hard, Ahmad. That's what it's telling you.
Yeah, it happens sometimes, and I think it's gone. All right, never mind. Then I can go back to this. Sorry about that. All right. So as I said, there are two exceptions when the monitors had a low dose and had really been annealed to high temperatures. We didn't see anything come out, so our method didn't work, which is fine. Again, we were just surprised anyway in the first place that we can even measure something from these samples, given that they were already annealed. And of course, the ones that were not annealed before, we got really good results out of these. Are you there, by the way, Austin? Can you hear me?
Yep, we can hear you. See your slides just fine.
Okay, perfect. Thank you. My machine is acting weird. Sorry about that. So conclusions. We out of 9 monitors that we monitored, that we experimented with, 7 gave us actually comparable results to the manual annealing process. And the other 2 that didn't were the ones that I mentioned had been annealed before to high temperatures, so we didn't really get anything out of them. In average, we got a standard deviation error of 15.2. When we convert this to the results we got for the manual ones, it was around 23.8. So there was actually an increase of accuracy. And as I mentioned, this is the kind of the weird conclusion we ended up with, is that we can still see some residual defects that had not been annealed out from the manual annealing process, and we could run this afterwards and get some also good results. And as I mentioned, there were some exceptions. So why did we do all this? What is the benefit out of this? Malvina touched on this, and I'm touching on it again. So we ended up running with a heating rate of 26% power. So our furnace is running at 26% power, and at that rate, we ended up with a heating and cooling cycle of around 15 hours. And I mentioned to you that we're running 2 cycles to get the 4 curves I showed you. So basically, in 2 days, you can run this and get enough results to get you the measurement. And the other benefit is that this is really a continuous range of temperature measurement versus the manual approach was more discretized. Remember, we had to go up and down heating and cooling to a certain temperature. So we're really discretizing the range when we're doing that. And I've seen also some efforts that are out there to automate the process, also doing the same process, annealing and cooling just in an automated fashion. This was just an attempt for us to actually do this in a continuous range, and with the hypothesis that this would improve the accuracy. And I think we kind of saw that with the samples we tried. And I know this is a short presentation, so we have a journal paper that we just submitted recently to a journal paper, and hopefully, sorry, to a journal, and hopefully we will get it published soon. So there will be a lot more details about how we set up the experiment, what kind of results we got, all the curves that for the resistances that we got, and it should be really conclusive of the research. With that, I end up the presentation and take questions.
Thank you, Ahmad. That was an excellent presentation. I'd like to start out by pointing out how much he enjoys his research, and that experimenting is considered playing. So it's a good sign there.
Thank you.
I actually had a question for you. The plots you provided, you know, they're a function of temperature, and you're sweeping through temperatures and measuring resistivity. What can you comment on basically the time response there, like how long that curve takes, and if there's a heating rate that you were targeting or something to move through that curve?
So the time response, so we ended up going with, so actually there was an interesting challenge there, and I'm glad you asked this. Initially, we were, if you remember when I talked about the setup, we adopted an approach where we forced the temperature of the furnace to follow a certain pattern. So we were loading a pattern saying, at this time you should be at this temperature, and at this time should be at the next, for example, a minute you should be at the next temperature, and so on. So the control was what we want in time. The problem with this approach when we applied this is that it caused dribbles in the data, because the furnace was actually turning on, heating a bit, and then shutting down, and waiting for us to get another instruction from the controller, from the program, to heat again. This heating and cooling process caused ripples and caused us issues with the data when we looked at it. So we moved away from that, and we said, no, we're gonna just go with a constant heating rate, which is what I showed you here. So it was at 26% power. And we optimized this based on what I showed you earlier with the thermal performance. So sorry, they're here. So we ran different powers. We looked at how bad was the thermal transients between them, because we wanted the thermal transient to be minimized. Of course, it's a source of uncertainty, but we also don't want it to be too slow that it takes really days to get each cycle. So it was an optimization problem. We did this to the point where the curves were basically really close enough for us to have confidence that the thermal transient effects are minimal, and that power was the decided power was 26%, and that landed into 15 hours of heating and cooling per cycle.
Okay,
that's
so maybe if you were
answer, Austin.
No, it's perfect. So if you're doing a different system, maybe you'd have to optimize that again because of the controls of the furnace or whatnot. But
correct, that is correct.
Okay, perfect. Check and see if there's any other questions here. I don't see any other ones that have come in.
No, I just want to mention there was a comment from Chris that related more to Malvina's presentation earlier. But it's really close to what Ahmad is doing, in essence, optimizing, if you want, the way that you analyze the data. And also in the case, this was for the dilatometer, but we expect Ahmad will continue to contribute to the best and most to optimize, basically, or automate as much as possible the reading of this data, whether it's resistivity or whether it's dilatometer, so that we can optimize time, essentially, because we are going to receive a lot of this silicon carbide monitors in the near future. So I also popped up Austin to introduce you, because I understand you will present the work on LVDTs, since Kurt Davis cannot be with us today or this week. So yes, we will discuss that, Ahmad, with Chris and Malvina as we move forward in the year. Thank you for your contribution. And, Austin will now present our work on the LVDTs, and specifically the initial conversation and talk will be related to their design integration, which is always a challenge, or always the fun and most interesting part of using LVDTs for irradiation experiments. Go ahead, Austin. Thanks.
Thank you, Patrick. You can see my slides okay?
Yes, and hear you properly. So start.
Perfect.
Anytime.
So I am not Kurt Davis. I am Austin Fleming, but this is his presentation here, and I will be giving it today. I'm pretty aware of all the work that he's done, so I think I'll be able to present the material in a reasonable manner, but probably not as well as he could. So I'll be talking about the LVDT design and integration and calibration into a whole bunch of different things. So a little bit of background. Linear variable differential transformer, I'll refer to it as a LVDT for the rest of the talk, or LVDTs. It's an electromechanical transducer that converts motion of a core to an electrical signal. How it works is there's a primary winding that is energized, is driven electrically, and then the position of this core, there's two other windings, coils, and this core determines the coupling between the primary and these secondary coils. So if it's more, on this left side, you'd have more coupling between the primary coil and the secondary coil on the left than the right. And then you can read out in several different ways the voltages or currents generated on these secondary coils and compare their values. It is a very robust technology. It's common in many industries, many applications. But at its core, it translates a position of the core to an electrical signal. So it's a displacement or a elongation measurement, if you will. Then I'll throw an interesting little tidbit in there, is that the resolution of these sensors is really only determined by the electronics that are reading them out, which is kind of unique. So there's that. And the other really interesting thing with these is you can change many other measurement parameters of interest into an elongation. All right, so take pressure, for example, is a common one. If you couple this with a bellows, so tie that core to a bellows, and then as pressure changes, that bellows compresses or elongates, it can displace that core in the LVDT to change the reading. And so you can use it in many other ways other than just for elongation or displacement measurements. So most of them that are commercially available are limited in their temperature range, their displacement range, their physical size, maybe they may be big, or their radiation tolerance. The Halden Reactor Project has done a fantastic job at developing fairly small footprint LVDTs that are both high temperature and high radiation tolerance. They're unique in that they provide them to the international community. It's not just for themselves to use, or we're not unique in using them. Other international radiation testing organizations use them also because of their high reliability. The fairly recent closure of the Halden Reactor Project has threatened this supply chain. And since they're considered, a standard supplier of these, it's kind of threatened the applications that we've used them in test reactors or irradiation experiments and whatnot. Currently the supply chain is still intact. They're still They are still making them while limited, and we've still procured some for other for radiation experiments at INL, and others are still doing also. But it still remains a possible threat that they will not be available in the future. And these LVDTs are considered one of the most reliable measurement devices for in-pile applications. And specifically, I mentioned a few here for field performance, qualification and testing, but it's certainly not limited to this. But they were commonly used for, like I said, displacement, so fuel stack elongation or cladding elongation. So you can monitor those as a function of burn up. You can use them for, I mentioned the pressure measurement, so it's commonly used to measure plenum pressure for detecting fission gas release, or for rod failure is another application of them. So this project overview, Kurt has listed here a couple of the milestones that were from, so it'll be a complete assembly of a test rig to enable LVDT calibration inert gas. And I'll talk more about that. And assessment of the supply chain for nuclear LVDT and related components manufacturers. And then he lists the collaborators here at INL. So this assessment of the, assembly of the test rig to enable LVDT calibration inert gas. What it is it's basically that. It's a calibration test facility that you can run to high temperatures and not oxidize your specimens. A good example of why this could be very problematic is not just oxidizing the sensor, but for example, if you were to wanted to measure the plenum pressure in a fuel rodlet for an experiment, the common way to do that is put the bellows inside of the plenum of that rod and the ferritic core in the top of that, and then put the LVDT over it, so you have no penetrations into the rodlet itself. And then you could calibrate prior to installing the fuel. But if you need to calibrate your bellows system at temperature, and can't hold an inert environment, then you would be basically pre-oxidizing your cladding, right? So it's very not prototypic. It's been subject to something very different. So it was pretty important to get this capability in place. And Kurt's been able to stand up 3 configurations, if you will, for calibration capabilities. The first is the LVDT alone, so by displacing the core at known amounts with some precision equipment inside of the furnace, so we can do it at temperature in this inert environment, and have a known displacement, and read out the LVDT and do a calibration for displacement measurements. And then he has the pressure calibration system. So then there's a bellows coupled to the LVDT, as I mentioned, and there's actually a pressure system that is inside of the furnace, and then that pressure system is also surrounded by the larger tube. I think you can see my mouse here. So this glass or quartz tube here contains the inert gas, the flow over it. And then the pressure system, in this picture, it's not the pressure calibration. I think it's the, well, it might be hard. It's hard to tell down here in this picture, but the pressure system sits inside of that, and this gold tube here is actually the furnace. And then the third system for calibrating is for transient pressure. So there's a specially designed pressure system that can inject high pressure at a fast rate, and has some high speed pressure measurement transducers, not the LVDT and bellows, but a separate one that's outside of the heated region to monitor that transient pressure. And it's basically to quantify time response of the sensors. That's important for several applications where you're trying to detect like fuel pin failure when it happens due to a transient response. And then he gives some specifications here on the right of what the system is capable of. And then here's some of the testing that he had done. So he gives the argon flow through that outer tube here. So all these components on the inside stay cool. The other thing he wanted to point out with this thermal image is all these motors and whatnot. He's got well insulated here. That it remains pretty cool everywhere, but right in the heated furnace region, and that he is in fact keeping out the oxygen from the system to protect the components and the device itself. So here he's got on the left is the diagram of the transient pressure testing. So he's got an accumulator here, some of the controls for it, valving and whatnot, and then the high-speed pressure transducer here. Out of the picture is the high pressure bottle and everything, supplying the gas. This is all controlled by a LabVIEW VI to synchronize the opening of the valves and the data collection on the high-speed pressure transducer, and also collecting the LVDT response. And so when that is triggered, it dumps this pressure into this pressure system up into the furnace, which is just above this picture, and collects the data there. And here he is plotting out some of the response of the system. It's really pretty quick. And the scale here is in milliseconds, so it does quite well actually. And then here he's showing the displacement, basically fixturing. So it's hard to tell what's going on here, but there's a support structure around it, and then there's an inner piece here that he's able to displace. Control very precisely the displacement, and it moves these rods up into the sample where the LVDT is held fixed in the core, moves relative to it in and out. And then he shows some of his calibration data here for one of these sensors, and it behaves quite well, and he's seen quite good performance from it. He's actually, I'll just point something out that's interesting. When he was first setting this up, he had some problems with this area here where he was displacing it. He was measuring drift in the LVDTs, and he couldn't figure out why they were drifting. And he actually found out that it was a little bit of a wear on the surface that was pushing it. So he ended up changing the material that he was driving it with, so it had better wear characteristics. So it was it's very sensitive to small changes, and he's been able to measure them very accurately actually with this system. So then he wanted to highlight the technology impact. So as my talk earlier about it, these irradiation experiments. Here's a few examples of them. One that's not shown in the pictures, but was discussed, I believe, yesterday, maybe 2 days ago, was the creep rig that Malvina was discussing. So it's based on the LVDT technology. And then also we used these LVDTs in the March CERTA experiment series. Shown here on the bottom left is the diagram of the or solid model of it. We had 2 in this, or the capability of doing 2 per experiment. One would measure the cladding elongation. Basically, the rod was held at the top, and it would elongate downward and move the core inside of here. And then the other one, there was a bellows located in the plenum of the fuel rodlet, and the LVDT is, you can see the back of it here, is sitting in here. So we were able to monitor the plenum pressure during the transient treat. Here he's showing some of the fabrication of the LVDT leads, And he's wanted to point out that he's jointly developing some things with other customers. And then our most recent one that we'll be utilizing this is a Thor experiment. This is a metal fuel experiment. In this, the LVDT and bellows system is coupled here, which is located right at the top of this experiment, just above this fuel pin. And its purpose here is to detect the fuel pin failure. So there'll be pressure released, the fuel pin fails, and this bellows will act as a bellows LVDT combination will act as a timestamp, if you will, for when that failure occurred during the irradiation. And that we just finished calibrating that sensor actually, and will be installed probably this next week, and we'll be going to treat for irradiation shortly. So we're pretty excited to see how that works. And then this was his other milestone that he completed. It was the assessment of the supply chain for LVDTs. Basically the strategy here was to look at possible alternatives to Halden LVDTs. And basically not all in-pile applications require the extreme temperatures and radiation capabilities of the Halden LVDTs. They were pioneered to be long-term irradiations, with high dose, operate in high temperatures, and very reliably for that long. So we started thinking, if maybe the quantity is limited or mitigating risk if the supply chain does become intact. There's some applications where maybe we can put them in a lower dose area, or it's in a lower dose application, like a transient test, for example, or maybe it doesn't need to be as high of temperature. And so we, as part of that assessment, Kurt identified some suppliers that have products that have some potential for meeting the needs, or some of the needs at least, certainly not all of the needs. And then is working on a path for the more demanding applications that would currently require these Halden LVDTs. So that means either working with these existing, commercial vendors that, to improve their designs, maybe make them more rad hard, change materials, things like that. Or shrink them in size. That's a common one. He identified a couple of companies that have some high temperature and we believe radiation resistant LVDTs, but they're rather large. So maybe shrinking them could be another potential path. And then perhaps there's a combination of in-house fabrication with an eye towards commercialization. Not saying that we would manufacture them for all future, but basically to help develop a design that could withstand these higher temperatures and doses, and then work with a vendor to produce those. So he's looking into those types of options. And then so he plans to procure and benchmark these potential replacements against the Halden LVDTs. So, what that looks like is, in his calibration rig for displacement, he can attach these different various LVDTs and assess their performance in there at temperatures and pressures and whatnot, and see how they perform, and then eventually take that to in-pile testing. So in the conclusions here, basically he's got to establish this calibration test rig for pressures, elongation, and the transient pressure, and it's all done in an inert environment up to 700 degrees C. So he can perform all of these calibrations without damaging the sensor or the I'll call the housing for the sensor. In many cases, that could be fuel cladding or something like that, where you definitely don't, for prototypicness, you definitely don't want to oxidize the surface under any different conditions. And here you got the transient evaluation is ready for testing, ready for calibration. I think that's a little bit of an outdated bullet because it's already been done. So, and as I mentioned, the future work includes purchasing these and purchasing new LVDTs and benchmarking them against Halden's, and also looking into some of the implementation strategies of LVDTs. I think that's the right way to say it, of quantifying their performance related to how you mount them and things like the thermal expansion of the components that are holding them in place and whatnot, kind of nailing down some uncertainties in designs and get some guidelines there. And likewise with these ones that we're purchasing, there'll be a similar effort. And then also he's interfacing with University of Pittsburgh on the implementation of a wireless LVDT and its possible applications, which is, you should stick around for that presentation. I think it should be up next. But I think at this point I would take any questions, and hopefully I can answer them. So it looks like one of them here is, what is the failure mechanism of the sensor when it is inadvertently oxidized? So the sensor itself isn't generally what is being damaged. There's a housing around the sensor that is hermetically sealed, and I believe it's a stainless housing. It's either stainless or Inconel, and so it can oxidize, but that doesn't actually affect the sensor performance. The concern was more about the housing that we would be putting it into, such as the zircaloy cladding, and perhaps causing premature failure in the test of that cladding material, so affecting the data objectives of the experiment. But I don't think he has seen any problems where the sensor performance has been degraded from the oxidation, because it is kept hermetically sealed, the sensor itself. Thank you for the question, by the way. Is there any other questions? If not, I think the wireless LVDT presentation will be up next. It's scheduled not until the hour, so we've got about 7 minutes before that.
I think the best would be to take a 5 minutes break, Austin. We can test the system with Hang in the meantime, but let's just wait until 5 minutes to start the next presentation, just in case people come in on the clock to listen to. And
yeah, perfect.
If you don't have, well, okay, we could have a break slide like we had in this last few days. I don't know. I don't have it ready. Disadvantage of that, Austin, is that you will use your computer for just to show the break slide, and here you can only show screen, so you would have that busy during the.
I'll make a break slide so fast you won't even know it.
All right, so let's just wait 5 minutes, Hang, and then we'll go with your presentation a minute before 11. I see your slides are on, and so it shouldn't be a problem.
Okay, can you see my slide?
You can test them now. I saw them before, and now they disappear, so we're going to wait a minute.
Oh, let me see. Show screen. Is it showing?
Yes.
See your screen, and you may want to, please go on a presentation mode. Yes, perfect. Yeah, that works.
Right away?
That's good.
You can leave them on, and we can just wait 5 minutes
Okay.
with the first slide on. Thank you.
What did I do?
That's perfect. Thank you.
we're okay to start, Hang. I think Austin is probably just sitting in the background. We're close enough to 11 at this point. I'll give you one more minute in case it's needed, or we can always, the next is break, so we can
Let me close the door.
all right. We could go on a break anytime earlier, Austin, if it's, they're all rather short breaks.
Yeah, they are. Yeah, so with that, we'll invite our next speaker, Dr. Heng Bang from the University of Pittsburgh, to discuss the wireless LVDT for reactor applications. And you can go ahead and get started when you're ready.
Okay. Well, thank you for the introduction. Thank you for the organizers to have me here to present our work. My name is Heng Bang. I'm a professor in mechanical engineering and material science, and also I'm the director of the nuclear program here. Let me ask Austin, can you hear me well? Am I too low in terms of
Oh, your audio is perfect, and in the slides we can see well.
Okay, and just volume wise, is it low or high?
It's perfect for me, no problem.
Okay, thank you. Yeah, I cannot tell. Okay, so this focus is wireless. Of course, Kurt and Austin has done a lot of work in LVDT. So I will go a little bit here in terms of LVDT, which was introduced already. I show some pictures of commercial ones. And the principle here is basically, it's a transformer, right? So it's a transducer and a transformer. Transformer meaning that you have a primary coil and passing your signal to the secondary coil. And these two, they subtract each other by the wiring. And then you get the signal directly proportional to the position of the magnetic core. And then you can put a rod here that is non-magnetic. You can sense things, the positions of this, or displacement to be more exact. And you can convert like pressure and some other things into this one, into the motion in this direction. So it's a standard system that you can buy off the shelf anywhere. But as Austin said, the Halden reactor project is the only place that you can go to get one for nuclear applications. So there are two meanings here. One is that for nuclear applications, because of its temperature and the radiation and all the other issues in there, not anything on this picture, the commercial ones you can buy that will survive, will give you good measurement. And second thing, actually, probably people take it for granted is that, hey, this is a sensor that can survive and has been used in nuclear reactors, especially for test reactors. So it's very high sensitivity. These are the generic advantages of the LVDT. And it's directly conversion to electrical signal, so it's relatively easy, and you can put in whatever voltage you want. And dynamic response is very, very quick and very sensitive. You can measure your measurement accuracy, or the sensitivity is directly to your voltage measurement sensitivity. So you can measure a micron or something even smaller, actually, depending on your range. The range you can measure, in sub-millimeter range, or you can measure, tens of a foot range even, some of the industrial ones. But our focus actually is not on LVDT, even though it's part of this. What I'm showing here is actually, in reactor experiments. And this one, I hope you can see my cursor, is a design for an earlier project to have a fuel rod in the static water pool, and then you try to do the RIA, reactivity insertion experiment. In a fraction of a second, your reactivity 10,000 times higher, and then you burst basically the fuel and the cladding, and you try to measure what's the reaction. You try to measure, of course, what's the initial temperature, let's say 300 degrees C or so LW, are kind of a standard PWR condition. But look at this one, is that this is not that big, and we're only talking about 3 inches or so of head space. And you have to pass all kinds of wires going through, thermocouples, pressure measurement, or you want to pass maybe optical fibers. So a lot of things you want to measure has to go through this head space, and you have to have enough wrench space for you to install these, because these has to be electrical wires, they have to be insulated. So yeah, you're competing for the head space, and the wires are a challenge, and you have lots of wires coming out. And coming to this corner, it's a hexagon structure of a standard fast reactor, sodium fast reactor, kind of a fuel assembly. And it's under sodium, right? If you want to unplug to do the fuel management, moving fuels around, and then if you have electrical wires, you have to unplug and plug. It's a lot of headache. So ideally, you have a wireless connection like this one, and you just put this one on top of these, and then they can communicate through the wireless, almost like well, it's exactly a transformer kind. So if you have a sensor inside, and I can supply voltage, I can read out voltage, and then that'll be ideal case. Well, the first question is, okay, can you how thick of a stainless steel can you penetrate through? Well, this is typically measured by what's called a skin depth. Basically, your signal strength is going down by 60-some%. And for stainless steel, if you go through a wall of 13 millimeters, so half an inch or so, you're still okay. You're still 30-some% signal left, and that's more than enough. So you can penetrate stainless steel vessel walls easily at this kind of a low frequency range. Of course, it's when you have a higher frequency, your penetration depth is much smaller. So it's inversely proportional to the frequency, square root of frequency to be rather. So, okay, so our focus is to look at LVDTs, which is the center part, and we supply the power of the primary coil through our wireless coupling, and we read out the signal through another wireless coupling. So you put in the power, and then you read out the signal. And this is separated by the coupling are separated by the stainless steel walls. So let's say a test vessel. So we made some, well, this is just a schematic of the experimental system, that we have these couplings, and then we read things out, and we put a commercial standard wireless, a standard LVDT here. And well, we also did many other different types of tests, and what this one is actually, you put rings of stainless steel. You put 3 of them in there just to see how much signal is dropping in this case. So this is a separate test on the mutual inductance in between the two coils, and then you put it in there, and then you just put the sleeves of stainless steel just to test how much difference is in there. The difference actually is that, of course, you can do modeling easily, and then you can. The difference actually is, okay, what if I put 1, and then what if I put 1 on the as a bigger diameter, right? Or you can put 2, or any 2 in different combinations. So position-wise, it has an influence, and thickness-wise, it has an influence. So you have 3 layers, and you may have different combinations of all 3. So that there are different ways of doing this. Which no blocking, the mutual coupling efficiency is pretty high, 80-some%. And then these are the wires are separated by some distance. And then you drop it down to, if you have all 3 of them, that's the lowest, and that's 20-some%. That's still pretty good, already very sufficient for our application. So this is just typical stainless. This is a 316 stainless steel. We put sleeves in there to see what's the difference. Okay, so looking at the wireless, looking at LVDT itself. So we first try to do the LVDT measurement and modeling and things like that. So just the LVDT itself experiment, and we have a fitting line. So it's just like what you saw from what Kurt did at high temperature in that furnace. So if you put the sleeves in there, the signal will drop. In this case, this is a 304 stainless steel, so we put different materials in there. But the signal originally would be like this. Now you have a lower slope, but still very linear, still very good in 0.2 volts to 0.4 or so within this range. I mean, this is just depending on what kind of input voltage you have. So we changed frequencies in terms of the different. This one is 5 kilohertz, and we changed frequencies. We changed the voltage range. We changed all kinds of combinations just to play with it, to have a better sense of it. And then part of the work we also did is that, okay, let's develop a model to give us a much better description of the LVDT itself. So, okay, so this is an LVDT. You have the primary coil. The blue one is the magnetic core. And then you have the secondary coils. And you look at the magnetic flux lines, and then you model it using some kind of a theoretical model. And then it's the M1, M2 is the mutual inductance in between the primary of the first one, the primary of the second coil. And then basically you're measuring the difference between the two. So you have a model, you have a result with the dotted line, and experimental line is a solid black line. And this is the different discrepancy between the two. This is a different scale, right? So this is millivolts. So we are talking about a few millivolts here, and the signal is in 200 millivolts range. So that's whatever percent is defined here. Okay, what's the difference of the theoretical description versus the actual measurement? I mean, it's just like all the LVDTs. The most accurate measurement is near the center, when the core is near the center. I mean, the measurement is to decide the core position. When the core is right in the middle, you're supposed to have zero output, because the pickup from the secondary, they are exactly equal and they cancel each other. And when you move toward one direction, then you have more output here and less output here, and you subtract each other, you immediately have the location of this. And the closer to the middle, the more accurate you are in terms of the discrepancy. So you can that's the look at the modeling of the LVDT by itself. Now with the two wireless couplings transformers, one is for the power side, one is for the signal to go out, and then we can derive Kirchhoff's law, and then we can derive an expression for this overall transfer function. So you have an equation to describe everything. So this is the mutual inductance of the power side, and this is the mutual inductance of the signal side, and M2 is the inductance, mutual inductance in between the primary of the LVDT versus the secondary 1, secondary 2 of the LVDT. So you have an expression of all these, geometries and frequency, and all the inductance levels of each coil. And you can optimize the system doing, okay, I need to match the inductance, I need to match the output. We look at a few things in this case. One is actually comparison with when you have the output here, do you directly, like the previous one, do you directly going through the difference of the output of the two secondary coils, and then read the difference, like a normal measurement? You read the difference, standard LVDT practice. But in our case, actually, it's nothing standard, right? We have the reactor conditions. This one is actually going through a pressure vessel or at high temperatures, or at least temperature of the reactor operating temperature. So that's the depending on whether you are in sodium, whether you are in lead, or whether you are in PWR condition, the water, pressurized water condition, or whatever condition you are in. So these can be at different temperature conditions, can be inside the very close to the test vessel. So it's very high neutron flux in there and all kinds of fluxes in there. And this line can be very long. So you have a resistance, power supply side, and the signal reading side. And that's something we have to consider, we have to optimize. So one of the ways actually is to, instead of reading the difference, we read the primary coils separately. So we combine with this common side, but then you read separate two readings, and then you do the subtraction that way. And actually, the result is that if you look at the transfer function overall, is that this is a much better way. And this way, you can cancel, they can cancel the differences in terms of the changes of the power transfer versus the signal transfer, whatever issues you have over there, it doesn't really influence the final result. So you can change these two with temperature, with whatever condition, but my final result is not going to be impacted. Versus the previous one, it's going to be impacted if I change one or the other. So that's one of the conclusions that we're talking about. And of course, in terms of supply of, what kind of a configuration we input as a constant current source or versus a constant voltage source, that's pretty common, is that you typically input a constant current source to overcome the line resistance and the effect of line resistance change. And second part is that, okay, output, you read current or you read voltage. Now, obviously, from experiment and from theoretical analysis, of course, it's the voltage reading is much better. So I basically said that, if a 5-wire type of LVDT, it's a much better for the nuclear application. And once you do that, you have to design and, based on whatever LVDT is, or you can optimize the LVDT design for the wireless. And that's kind of a theoretical model based on the circuitry and things like that. And we actually couple it with two things. One is the finite element COMSOL modeling of the whole system. And another one is actually the theoretical solution of the electromagnetic waves to give us a chance to look at which parameter is more important, and what are the things we can tweak to have a better reading out of this. So comparison, the system transfer function overall experiment and the theoretical is in blue, and the red line is the discrepancy of the two. And kind of as you expect, the discrepancy is a function of how far you're away from the measurement, right? So if we limit, the closer to the middle, the better off you are. So the measurement is, the smaller the range, the more accuracy you will have. So that's the LVDT model plus the system model. And this is a summarized thing. And the two outputs type of 5-wire LVDT is actually, you can eliminate the influence of the wireless transfer system. So we have the power in and the signal out part. So of course, current input, voltage output, in terms of uncertainty introduced. And also we look at the sensitivity analysis, looking at all the parameters. We vary the parameters to see how sensitive they are in terms of influencing your measurement result. And that includes the mutual inductance coefficient and whatever your inductance is, whatever your line resistance or resistance of your wires is, and also frequency and all the other things. And there's one thing, of course, temperature is the one thing. And another thing is that as a function of temperature change, your mutual inductance, which is a material which is dependent on the material of the core, and that will change too. So that is an important consideration. Is that okay? My biggest concern is the temperature actually, and also the material property change. So when we do this analysis, look at all the combinations. This one is we do just a change. Let's say we change, decrease, or increase by 5%, and look at the. This is your decrease or increase of your parameters, and this is your output. And if you look at the result, it looks like this. It is supposed to be the black one, which is I cannot see under the red, I think. And then you can see the change from the others. And these are the numbers in terms of how they will change. So the line resistance change doesn't really impact much because our setting, this is the voltage in current input power and constant current power versus the voltage output. And you have a high resistance reading of the voltage. Now we change the temperature, 20 degrees C to 120 degrees C. And the difference is relatively small because in this case, we did not consider the material property change, which I will talk about it later, because the material property of the magnetic property, permeability change. So that is something that we'll have an approach to it. That's one of the more important results out of this. So we know the mutual inductance will have a big influence on this one. And a temperature will have some influence as a result of the mutual inductance. And the resistance, line resistance is not a big deal in this case. As I said, we have the console modeling of the system, and this is the LVDT modeling of the, you have an LVDT system over there and looking at the comparison of results. Now here is probably more important here. And if you don't really understand some of these, actually, I guess that's okay. So I still have a few minutes to explain. And we look at the output voltage, right? I mean, we set an input voltage. We look at the different, change in terms of coil thickness, positioning change inside, and so secondary coil change. So all the geometrical changes as a result of temperature. And we're looking at, of course, radius change as a result of temperature. Looking at this is the magnetic permeability of the core. So the magnetic permeability will change, and as a function of the result of this, and then we have the change of this, and this is probably the most important result. The result is here is that okay, what's my coil or core diameter, and the coil thickness too. So look at these and look at the result of the going from increase. This is the magnetic permeability. So if I change the magnetic permeability as a function of temperature, and this will result, my reading can be very different, changing very dramatically when you have this kind of a range. However, if you are here, then yes, you can change your magnetic permeability, but that doesn't affect my result in terms of my reading. It's very small influence. So that gives us an opportunity to overcome the whatever temperature change, you will have magnetic permeability change. But then if you're within this region, we don't care about your magnetic permeability. Now, it's a function of how big your core is. So if you have a smaller core, you need a little bit bigger, let's say 3.5 above. But if you have a bigger core, which is it's a 3 millimeter core, and then we're talking about really, even if it's here, the change is minimum. So it doesn't really matter. So that's a very good way to deal with, as a tool for us to deal with the temperature or other influences on the property. Because both of these, LVDTs and the wireless transfer transformer, they are just a wire, and it's a transformer. So very resistant to any other changes, actually. The influence of the radiation on material property change, the only concern is the permeability. The other things, it's not really too much of a concern. So this is a very important result that we can use. If I summarize everything that, our experiments, our theoretical derivation, and our console modeling of the system, and we compare all these, we came up with the, what kind of a configuration is the best, and more importantly, we are able to now design our own LVDT and design our power transfer and signal transfer wireless transformers or systems to work with the LVDT for whatever measurement you want to measure. Now, we used a commercial LVDT in this case, but it can be matched to different designs, so even the Holden ones. And it's the dual outputs that is also we found that is the best for the measurement, because that eliminates the effect of wireless systems, the difference or the change of wireless systems to the measurement result. I guess that's my presentation, and if you have any questions, I'll be happy to answer.
Thank you for your presentation there. It's very, very interesting work. I was hoping you could comment on some of the future work and plans.
Okay, I think a question that near the Curie temperature, of course, we are limited by the magnetic property of it's just like LVDT, right? I mean, it's dependent on the core. The core has a magnetic core, and the core has a temperature limit. Above that temperature, then you don't have the magnetic property anymore. So yes, you are limited by the Curie temperature, and that's your upper limit. It dependent on different materials, and then we typically, I think we can go, Austin, what do you say, 700 something for the ones you guys tried, is that right? What's your highest temperature, Kurt's experiment?
Yeah, that's correct, 700 C.
Yeah, that's the limit. And if you are above that, then your magnetic properties will not work for the LVDT. Now, for the wireless transfer systems, we also use magnetic core to increase the efficiency. Depending on the design, you may or may not need it. And we use actually, we also look at the shielding of all the other issues in terms of, if you have a flowing liquid metal, and how does that impact your result? So we are looking at shielding and things like that, and it's outside the coupling. So that is a separate topic that I did not present. I think the further down the road is actually we are still doing one of the theoretical derivation side. We need to complete the solution from the Maxwell equation side, so we have a much better definition of things, knowing that what kind of things we can change to achieve what we want in the design of LVDT and in the design of either power transfer or signal transfer systems. Of course, we want to test it in the lab at temperature, working with Idaho National Lab system, working with Kurt to test our system over there for the preparation, I suppose, to be tested in the future in a reactor.
Thank you. I don't see any other questions that have come in. The timing's actually quite well. We're scheduled for a break now. So I'd like to thank our speaker again, Heng Ban, and we will reconvene in 1:45 Eastern time for Zilong Hua's presentation. So thank you again.
Okay, thank you.
Hey, Zilong.
Hey, Austin. Looking for the share screen formation here.
So we can see your desktop.
Oh, you can see my desktop already? Is that the slide?
I do not see slides, just the desktop background.
Looking for, I was told, or the
Maybe
drawing
it's-
wrong again. Oh,
Maybe sharing the other screen or something.
yeah. I'm dragging it to this screen, but I don't. Oh, I see. Okay. It has to be in this screen,
Yep, we can see it now.
but I don't know how it works when I click the slideshow mode. Does it work?
Let's click the display settings and switch the. Nope.
No?
Go to the display settings in the top middle,
Okay.
and then swap. Yep.
Okay.
Perfect. We're seeing your slides in full screen now, and we can see your camera and your audio is good also.
Okay.
And perfect because it
So-
is exactly on time. So
Let's start.
yeah, I would like to welcome everybody back from the short break. And our next speaker is Zilong Hua from Idaho National Laboratory. And he will be discussing in-core measurement systems for nuclear materials characterization. And Zilong, you can take it away when you're ready.
Cool. Yeah. Good morning or good afternoon, depending on where you are. My name is Zilong Hua from Idaho National Lab. And here I'm going to give a summary presentation for the work package called in-core measurement systems for nuclear materials characterization, code validation, and verification. So in this work package, we're developing the instruments to provide unique capabilities of measuring critical physical properties of nuclear fuels and materials in the reactor and in the real-time manner. And currently, there are two instruments under development. The first one is photothermal radiometry, or PTR, which measures the thermal conductivity. The second one is called laser-based resonant ultrasonic spectroscopy. So RUS, this instrument measures the elastic property, which can be used to monitor the microstructure evolution. And in the past fiscal year, we just added a new detection capability on a specific plate wave mode. It's called the zero group velocity plate wave, or ZGV. I'm going to give more details in the coming slides. And the major researchers, or the PI of this work package, are Rob Schley from Idaho National Lab as well, and myself. So I'm going to start the presentation from some technical background of these instruments. We start from PTR, and in photothermal radiometry measurement, we use an intensity modulated laser to introduce a temperature field, which is periodic in both time domain and the spatial domain. And we collect the local blackbody radiation to rebuild this temperature field, from which we can extract the thermal transport properties. And this instrument has several unique advantages. Because of the use of the thermal wave and the detection of a period temperature field, we can use a lock-in detection approach. It can improve the measurement signal to noise ratio, which is very important because it guarantees the tolerance of the instrument to the background noise, which is a common situation in the in-reactor environment. And we all know the blackbody radiation heat flux increase exponentially with temperature, making this measurement technique ideal for high temperature measurement. And the signal also change linearly with emissivity, which means the rougher sample surface give you better signal level. So this technique can deal well with the surface deterioration of the materials in the in-reactor environment. And we use fiber to transmit laser and collect the black body radiation heat flux. Because of that, the whole measurement is remote, non-contact, and it is easier, relatively more easily to modify the system to make it in situ measurement. And lastly, the measurement only needs one side access to the sample surface, which is also important for the in-reactor application. So I'm going to jump onto the second instrument, the RUS. So in this RUS instrument, we use a high power short duration pulse laser to introduce a train of acoustic wave into the sample. And we use a laser interferometry to detect from the backside the small displacement of the surface, from which we can back out the acoustic wave propagation information in both time domain and the frequency domain. And we can detect all different modes of the acoustic wave, including the surface acoustic wave and bulk waves in the time domain, and the resonant vibration modes in the frequency domain. And by using the elastic property to monitor the microstructure is actually not that new. People have been using it for decades, but until the introduction of this laser-based ultrasound technique, researchers start to get very repeatable results because we remove pretty much how we generate and detect the acoustic wave, the boundary condition, the coupling conditions. And in the past fiscal year, as I said, we introduced the detection of a specific plate wave called ZGV plate wave, and it is relatively harder to imagine. So I'm providing a small video to show the wave visually. If you can see this video, on the left-hand side is a typical propagating acoustic wave, and on the right-hand side is a ZGV plate wave. And as you can see here, the ZGV plate wave does not propagate like the typical wave. It provides several important features because of the energy is locally trapped, and we actually increase the measurement signal to noise ratio, again, increase the tolerance of the instrument to the background noise. And also, since the wave is not propagating, actually this wave detection is supposed to be less sensitive to the boundary condition or how we mount the sample. Also, I'm going to introduce why this is important for this RUS instrument development in the coming slides. So the technology impact, why do we care the real-time small property data, or these physical property data, I should say? It is because currently this real-time measurement capability still remain as a technical challenge for the experimentalists. In order to know the real-time behavior of the nuclear fuels and other materials in the in-reactor environment, people still rely on the modeling prediction from the computational scientists. And the results of these modelers need to be verified or validated through some PIE test, or post-irradiation examination. But for a while, researchers suspect the PIE results cannot correctly reflect the real situation in reactor. I can give an example for the thermal conductivity of the nuclear fuels. So one type of microstructure defects, point defect, it influences the thermal conductivity of the nuclear fuel, specifically for the oxide fuel, significantly. But point defects are atomic defects. They're very small, interstitials and vacancies, so they are highly mobile. So after you shut down the reactor, due to the remained heat generation, these point defects can still move around, recombine, and anneal before you can perform the PIE test. The thermal conductivity of the nuclear fuel through PIE test will be generally higher than what it was in the in-reactor environment. So both of these instruments are supposed to provide the unique understanding of how this microstructure evolves dynamically in the in-reactor environment, and we can also provide direct validation and verification for the advanced field performance codes. I'm giving an example here in the bottom right corner. So this is, I got it from a milestone reports. It is from computational scientists at INL. The researchers are studying how these green boundaries move in the high temperature and high irradiation environment. And once our instrument is working online, we can provide experiment data to compare with simulation results. And another important application is we can actually perform continuous non-interruptive measurements of the nuclear fields and other materials. When you want to study the damage from accumulation radiation dose. And I'm giving an example here at the bottom left bottom corner. This is actually a very recent result from a system working in Sandia National Lab. It is called in situ transintegrating spectroscopy system. And this is developed by our colleague, Cody Dennett, and his Ph.D. advisor, Michael Short from MIT. So this system can measure the elastic property and thermal property of materials under ion radiation. And this 5 sets of plots shows the results on a series of nickel-based solid solution alloys. And you can see the x-axis is probably not very clear, but it is the radiation dose. So as you can see here, the both properties change pretty much with different radiation dose. So since our measurement will be continuous, so similar to the figures showing here, you don't need to take the sample out, or like before you have to prepare like a set of samples, stay in the reactor with different time duration, and take out and do PIE test. And it's not only provided in situ real-time results, but also it can save you a lot of time on this, if you want to study how this property change with different radiation dose. So it's expected to boost the development of advanced nuclear fuels and materials in the future. So in this slide, I'm giving a little bit of the background of PTR measurement or the PTR instrument development in the past several years. So I have a better plot slides. This is more visual again. So we started in fiscal year 18 and 19 from building a benchtop system to verify or to validate this measurement technique. And we got reasonable results from a series of materials, but we also identified some systematic error which can cause the overestimation of the results. They are from the diffraction effect due to the use of lens and parabolic mirror optics, and the nonlinear effect, which is because we kind of oversimplified the model by considering the thermal flux is linearly changed to temperature, but which is exponentially. And then we developed a complete model to include both effects. And in fiscal year 20, we started the design and build up of this fiber-based system, as the picture shows in the middle. We started the first generation of this instrument. We started with fluoride fibers and a liquid nitrogen cooled detector, this detector with a red door here. And this system is optimized for room temperature measurement. It transmits and detects the mid-IR range black body radiation heat flux. We got reasonable results from it. And as you can see here, we have a picture of the fiber probe head of 2 fiber cores here. The second one is not very clear. And in the past fiscal year, we upgraded this instrument into the second generation. We use a silica fiber to replace the fluoride fiber, and we used thermoelectrical cool detector to replace this liquid nitrogen cool detector. So it made the system more portable, and also more importantly, the system is optimized this time for the near IR wavelength. So it is supposed to be give you better performance in the high temperature. And when we do the high temperature test, we found the oxidation issue of the samples. So we purchased this vacuum chamber. It also gave us the capability to test this instrument in the in situ environment. So, so I'm going to the recent results slide. So in the fiscal year 21, we tested this instrument at high temperature on a series of samples, which covering the thermal conductivity range from as low as 1 watt per meter per Kelvin to all the way up to above 100 watts per meter per Kelvin. So in this temperature range, actually, this thermal conductivity range actually covers the common nuclear fuels and most of its materials we're interested in. And the measurement it was done in the temperature range from around 250 degrees C all the way up to 515 degrees C. As you can see here, the results on the two lower thermal conductivity samples, the experimental data, or these red spots, they match closer to the literature value, which is the dark line, within about 5% difference. And on the two higher thermal conductivity samples, this difference is still better than 20%. So this is actually pretty impressive for the in situ real-time thermal conductivity environment. And I didn't show the signal level here, but you also can tell when the measurement is above around 330, 340 degrees C due to the increased black body radiation intensity. This experimental data also approaching the literature value line closer in most cases. So it is as what we expected. And in another result or another achievement we have been done is to study how this spatial resolution influence our PTR instrument measurements. This is also very important because the spatial resolution, if we do the measurements with a high spatial resolution or too local, you may be trapped into some very local feature, like if you have a microstructure, macro crack on the sample surface, the measurement result will not be too representative to the, what we are looking at. But if the spatial resolution is too low, you are pretty much measuring the bulk property and you miss the microstructure information. So before we designed this instrument, we decided to make the spatial resolution in the order of about 100 micrometer, but we still don't know which spatial resolution is a sweet spot. So we designed a second probe with 2 times higher or 3 times as much as the spatial resolution of the first probe, about 500 micrometer, and we ran the tests on a series of stainless steel samples with different porosities. And you can see the results here. If we look at the bulk results, which is from a reference laser flash measurement, the thermal diffusivity change from the most dense sample in this 3 to the most power sample in this 3 is about 15% to 20% different. And this difference increased with spatial resolution. And for this probe, second probe, clearly the second value should be in between the two, but we are probably trapped in some local pores. But the difference you can see is a lot higher, it's about 50%. But in the first sensor, which has the highest spatial resolution, this difference is more than 10 times different. So it shows how important the spatial resolution is to this measurement. And due to the time limitation, we have some other plans we want to do, but we didn't. In this fiscal year, we were thinking to run more measurements and get a standard deviation of our measurements, at different locations. And also we're thinking to map the whole sample to also show the power of high spatial resolution. If we have a dual phase or multiple phase system, this raster scan or mapping function can be similar to, you run a quick SEM measurements or, through the thermal feature. So you can tell the different phases from this thermal diffusivity measurement. And the third, but is probably more important achievement in the last fiscal year, we submitted a CNR NSUF proposal, and it was recently awarded. So this instrument will be sent to MIT Research Reactor for insertion experiment starting from fiscal year 22. It's a 2-year project, and we collaborated with MIT professor Michael Short and the researcher from MIT are David Carpenter. And actually, this project has started from this October. Currently, we're working on modify this instrument to make it a complete package. As you can see here, in the MIT reactor, depending on which position you're sending this to, you have to modify the geometry of this instrument. And we were told the temperature control is by adjusting the inner gas ratio. So we need to make sure the instrument, this package has like entrance and exit for different inner gas. And we also need to design a sample holder to protect the sample from contacting the water and steam and from moving during the measurements. So we're working on the designing at this point. And from the quarter 2 or quarter 3 in the next calendar year, we're going to send this instrument into MITR for insertion experiments. So we planned 2 rounds of insertion experiments. We're going to collect real-time thermal diffusivity data. We analyze at INL. And after both rounds, we're going to do PAE test on the fiber and instrument to test the survivability of this instrument. Between these 2 rounds of irradiation experiment, we'll have a round of the instrument optimization round. And we also have a finalization round after the second round of insertion experiment. By then, we're expecting to provide a user protocol for the nuclear materials communities. So researchers, if they want, they can perform regular thermal conductivity or diffusivity measurements of any materials they're interested in the in-reacting environment, as what I just showed earlier. You know, the in situ transient grating spectroscopy system is doing at Sandia National Lab right now. So here is a similar background slide for the RUS system. We started the development of this instrument since fiscal year 18. The very first detection mode is resonant vibration, and we have the sample designed to be a cantilever beam, and the instrument's result, the testing result is pretty promising. Was pretty promising. So we further developed this instrument to be a capsule for the insertion experiment in treat reactor. And as you can see here, the results on a copper sample in the treat reactor shows a very repeatable curve of the resonant frequency to the in situ measurement we done in the in-lab environment. It's good to see the reproducibility, but also that shows the irradiation dose is not high enough to cause sufficient microstructure defects, which can change the elastic property. And in fiscal year 18 and 19 study, we figured the elastic property or the Young's modulus we back out from the resonant vibrational mode is always like a few percent to 10% different from the analytical model prediction. And eventually we identified the problem to be a poorly defined boundary condition of the cantilever beam, which is hardly to be achieved because the elastic wave or the acoustic energy always goes into the mounts. And in fiscal year 20, we tried a free beam instead of the cantilever beam. And we were hoping the free beam boundary condition is easier to be defined, but we figured the sample actually slide in the capsule, and it's hard to, provide a free beam boundary condition without preventing the sample from sliding. And as you can see here, the similar issue is causing a low signal to noise ratio. On the left-hand side is cantilever beam, the resonant frequency measurement. On the right-hand side is a free beam. It shows a lot lower signal to noise ratio, makes it hard to identify where the vibrational mode frequency is. So in the past fiscal year 21, we decided to go to the ZGV plate wave. As I introduced earlier, ZGV plate wave is supposed to be less sensitive to the boundary condition or the mounting approach of the sample. And ZGV plate wave is quite different from all the acoustic wave modes we have been studied. So we have to derive the analytical model and code it into MATLAB. And we found the Young's modulus or other elastic properties that are not explicitly related to the ZGV wave frequency. But a series of ZGV plate wave, a series of land mode plate waves coexist simultaneously in the sample, and only several of them or a few of them are ZGV plate wave. And we compared the experimental results of the first ZGV plate wave with the model prediction, and as it actually shows very good matching on all four materials at room temperature and at high temperature all the way to 1000 degrees C. Here I'm showing the ZGV plate wave measurements on copper sample from room temperature all the way up to 700 degrees C. And as you can see here, the plate wave frequency is shifting to the lower end with increasing temperature, and the also the ZGV plate wave amplitude reduce with temperature. At first, we were thinking the reason is from surface deterioration of the sample at high temperature, but later on, since this reduction is different in all samples, later on, after we read more literatures, we figured this is probably due to the increase of internal friction. And the internal friction has been used to characterize the microstructure features like point defects and dislocations. We can give, from some model, we can actually quantify the concentration of these defects. But again, due to the time limitation, we didn't go into this physics part in fiscal year 21. So this slide summarized the challenges, but we also consider them as future opportunities of the, during the development of both instruments. For the PTR instrument, we are pretty curious how this fiber and instrument, how they survive the high temperature, high radiation environments. And we hope we can get the results from this NSUF project. And also the second bullet here, we are expecting a signal reduction in the in-reacting environment due to the deterioration of the fiber condition. So we're thinking we can increase the fiber core diameter, which is the most straightforward solution to get more signal, increase the detection area. But we actually did some preliminary tests, and we figured that's actually that's not going to work as we expect. That's straightforward, because when you increase the fiber core diameter, you actually increase the probe beam size, and because the temperature in this probe beam detection area or the probe detection area, there is a temperature gradient, and you are not actually collecting the single temperature from a point, but it will be like a weighted temperature information. It causes some systematic errors. So we need to figure out, we need to find the balance point between guaranteeing the signal to noise level or high signal and with minimal nonlinearity issue. And for the ROS measurement, as I just said earlier, you can see the Q index is still not ideal at high temperature, but we consider it as some physics we don't fully understand at this point. If we have more time, we can dig into it, so make ROS a powerful tool to characterize some very small scale defects like point defects and the loops and the dislocations. And also, as I said earlier, the Young's modulus is not explicitly related to this ZGV plate wave frequency. So we're going to also simplify the data processing procedure. So as a summary slide.
Can you wrap up quickly, Zilong?
Sorry, what's that?
Can you wrap up pretty quickly? We're just about out of time.
Yeah, that's the last slide. So in the past fiscal year, we did high temperature in situ measurements on both PTR and the rust instruments. And the new measurement mode, ZGV plate wave mode detection, has been added into rust. And also we won the proposal for insertion testing at MITR. In the future, we want to further develop this instrument so make them possible to characterize or quantify the microstructure defects, which are either impossible or more expensive to be done by using other techniques. So I'm leaving my contact information here. So if you have any further questions, you can also call me or email me. Thank you.
Thank you, Zilong. See if we have any questions in here. It doesn't look like we have any questions, but we're just ready for the next speaker about right now. So I'd like to thank Zilong again, and like to invite Joe Palmer, who will be our next speaker. He'll be discussing radiation testing of flux sensors. Joe Palmer is from Idaho National Laboratory. And we can see your video. Oh, we can see your screen now. Perfect.
How's that, Austin?
Looks great, and we can hear you well also.
Okay, great. As Austin said, my name is Joe Palmer, and I'm a reactor experiment designer for Idaho National Laboratory. And so I'm a little bit different background than some of the other presenters we've seen. My career has been designing experiments and then integrating sensors into those experiments. And so I've been able to leverage that and work with the measurement sciences group to help them test their sensors. Let me get a pointer. On the previous slide, it said that the title was radiation testing of neutron sensors. Actually, our project was quite a bit broader than that. It used to be called performance testing in operational conditions. And so really the overall goal of what we're doing is to create a means for PIs to test their instruments prior to them being incorporated into a high value experiment. We're focusing a lot on sensors that would support advanced reactors. And ultimately, even some of these sensors may be incorporated into the advanced reactors themselves. Participants on this project, I've been the project lead, kind of the project manager, and I designed the hardware to support people like Kevin Tsai, who's the PI for self-powered neutron detectors. Dr. Michael Reichenberger is our PI for miniature fission chambers. Calvin Downey helped us with test rig design for an ATRC experiment. We have Corey Manning, technician extraordinaire, is helping us with retractable sensor development. I'll explain a little bit more later. We've got several slides that talk about what a retractable sensor is. We're working with Dr. David Carpenter at MIT for an irradiation that we're going to conduct early in calendar year 2022. Also working with Dr. Gi Yang, who was one of our kind of kickoff speakers on Monday. He's the project lead at NC State for retractable sensor development. So I'm going to show these timelines of things that we've been doing over FY21 and FY22. This first bubble here is talking about some optical fibers. These were temperature fibers that we put in the HDG1 experiment. That experiment was to do high temperature testing of graphite. And this is a perfect example of the kind of work I've been trying to do, which is to incorporate sensors into customers' experiments. These are developmental sensors that are not really interfering with the customer's main objective, We, a lot of times, will incorporate the sensors a little bit above, right above the core. And we're able to do this so much more cheaply than if we had to have a devoted sensor experiment. This particular irradiation is a spillover from FY20, so I don't have any slides that show results of this. I already reported on that in last year's webinar, but it continued into this year, and I just kind of wanted to take credit for it because it was the only experiment that this project ran in ATR this year. ATR is currently down for CIC. In November, we did some initial irradiation of SPNDs in NRAD. This was a kind of a work out the bugs little experiment. It was good that we did that. It was in support of this ATRC irradiation that took place in February, and we were able to get those sensors working perfectly. And so when we went into the ATRC irradiation, our SPNDs and fission chambers worked very well. What we were doing in February was not only testing sensors, but we were verifying a % flux increase due to some booster fuel that was installed in ATRC. And I'll talk about that a little bit more in detail. In March, we had a collaborative effort with Dr. Immel at Idaho State University, irradiating SPNDs in their little 5-watt reactor there. In August, we conducted a high temperature irradiation in our NRAD reactor. NRAD is our radiography reactor. Not a lot of experiments are conducted in this reactor, but we found it a very low cost and convenient facility for things that don't require a high neutron flux. And I'll talk more about that in detail. And all along during the year, we were irradiating sensors in treat. Now, Kevin Tsai is going to talk about this in detail, but it was partly funded under my project, and so that's why I mention it here. It's called concurrent testing. What that means is, again, it's kind of like the HDG1 experiment. We're kind of piggybacking on other people that are paying full freight for their experiment. We're kind of just tagging along. So I made this little star to advertise that during FY21, this project irradiated sensors in all 4 INL reactors. That's ATR, ATRC, treat, and NRAD, plus the IXU reactor. And so that's every reactor that's within 50 miles of our facility. We had sensors in them. In FY22, we've already conducted one test. We performed a high temperature test in NRAD. And in February, we're planning on going to MITR as part of NSUF collaboration. My cat is trying to join the webinar, so I'm going to put him out. Sorry about that interruption. In July, we're going to run another NRAD irradiation experiment in cooperation with our CEA colleagues. They are providing both SPNDs and fission chambers. During FY22, for many months, we're going to be developing a retractable sensor mechanism. I'm going to explain later what that's about, but the main purpose of this, I'll just explain now, is to be able to enable us to insert sensors into in-core reactor experiment and then pull them back out. So we just briefly insert and then pull them back out. That enables them to greatly extend their lifetimes. As far as milestones, we have a milestone in March or we had a milestone in March of FY21 to test our sensors in ATRC, which we met in February. We also performed our high temperature irradiation, as I mentioned. We completed it in August, so ahead of time. This year we have a very similar milestone to do another test in NRAD by the end of the fiscal year. And then this retractable sensor system, we have a goal to get that done by the end of October of calendar year 2022. We've already developed a very rudimentary form of this, and what we will develop this year will still not be ready to go into a reactor that takes really a lot of resources to put a more sophisticated system into a test, but it'll put us well on the way of doing that. So what's the impact? Why are we doing this? Advanced instrumentation enables testing of nuclear fuels and materials in support of our advanced nuclear industry. There's a lot of concepts out there. Most all of them involve high temperature. And so that's one of the things we're kind of focusing on, where our sensors need to operate at temperatures well above what's been developed commercially for LWRs. The early part of the sensor development can take place in the lab, but to be fully ready to incorporate them into a test, we need to have let those sensors experience in-core conditions and prototypical temperatures as well. As we succeed in doing this, we'll have additional capabilities for our main test reactors, ATR, HIFER, TREAT, MITR. One thing we notice is that customers usually only have one shot to conduct a radiation experiment. A radiation experiment is a little bit like, you know, sending out a space probe. Any instrument that would be on a space probe would need to be very well tested and characterized. And we would expect to spend a lot of money doing it. And it's going off into an environment that is not the same as it is here on Earth. That's the same thing when we put sensors down into a reactor core. And also, once the test is inserted in the reactor and irradiation's begun, we can't typically change it. Everything now is irradiated. We can't fix it or anything. It's what you've launched is what you're going to live with. And so it's very important to demonstrate these newly developed sensors in operational conditions prior to incorporating them into a long-term experiment. Some of these reactor experiments go on for 2 and 3 years, and they might cost millions of dollars. So we better be sure about the instruments that we're putting in them. A lot of the sensor work that we're doing in FY21 and 22 is focused on high temperature. Our SP&Ds and miniature fission chambers, they've been deployed in commercial reactors. They operate up to 300C, 350C with no problem. They're well characterized. But for temperatures envisioned for advanced concepts, 500 to 1000C, we just don't have that much experience. Early indications that there might be some temperature effects at temperatures above 500C. We at least think there'll be minor effects, and a major effort will be to better understand these effects and to mitigate them. So as far as accomplishments, this slide shows one of the main tests that we had during FY21, and this was in support of the medium I loop. You can see this is a ATR fuel assembly right here, and it has been placed in the I11 position of the ATRC reactor. Then this is a beryllium plug here. Here's our sensor test rig right here, and it contains SP&Ds and miniature fission chambers. So first we ran it without the booster fuel, and we got 1 level of neutron flux, and then we ran it with the booster fuel. We can see that our measured increase was 23%. Over here I say that the calculated increase was 21%, but actually their initial calculations were all over the map. And so it shows why it's always important and vital that we measure things rather than just calculate them. But after they had a chance to revise their MCMP model, both the measured and the calculated agreed pretty well. This is just a plot of the data we gathered. This is both, we have fission chamber signals on the left. And so like that's this blue plot here. And we can see every little bobble in the fission chamber, they're matched by the SP&Ds. We can also see our signal to noise ratio is quite good. Our SP&Ds have less noise than the fission chambers. We used, as I mentioned previously, the NRAD reactor to perform high temperature testing. We also conducted a room temperature test. In fact, this little photo here is from the loading of the room temperature test. We're able to conduct these experiments quite economically. You can see this is a very temporary setup. The NRAD reactor's behind this yellow door, shield door here. Here's Kevin gathering data and me just watching him. And we're just there with a temporary hookup. It didn't cost very much to run this experiment, but we got a lot of good data out of it. You can see this is our temperature ramp. We went up to 350, 500, 650, 800, and then we ramped down. We saw some anomalies in the ramps from 500 to 650 and from 650 to, let's see, make sure this was 350 to 500 and then 500 to 650. We see these small little dips. And then we saw a reverse dip when we went from 650 to 800. Currently, we're thinking these actually have to do with our electrical heater and the way we have it assembled. And so we have some more work to do to determine and sort this out. And that's why we're going to do the test in MITR, which will be in about February. There'll be no electric heater in the MITR reactor, so we'll take that complication away. We also irradiated SP&D sensors in Idaho State University in a little 5-watt reactor. This is an excellent collaboration that we did with Dr. Emmel. We're comparing rhodium-based SP&D to hafnium. Hafnium has a much quicker response time. You can see when we shut the reactor down, there's a little bit of a time constant on the rhodium, while the hafnium is just very abrupt and gives a good, a very rapid response to the reactor power. Part of the reason something like this, I mention it, is we're able to do this kind of testing. This is like the very beginning of proving that our sensors work. In a reactor like this, the costs are very low. And so we can leverage these other facilities to accomplish this work. We use the treat reactor, which is a gas-cooled reactor, to test quite a variety of sensors. And we do it kind of similar to the HDG1 experiment in that we're kind of piggybacking on customers that are paying full freight. We put these sensors in the cooling channels. Can't see too well, but they're little cooling channels, and they're not actually in experiment positions. This enables us to get good data for transient testing of these sensors at a low cost. This slide shows kind of a map of all the sensors that this is Kevin Tsai is doing this work. He's put them in all these cooling channels. The presentation after mine is going to be by Kevin, and so I'm not going to go really any further than just saying it was part of my work package, and this is the philosophy we have. How can we get sensors tested at low cost and quickly? I'm going to shift gears a bit and talk a little bit about an idea that we've had first germinating about 18 months ago. And it comes from the observation that our sensors that we use in core for a lot of the experiments that I work with, they are affected by the very harsh environment. This is an AGR experiment. It's about 7.5 meters long. The in-core section's right here. So this is where high flux and high temperature is. And we're running, thermocouples are our main instrumentation here, and we've run them all the way up to 1500 C. Well, at 1500 C, they don't last very long. Even at 12 and 1300 C, they drift fairly readily, and they tend to not last very long. And so we thought, is there a way that we could just, the temperature that we're trying to measure, it doesn't vary, it's basically steady day to day. Is there a way we could insert the sensor for a minute or two and then pull it back out so that it stays out of that harsh environment? So our concept is put a capillary tube that's fixed in the experiment, running all the way from the top here down into the hot zone. And then we would put a mechanism in this region right here that could drive the thermocouple into that hot zone through the little capillary tube and then just pull it back into this maybe 0.5 meter, where the temperature is actually not far from coolant temperature with 60 C, and the neutrons are going to be down 2 or 3 orders of magnitude as well. And so that was the basic concept. We don't need to pull it all the way back to here. The mechanism that would do it would be kind of in this region where there's a larger diameter where we can house a mechanism. And so we thought, how could we make a little progress? How could we develop this? And we decided that we would try and use undergraduate capstone design teams. You may be aware that most undergraduate degrees in engineering require a capstone project where a team works on something. It's nice if it's practical. And so we set 2 different capstone design teams, one at NC State University. These were actually nuclear engineers. Another one at BYU, Idaho, and those were mechanical engineers. And they both made kind of similar mechanisms, mainly because I coached them along the line. And what it is this is a drive mechanism that's adapted from a MIG welder. A MIG welder pushes a wire into the melt pool, and it uses a DC motor that can be reversed. And so what happens is a little carriage here, and the cable for the thermocouple is right here, and goes into a capillary tube right here. You don't see this. This heads off then 6 meters. And so what happens is this thing cycles back and forth. This is a limit switch right here, another limit switch right there. It cycles between these 2 limit switches, it's about 0.4 meters. And what we're seeing then is this, it was put into a furnace the furnace was running about 120 C. The furnace is designed for more like about 700 C, and so that's why the temperatures are not very even here. But they cycled it in about every 2 minutes. As I said, we were planning on cycling it when we're in the reactor like once a day, but that would be too slow to do this. So they cycled it. The system worked. It worked automatically. They weren't having to do anything. They had a little program that did this. And you can see that what they built was robust enough to cycle about 15 or 20 times. So it accomplished basically what we wanted it to do. The BYU team made a similar system, similar looking. It's they housed theirs inside of a transparent tube. You can see that here, where this is the more narrow part that looks like the test that I had laying on the table. And then here's the fatter part, which has enough room to house a drive system. Now, these are very simple systems that have to be matured a great deal before they could put in a reactor. But you can see where we're heading. This hardly cost us anything because these students don't get paid. It's part of their undergraduate educational experience, and we just paid for the hardware. So I think it's a good way to do a little bit of early development, and we think of something along a similar line, we'll do it again. As far as publications, Dr. Yang and his students, they gave a presentation on these retractable sensors at the TRTR conference held just a month ago at NC State. So, in conclusion, advanced instrumentation is needed to test nuclear fuels, but the developmental process is difficult. It can't be just done in the lab. We need to be able to prove these newly developed sensors in operational conditions before we incorporate them into a very expensive long-term experiment. During FY21, this project irradiated sensors in all 4 of our INL reactors, plus the research reactor at ISU. So any reactor within 50 miles of our facility we used. Important part of our scope this past 2 years or past year and coming year is to focus on these high temperatures, especially with the neutron sensors. We leveraged a couple university capstone design teams to create functioning systems, and they demonstrated the retractable sensor concept. We have a limited amount of funding this year that we'll use for in-house development and maturing of these ideas that the capstone teams did. We'll put a professional technician on it and see how much we can mature it and make a good, robust system. Hopefully, we'll be able to demonstrate it in MITR sometime here in the next couple of years. Looking for funding to do that. So with that, that concludes my presentations. I think I'm finishing just a little early, but that'll give Kevin a little more time to talk on the next presentation. Are there any questions?
Thanks for your presentation, Joe. I don't see any questions that have come in yet. Got a comment about the senior design. That's a pretty good way to leverage student experience and for something useful, and perhaps even tie into the talent pipeline idea. But
We found it very enjoyable, and the students, they seemed to have a great time. They thought it was a great project.
Yeah, especially a realistic one. Right? It's a real world. I mean, it's something we would like. So I think it's an excellent idea.
Yeah. What'd you guys think about my cat? Was it a good looking cat?
Fabulous, fabulous. Yeah. So I haven't seen any other questions come in. So I think we can thank our speaker again. There's none in the chat here. No, I think we're good. We're a little bit ahead of schedule. So I see Kevin shared his screen. Why don't you wait, Kevin, until 45. We've got 6 minutes until you're scheduled to start, in case somebody wants to join at that time. Is that okay with you, Patrick? Is that what you're hopping in to say?
Yeah, that's exactly right. So a few minutes earlier is okay, depending on how long your presentation, Kevin, will actually last.
I think I'll make it in 15 minutes.
Okay, so then let's just wait until the due time, until 45. You can start and keep the screen on if you want.
Okay. So I'll do that. And
Well, I think we're about at the right time, Kevin. I'd like to, we can see your slides good. I'd like to introduce Kevin Tsai from Idaho National Laboratory. And he'll be talking about treat concurrent testing of instrumentation. You can take it away, Kevin.
I just want to make sure because I'm seeing at least the webcam screen, but you guys don't see that, right?
Correct. So all we see is your slides. All the GoToMeeting stuff is blocked from our view.
Okay, that's good then. All right, so thank you for that introduction, Austin. My name is Kevin Tsai, so I'm a nuclear instrumentation engineer, as I have presented in the past couple of days. So in this capacity, though, I'm more of a point of contact between ASI or many collaborators who wish to take advantage of concurrent testing and treat. And I'm the kind of the person who will then work on all the parts in the background and coordinate with our the treat team to make sure the sensor testing does happen. Let's see. So as kind of mentioned by Joe, the objective here is to enable empower irradiation testing of instrumentation for treat. Most of this is to evaluate the impacts of radiation to environments of sensors. And in more case here is for treat, and so it's to also demonstrate sensor integration within a treat facility. All this is to support mostly the experiments that's been ongoing, similar to kind of the presentation Austin gave at the start of today regarding all the sensors that were used in the experiments. A wide array of them have been tested in concurrent testing before we deploy them into the experiments. And so as we mentioned before as well, the overall strategy is to perform these testing alongside other planned experiments and operations. And so that's why we call it concurrent testing. TREE has a handful of type of transients. They have the type of, they have their standard core characterization transients where they go through different pulses of varying height, pulse height, as well as so energy deposition, as well as peak power. They also have these things called trial transients, which is transients they will perform prior to an experiment just to make sure the reactor will function accordingly. And then finally, they have their actual experiment transients. And so the idea is to perform these sensor testing, for example, for the trial transients during the scoping to make sure your sensor works during that phase in a near identical neutronic environment to the experiment in which it's supporting. So the participants there's a whole list of people, so I can only list them in sense of the groups. So there's the ASI who take advantage of these type of a testing, as well as help me coordinate. We have the entire treat team. This ranges from reactor engineers to safety engineers, as well as operations. Work with them on a daily basis to make sure everything is going smoothly and all coordinated. And of course, we have some external collaborators that have caught wind of the concurrent testing and has gone through the process in which we are helping performing these testing. So a timeline of these activities in FY21 and 22. These are just some of the newer sensors that we have placed in during this time frame. Concurrent testing has been undergoing for about 3 years now, and so many sensors has gone through this process, and some are still in the middle of testing. Some but what I've listed here are just the ones that are new in this year. So starting out the year, you can see we have placed in the ultrasonic gamma thermometer. In November, we have, this is one of the external collaborators who came through to treat, knowing about our capabilities and wanting to do structural tests. We have imaging fiber assembly, which is Austin's presentation he talked about yesterday, as well as his pressure sensor. We do have CEF fusion chamber and SP&D planned originally for September. Now it's just placed as a placeholder in there and within the reactor as a neutron equivalent device. to support this testing in next year in July. We have ultrasonic transducer testing going on as well in September, and look ahead to is we're working on some concurrent testing expansion, which I will briefly mention more in the future work section of my presentation. Finally, we have as presented from yesterday, we have the Goldfinch sensor technology coming in January for their sensor testing prior to the SBIR. And then dosimetry, which I will only mention just lightly as dosimetry because it's still in the planning phases with a external collaborator. So the technology impact, as Joe mentioned, is that advanced instrumentation are needed for qualifying nuclear fuels and materials. So TREAT has these unique capabilities to posture access and nuclear plants. And so we do need unique sensor technologies. Most of them are obviously under development. And so what concurrent testing does, as I mentioned, is to enable the evaluation of these sensors in near identical nuclear conditions prior to the actual deployment. These activities ensures the successful integration and deployment of to support nuclear testing at TREAT. So to kind of give you guys all a detail, this is something I made just a handful of months ago to kind of help, provide information to everybody who is looking to do this testing. How we start out on the lower left is these titanium holders. They're TREAT equipments, so we have a surplus of them for use if anyone needs to use them. But they're mostly there just to enable support the insertion into these cooling channels. They're about ½ inch in diameter cooling channels in between fuel elements. And so what I do is help out on the preparation phase into these holders, and then work with the operators into inserting them into the cooling channels that you see in the second and third picture here. And this is kind of the reason why we talk about sensor integration, as well as what Mark from Goldfinch mentioned too. So outside of the reactor, we do have a cable route into the corner. Now, in this corner of the reactor, they have things such as a permanent DAS for interfacing to the interfacing controls, as well as anywhere we would lay down preamplifiers of etc. to kind of extend the signal if we ever need to. But the cable does route to a adjacent room, which is what is depicted here. The cables are routed to the experimenter's room. And so this is kind of the extra 20 meters that you need, basically 30 meters, 20 and 30 meters you would need to go from your experiment center all the way to the, your nearest electronic equipment, short of a preamplifier of the sort. And so in the lower left here is the experimenter's room. This is kind of the picture of what we had set up at the time when I made this slide. But we do have a cabinet as well as a handful of equipments lined up, ready to support experiments. And what is essentially happening here is within the experimenter's room, all the equipments plug into a network, a Ethernet network called the experimenter's network. This is where we have access into it that is not tied to INL. So experimenters from outside of INL can bring their laptop and connects to this network. And it is then patched in about a mile down the road. I want to say a mile, could be half a mile down the road, where we have the control room, which is in the lower right. That Ethernet comes out just behind the observer's area, where you can patch in and make sure all your equipments are operating. So then to go through the accomplishments real quick, as kind of listed here, we have things such as the NASA structural test, which is a collaboration between TREAT. We have a handful of the fibers that Austin presented on from the FY21 activities. Gallium SPNDs are kind of there for follow-on testing, but also to still provide a flux measurement to the nearby sensors for them to evaluate their testing locations. We have performed ultrasonic transducer test. This is for Josh Dawes' work with regards to their ceramic integrity. And finally, we do have dedicated positions. These are kind of positions that we have spoken with people who are wanting to do testing in the near future, just to make sure the position is held, and that when we do actually have the sensor, we can swap them in and out more readily and without much delay. So in summary, what I mentioned here is concurrent testing is a crucial component for sensor qualification as well as for successful deployments. Many sensors has gone through this process, and the future work is kind of open in the air, because concurrent testing is always continually evolving. I would end up, going in and go through the process a handful, 2 to 3 to 4 times within the calendar year, depending on the time of the year as well. And so it will always continue in terms of making sure sensors go in to be irradiated. And then separately, we are working on a kind of a concurrent testing expansion that is to reduce the turnaround time for in a much better manner, including adding new positions with access dimensions even up to 2.5 in diameter. And that should be it. I think I made it.
Perfect, Kevin. Right on time. Thank you for your presentation. If there's any questions, we can drop into the pane or the chat here. I don't see any that have come in. Yeah, I think that was an excellent presentation. I'd like to thank you again, Kevin. We can probably, we've got 4 minutes until the start of our next presenter, but we can probably go ahead and get it pulled up. It's Joe Palmer again.
Are you ready for me, Austin?
We're ready in 3 minutes. Okay. So you can probably share just get it into presentation mode, and then okay, maybe wait a minute or two before we get started.
Okay. For some reason, I thought I had another 15 minutes. Okay.
No, but these ones are the
short ones.
Yeah, exactly. It kind of threw me off for the second there too. I was like, oh.
Okay. Is everything good? Can you see me and everything, Austin?
Yep, audio's good, video's good, and we can see your slide. Why don't you just hang tight for about 2 minutes, and then we'll.
Yeah, we'll do.
We'll go. I think we're probably good to get started. So I'll introduce Joe Palmer again for those who have recently joined. He will be speaking today about the fuel refabrication prototype efforts that are going on here at Idaho National Laboratory. And take it away, Joe, whenever you're ready.
Okay, well, great. Hello again. Going to be a bit of a shift in gears here with this presentation. Talking about fuel refabrication prototype. So as far as objective, I'm going to give just a little bit of a background on what refabricating fuel is about. The Institute for Energy, IFE, formerly called the Halden Reactor Project, was the world leaders in this technology. And what they do is a fuel rod, 14-foot fuel rod is taken from a full fuel bundle. Then it's cut down to a chunk of, varies, but let's say around 200 millimeters. And what they do then is remove a pellet from each end, clean up the ends, attach end plugs, which have a instrument attached. Almost always for them it was a thermocouple, and weld up those end plugs. So now we have a little miniature fuel rod with a thermocouple out of it that can be put in, they put in a high pressure water loop and irradiated at conditions similar to what it saw when it was in the LWR reactor. So we want to further that technology, incorporate advanced instrumentation, perhaps fiber optics, linear variable displacement transducers, or perhaps ultrasonic based sensors. We'll start with thermocouples, but our idea is to, as it says here, capture that technology that IFE developed. Participants are myself, Austin, who's our moderator right now. He's the technical point of contact. And Corey Manning is our technician extraordinaire that's working on it. We have a professional weld engineer, Spencer Parker, help us with the welding. And our contact in Halden is Steiner Solstad. He's the project lead there. So looking at our timeline, we received the drilling and defueling modules in February of this year. It took us several months to get basically our work control process through our system so that we could go ahead and operate these pieces of equipment. And by the end of September, we had mostly completed checkout of the 2 modules that we had on hand. There'll be 3 modules. I don't think I mentioned that that's kind of how it works. There's a defueling module. It removes the pellets and cleans up the cladding. Then the drilling module is what drills the hole in the irradiated UO2 to accommodate the thermocouple. And then there is a welding module that welds the end plugs on. The drilling module uses fluids, and I'll talk more about that. That's one of the challenges. Moving to this year, we're going to complete checkout of the drilling module, and we're going to receive the defueling module this month. In fact, it is being shipped as we speak. It's going to go to Houston first, then we gets trucked eventually to Idaho Falls. We'll spend several months updating our lab instructions so we can fully operate the welding module, and we have a milestone to complete checkout of that by March. And we'll spend the spring and summer practicing with these pieces of equipment, drilling both cracked and uncracked pellets, and practicing installing instrumentation, including some alternate instrumentation. And by the end of September, we should, our goal, our milestone is to be able to make a little fuel rodlet that's all welded up with a thermocouple coming out one end. So again, then kind of reviewing these milestones, we have a milestone to receive the weld module. That was supposed to be by the end of September. For one reason or another, the folks at Halden, who are fantastic engineers and technicians, when you see their equipment, you're going to see how good they are. But they don't do their work quickly, and so that slipped a couple months. We have a milestone then to complete checkout of including that welding module by the end of March. And then our main milestone is to make a little miniature fuel rodlet. A miniature, it's a short rodlet, completed by the end of this fiscal year. So what's our impact? Why are we doing this? For decades, the Halden boiling water reactor in Norway. It was the RISA. It was the worldwide resource for assessing nuclear fuels and materials. So many commercial, both vendors of commercial power plants, operators of power plants, and EPRI used Halden's capability. They were head and shoulders basically above anybody else in a specific field of testing LWR fuel. Well, it was shut down in 2018. They were so good and so much effort had been put into developing their techniques. DOE has funded a certain amount of money to capture what they did. We're procuring 3 equipment modules. And as I said, they're designed to re-instrument these little chunks of fuel rods. It's part of a broader effort. They have other things that they can teach us to transfer expertise developed at Halden to relative facilities such as TREAT, HIFER, ATR, MITR. This fuel testing is key to advancing and qualifying new light water reactor technologies. So what did we get done then in FY21? We received the defueling module. Look at it, very professional looking piece of equipment. I'm going to show you a control panel and you'll see what a good job they do with their software as well. So it's basically a light duty milling machine. And it's equipped with this little shroud. You put the fuel rod right in here. It actually, for long ones, we're gonna have to drill a hole in the table. But you put the fuel rod in here vertically. And you use the milling bit to mill out one pellet and clean up the surface. While that's happening, this vacuum pump is vacuuming the fines away. And they literally just use a simple vacuum like this, but not shown here, which we since installed as a pre-filter that we can collect the fines. This equipment will never go into a hot cell. So we're trying to mimic some things in a hot cell, but it doesn't have to be exactly like it. One of the things we installed, Corey put together this beautiful barrier, kind of a transparent barrier. When Halden uses it, it's within a hot cell. And so there's some moving parts here that you wouldn't want to run into. And so we were asked to put some little barriers since we're not putting this stuff in a hot cell. We practiced defueling one surrogate rod. We made a little mock-up up. It's actually out of stainless steel rather than zircaloy. And we epoxied molite, which is a pretty hard ceramic inside of it. And we put it in the machine and we were able to clean out one pellet and clean the oxides off both the inside and the outside. And then it would be flipped over and that would be done on the other side. And so this cleaning of the oxides is prep for welding. You can see the little shroud there for catching the fines. He didn't use it in this particular first practice. So this would all be highly radioactive if it had been irradiated. The second piece of equipment is the drilling module. It's horizontal, the other was vertical. And so the fuel rodlet is placed here. And surrounding it is a chamber which is filled with pressurized CO2, liquid CO2. CO2 is not a liquid at room temperature unless we're at a pressure of about 50, 60 atmospheres. So it's liquid CO2 is put in here pressurized, and then we transfer liquid nitrogen from this tank. It transfers through a little tube right there into another chamber that surrounds the liquid CO2, freezes the liquid CO2. Now we can depressurize it because once it's at minus 280, it can see atmospheric pressure and everything is fine. And then what happens is this is automatically moves this way. There's a drill bit placed in it, which I will show in the next slide, that drills out the fuel rodlet. What did we do? Well, we again built a nice little transparent shield. This is Corey's nice workmanship. We incorporated 2 vacuum systems. Here's one right here, and it's vacuuming through a filter right here. So this is where the fuel fines are caught, and that is the filter can be removed with manipulators and a new filter put in. And then we have another vacuum pump right here, which this little plastic line has since been replaced with a metal one, and it evacuates the jacket for this dewar, and there's a jacket here. So when you want everything to come back to room temperature, you allow air to get into these annuli, and that enables all this stuff to boil off and remove all the cryos. We practiced drilling with the cryo system active. You can kind of see right here, this is our practice. You can barely see the hollow drill bit right there. You can see liquid nitrogen venting off here. Here's the control system display. They did a beautiful job on this. This is the temperature in this chamber right here. So this is when we pour in the liquid nitrogen. Right there. And this is, there's a vacuum. We're measuring the degree of vacuum going through the hollow drill bit. As you're core boring through here, it frequently plugs with a solid core. And you have to pull it out and actually use like a little rod to rod it out and then start again. So it's a very nice control system that they put together. Okay. What are we going to do in FY22? Well, we're going to receive the welding module, which should be here within a week. We're making little rodlets, which will mechanically crack some surrogate ceramics. And you see how that compares to the actual cracked ceramic. Looks a lot like it. Here's the welding module that we'll use to weld it up. Before we weld it though, we have to dry it out. There's a drying chamber right here. We weld it, and then right in here is a leak check chamber where you can pull a vacuum into a helium leak check. This is what we're trying to complete. This one's only about 150 millimeters long, probably a little longer than that. And the little purple represents the thermocouple installed. So that's our objective. Conclusion, summary, we're capturing this critical technology from Halden. There's 3 modules that do defueling, drilling, and welding. We received 2 of them in FY21. The next one we're going to receive next week. By the end of FY22, we will produce a fully instrumented prototype fuel rodlet using surrogate ceramics in place of UO2. So that completes my presentation. Are there any questions?
Thanks, Joe. Let's see if I can see any questions here. I do not see any questions.
Okay.
So I'd like to thank you. I'm pretty excited to see the welding module results. Should be pretty interesting. See it all come together.
Yeah, we'll have some fun working with it this year.
So that actually takes us into our break. Just 2 minutes early, so everybody can enjoy their 2 minutes additional break. And we'll be back at 3:30 Eastern time. So we'll see you then.
Hello.
Hi.
Hey, Austin.
Perfect. Looks like you know the drill.
Okay, so you can see my screen, right?
Yep, we can see it's in presentation mode, and I can hear you and see your video also just fine.
Okay.
Right on time. So I'd like to welcome everybody back for our next presenter, Uday Singh from X-Wave Innovations. He'll be talking on the development of radiation endurance ultrasonic transducer for nuclear reactors. And you can take it away when you're ready.
Okay, thank you, Austin. Hello, everyone. So again, I'm Uday Singh, and I'm a PI of this Phase 2 SBIR project titled Development of Radiation Endurance Ultrasonic Transducers for Nuclear Reactors. And I'm from X-Wave Innovation. We are a small company as SBIR by its name, and we are in Gaithersburg, Maryland. And let's go to the next slide. So first of all, I don't feel comfortable explaining that what is the need of sensors in the nuclear reactor, which people have already explained very nicely. But only thing which I'm going to tell you is that what motivates us is that we wanted to demonstrate a great accuracy, reliability, resilience, and ease of replacement and upgrade. So these are the 4 factors we take into account in all our designs, and then work around it so that people can use it conveniently. So this ultrasonic transducer is just ultrasonic transducer. There is nothing special about it. But what we are doing differently is that we are using all the material properties, how the acoustic wave propagates in the material, and thermal expansion, and we are all taking into account into engineering design and coming up with this REUT ultrasonic radiation endurance ultrasonic transducer, which can demonstrate a high temperature operation and potentially operation in nuclear environment. So it is totally customizable. Any user can use it as they want it. So the participant of this project is the project Melissa Bate is the program manager for this project. I'm the Singh PI, and we work with Joshua Dow from INL, Orano, Swain Badr. We have in touch with David Carpenter for irradiation testing, which is a little bit slow these days. And we have other colleagues, Ijo Wang, Carlos Rental, Shi Gong, and Omid. On the other side, my boss Dan Jiang, and Bill Wilson from TOC, they are working in the on the commercialization side. So here I'm just trying to so now we are in a phase 2. So what we are trying to do is that I'm going to explain the phase 1 results, but here, so we are just trying to make this transducer design much user friendly, so that people will like to use it. They don't want loose connections, they don't want installation issues. So we are improving our design, and what we are further going ahead with that is these ultrasonic transducers, then how can we use them? So we are building temperature sensor, pressure sensor, acoustic emission sensor, liquid level sensor, and also there is a little bit ambitious plan to make these transducers wireless, which we do not want to have a wire connection with these ultrasonic transducers, which is ongoing. And then finally testing and validation. So on the right, you can see here is that these are our test plans. Of course, we got delayed a lot by COVID, but we have some good results to present. And the irradiation testing, I hope so that by end of this year or very early first quarter of next year, we may have some irradiation test results as well. So currently what we have achieved here is that we have used our REUT using lithium niobate and zinc oxide. Lithium niobate cheaper, easier to test, break, and reinstall another one. Zinc oxide a little bit expensive, but still we can acquire them. We wanted to try aluminum nitride, we wanted to try other piezoelectric, and right now we don't have them. But this REUT design can be used with any piezoelectric crystals as test means like this whole infrastructure demands, like if certain piezoelectric is good in certain applications, it's good enough. If lithium niobate can work, then by all means use lithium niobate. And with this new design, we have currently achieved temperature sensor, viscosity monitoring sensor, and acoustic emission and guided wave structural health monitoring system. We have developed application software around these three different sensor systems, and right now we are again performing. We have some results for high temperature and irradiation test. So let's go ahead. So the reason, or I mean, like the advantage, again, I don't feel comfortable again that what's the advantage of these transducer going to be for the nuclear reactor and the future nuclear reactors, because I'm just gonna quote this from 2016 report from ORNL, Oak Ridge National Lab, that of course there are ultrasonic transducers and they are used in nuclear reactors. There's no problem, but there is a problem. They mentioned very nicely that it fails at elevated salt temperature, and then if we use a waveguide, then waveguide has its own problem because it changes the heat sink. So there was always a desired need that if there is a transducer which can support 700 degrees C or more, then it will be good good for this sensor development. So our transducer is good at 800 degrees C or even higher. We have tested it up to 1100 because we use lithium niobate, so above 1000 degrees Celsius it breaks. But for 800 degrees Celsius it gives you a means like long-term operation. It does not degrade, and it is a potentially irradiation tolerant. Potentially is underlined because we haven't done the irradiation test, but in our design there is nothing like that it will fail. But again, we'll call it a potentially being radiation tolerant. So this is the phase 1 result. So what we have is that we in phase 1 of this SBR project, we developed 2 transducers designs made totally of stainless steel and ceramic and lithium niobate. So there is apart from these 3 materials, there is no other materials. And this is, as I already mentioned, that this is all engineering problem right now, that how we really handle the acoustic inside it so that the performance of these transducers is good. So the backing also is made of stainless steel, and this whole design can be transformed into any metal or any other means like alloy if application demands it. So this is purely a design problem. So here we have used a lithium niobate, and in the middle you can see, I believe everybody can see my cursor, right, Austin? So here
Yes, we can see it.
yeah, so here this is a lithium niobate. This is a 6 megahertz transducer, and we have subjected it to 800 degrees C as it was installed on this half-inch stainless steel plate. And you can see that by the 800 degrees C, the echo is not going bad. It's rather it improves, because that's how we design it. The whole thermal expansion, the material property, acoustic has been taken into account in design. So the more higher temperature you go, the performance of this transducer is supposed to improve. Of course, there is a limit based on the material property itself, like stainless steel. By going above 1100 degrees C, it may have its own problem, and lithium niobate will lose its piezoelectric property. So we will always going to have a limit on this transducer operation based on the material we use in the whole housing fabrication and the piezoelectric. But with the stainless steel and lithium niobate, this transducer works fabulously till 800 degrees C. As you can see that we have done this repeated measurement 7 times, and amplitude always comes back and repeat itself. So peak to peak signal of this first echo repeat itself multiple times. Of course, there is always slight variation in amplitude because it involves a soft metal gold for acoustic coupling, and that for the first thermal cycle it just readjusts itself, but later on it does not it retain its property and it does not change. So after first heating, this system maintain its operation for a long time. But apart from that operation high temperature, we have tested this system for different piezoelectrics. So again, these are 6 megahertz, 20 megahertz, and 30 megahertz are different piezoelectric thicknesses, and changing the thickness of the lithium niobate, we can get a different frequency. And as you can see that these are the echoes we get from different piezoelectric elements. That means we can make this any frequency transducer. There is a limit that the performance is not so good if you try to use 2 megahertz or below, but above 2 megahertz it works perfectly fine. And this is the FFT on the right. So you can see that if needed, we can go up to 40 megahertz based on this stainless steel 316 design. So it's a very high frequency, high performance transducer. and we have tested its high temperature performance, and we saw no degradation at all up to 800 degrees Celsius. Above 1000 degrees Celsius, the degradation starts, and that is just because of the lithium niobate and some variation because of the stainless steel. But once we have subjected it to 1100 degrees Celsius, we took it down, we cool it down and change the piezoelectric, and the transducer starts performing again. So the stainless steel do not get bad. It was the lithium niobate which was going bad. So moving on, so this is our like at the bottom, this is our new REUT design, which is, we call it REUT 3. And this is this we have a delay line on the top, which may be of use to certain application, which may be not, but we are using it and it is easier to install. So we are using zinc oxide, and sometimes people ask that, do you always need a gold coating? No, zinc oxide we have used without a gold coating, and here is the first pulse signal and then FFT of this. So we can easily see that this zinc oxide is almost a 6 megahertz transducer. We have used with this new transducer, this is the lithium niobate, and with this delay line, which is 20 megahertz, you can see that the bandwidth is almost 30 megahertz, and this is a single pulse transducer. So that having this sharp pulse implies that we can do better time of arrival measurements. It means that better thickness measurement and related applications. So we have used this transducer in thickness measurement, and we can measure thickness of stainless steel at higher temperature absolutely fine. So again, I have already mentioned that the limit we have is that the operation of these transducer is good if you have a frequency of operation above 2 megahertz, and that's the design or limited by the design of the backing material. If any other design is needed, the variation is not difficult. We would really like to try aluminum nitride with this, because aluminum nitride is considered and proven that it is much more radiation tolerant. But once we get this, then this ultrasonic transducer which we are presenting here means like can potentially operate at the limit of aluminum nitride. Now moving ahead, that so this is the temperature sensor we built. So this is the first version of temperature sensor, which comes with flange. Either it can be tightened on the structure with a screw, or the flange can be directly welded wherever it needed. Again, it's like I'm not going to repeat again, is that this transducer can support higher temperature. I have already presented in phase 1, and this one can do too. But right now I'm just moving ahead with the testing, that how the sensors can be developed around this transducer. So this is the 100 millimeter waveguide, and on the top we have a one small notch. So you see the reflection, you can see here is the reflection from notch and the end, and the time delay difference between this notch and the end are used for the temperature measurement. Here the transducers can be run using 30 megahertz longitudinal wave system. So means like 0.1 millimeter thickness Z-cut lithium niobate, or 0.3 millimeter thickness X-cut lithium niobate. This material generates 6 megahertz shear waves, shear wave in the waveguide. Both the systems can be used for temperature measurement. We have another design ready, which we are waiting for that to get it from that manufacturers after from the CNC suppliers. So this is with NPT, and it can be used in systems where the high pressure is there, like measuring high pressure liquid or gaseous systems. Because of the NPT, it can potentially go up to 20,000 psi, up to the limit of NPT connectors. We have a whole software system developed around it. We have a pulsar, we have acquisition digital picoscope as acquisition system. Now moving on to some tests. So we have put this waveguide inside our oven. We've modified its design, and then we measure the time delay difference between the notch signal and the end signal. So here is the comparison between the longitudinal wave system, 30 megahertz longitudinal wave system. Here you can see that the thermocouple and the waveguide system up to 700 degrees C was following very nicely. We didn't went here above that because we can't run the system whole night. We just need to shut it down. So this from here to here, 700 minutes, we were just tested that, and then we repeat to do it again, and we couldn't go just beyond 700 just for safety reason. But if we want to do the quick experiment here, so what we did here is that we For a 6 megahertz shear wave, we just subjected it to a higher temperature up to 1000 degrees Celsius with stainless steel waveguide. And you can see that 3 cycles, so first cycle has a slight variation, but second and third has a very high repeatability in time delay variation. And also we measured the end-to-end pulse echo. So what we try to test is that if the transducer is if the waveguide is going bad or transducer is going bad, then the amplitude between this notch signal and the end signal will vary. Here you can see that reaching up to 1000 degrees Celsius and then coming back again in different cycles, the measurement has no issues. We can measure it to the, we can use this waveguide for 1000 degrees Celsius measurement for means like for a very long time. We use we try to use titanium for a waveguide, but we come with a problem that all these measurements were done in ambience. So titanium gets converted into titanium oxide and then it stopped performing. Apart from that, even though if we do it in vacuum or other inert environment, the problem is that the titanium we have here, titanium has a phase transition around 700, it becomes brittle, and at that time the acoustic propagation stops. So we cannot use this titanium waveguide above 700 degrees C, although we have it, we can calibrate it, but the performance is not good as stainless steel. So this temperature system can be designed with any metal waveguide, like except titanium or certain similar, but we can use molybdenum or we can use any other platinum if desired. And the length is not a limit. We can weld any other metal we want to. Moving on, so we have used to develop a viscosity sensor using this transducer. So it is another application we developed. Here is the wave delay line on the top, and how it is means like I will not go here in detail that how it is doing the viscosity sensing, but for in simple word that shear wave responds to the liquid viscosity. So if there is any viscosity on the tip of this any fluid with a different viscosity on the tip of this transducer, it will this transducer will respond because this has a shear wave piezoelectric crystal inside it. So here you can see that we calibrated the system with respect to air. So when there is no fluid, we have a 0 reading, but when we have a water, then the viscosity of the signal is changed, the response is changed. Here the viscosity arbitrary unit is the attenuation factor, and the more negative it is, the more viscous fluid is. If it becomes positive, then it means that the system is more less viscous. So we can calibrate, we can choose reference as water. In that case, the air will have a more positive value because it's less viscous than water. So you can see that the spectrum is pretty broad. We can go from water to honey, and that's the fluid we have, and we can go further as well with different fluids, but I don't see that it I don't know that what viscosity level is good for nuclear application and what we should be doing. But apart from that, one thing more here, you can see that we are capable of even differentiating different fluid engine oils. So this viscosity sensor is capable of differentiating different fluid. So we don't want to call it as a viscosity sensor. We want to call it as a viscosity monitoring system because you can track the viscosity change at higher elevated temperatures. And we have a whole software and built around this. So now moving on to the guided wave. So same, this is the ultrasonic transducer and how it is mounted on mounting ring. You can see here is that you just thread it on this plate, and there are 4 screws fastened here. So in this guided wave structure health monitoring, what is happening is that this TX is sending a wave in every direction possible, and this one is receiving. And here this red and blue are two means like a wave received by this RX when the TX is transmitted. The red and blue are 2 different scenarios, meaning that in one of the case that one of the screw is loose, and as you can see is that it is very hard to differentiate that is there any difference. So what our software does is that we take the difference between the earlier signal and then current signal, and that difference is used to identify that is the system has any change. So moving on, to the down here, you can see that if screw 1 is there, or screw 1, 2 is changed, or 1, 2, 3, or 4, all 4 of the screws are changed, you can see that the FFD of the different signal capture is different. So we have developed a whole system around it. It's like to see that if the system is changed with respect to its present or past state, which can be used in case certain sensitivity is required, that certain cases that some nut is loosened or something else. The same thing goes to the acoustic emission. So here is a zinc oxide based this REUT, and we used it for acoustic emission, and these are the acoustic emission captured by the transducer. Here we have this delay line inside. It is not directly attached to the system, so it is still able to capture the acoustic emission signal. Here this transducer is with lithium niobate directly connected to 1/4 inch stainless steel, and it is still able to capture acoustic emission signals, so with delay line, without delay line, or with delay line. So this system, this REUT, although it has been proven for a high temperature, now it can be used for high temperature acoustic emission sensing for structural health monitoring. We have also used
wrap up quickly.
okay. So we have used comments like a software we have developed software where we use a maximum likelihood. So even if your system is quite big and outside the scope of this system, it can still tell you that which direction the acoustic emission has happened. And we have our software can on multiple repeats, we have tried that the accuracy is very high. We are also building electronics around it, and this electronics can support 4 sensors. So we can use 4 sensors for structural health monitoring, guided wave. We can use 4 sensors for temperature measurement, viscosity measurement, thickness measurement, or we can use any combinations as we like. So this is the electronics we are building. And this is the structure health guided wave system we have built with the software. So it can even tell that where that flaw has originated inside the system. We have drilled used aluminum, and we have drilled a very small dent inside it. Now summary, our transducer is potentially radiation resilient, because if we change the piezoelectric accordingly, there is no element which can go bad. Easy to install, just screw tight it will be fine. We do not use any organic couplant. We have gold, silver, and aluminum. There is no electrical issue. The electrical connection maintains its operation for at high temperature. Easy to upgrade, just change the piezo and move on. Compatible with existing systems, so pulsar and the data acquisition exist. Ultrasonic has been in use for a long term. We can use that system if there is. We just have a new sensor head, and low maintenance. So we are right now working towards the commercialization. We are talking to nuclear reactor people if they like it, and all the answers right now we have found is no. And in terms of summary, we have developed modified REUT, viscosity sensor we have developed, temperature sensor we have developed. We have a structure health monitoring software, and in future work we wanted to go for an irradiation test and perform performance evaluation and validation at high temperature for these systems, not the sensor head, I'm talking about systems. And at this moment, I just wanted to last word is that we are open for collaboration. We see that these ultrasonic transducer has higher potential for testing piezoelectric materials or building an ultrasonic sensor system. These transducers can be of great help. So we are open for collaboration at this moment.
Thank you for your presentation. That was excellent. We're out of time, but we did have a handful of questions come in. I've got some myself, actually. If it's okay with everybody, I'd like to table the questions until our moderated discussion at 4:40 Eastern time.
Sure.
If that's okay with you. That sound good with you, Patrick?
Yeah, I was going to say we should do that. This probably will be a similar interesting conversation as what we had yesterday. I noticed Josh is not part of the panel right now, but maybe I'll go try and fetch him. Well, yeah. So I'll try to figure out to make those appealing to use. You know, the more we use them, then the more they will be accepted in essence in answering Udai's comment about.
Yeah, similar things like sometime electrical failure or backing failure, all those things, problems. So we are evolving towards like how to use a piezoelectric system. No, we just wanted to do that. This is a system. You put your piezoelectric inside it and then develop that sensor system around it. Some people have much more better idea about sensor. Why to start with a basic piezoelectric?
Correct. I mean, you know that one of the things that we have pushed a lot is multi-point. That's one of the most attractive ways to evolve from a thermocouple, right? Which is what you're competing against, particularly for the temperature measurement in this case. Well, there's a lot of work on structural health monitoring. There is now emerging, and I am sure that your sensor will be more, again, generate more interest once we move into this space of structural health monitoring for advanced reactors. So yeah, let's continue this conversation later. We can collect input from others. I don't have to be the only one. I saw Dan came up too, but maybe in the interest of time, we have just a few. So let's listen to Intelligent Optical System, to Marvin, and then we can come back later if you can stay on, Uday.
Sure, I'll be here. Thank you.
All right, thank you.
That's perfect. Thank you. Looks like we've got Marvin's slides up and ready to go. I don't hear any audio though, or see the video.
You want me to start?
Oh.
Do you want me to start? Can you hear me okay?
Yep, now I can hear you. We had an echo for a second, but I think it's gone.
Hello?
So you can go ahead and get started whenever you're ready.
Can you hear me?
Yes, yep, we can hear
Hello?
you. Yes, we can hear you well.
Okay. I'm going to start on the assumption that you're hearing me, and my colleague next door will tell me if I'm wrong about that. Okay, so the title of my talk is Advanced Laser Ultrasonic Sensor for Fuel Rod Characterization. And our motivation is that we see an unfilled need to measure fuel rod pressure without removing the rods from the assembly. And if we can do that, we see large savings in time and cost. Now, the current methods to measure internal pressure in a cooling pool require partial or complete removal of the rods from the array. This is undesirable. Again, it takes a lot of time if measurements are going to be done this way. Now, there are conventional transducer-based testing instruments that can make measurements without rod removal, but they only sense the presence of internal water due to a leak. And so that's good as far as it goes, but there's no direct measurement of pressure. By contrast, our method allows a direct measurement of pressure. And the goal is to determine under pressure from gas leakage or overpressure from excess generation of fission gases. Both of these are important needs. And as an aside, we also can actually measure the rod wall thickness with a very high accuracy if there is a need for that. Now my slides won't advance. Oh, no. Excuse me. Okay. So the method we use is laser ultrasonic testing. And the idea is to generate circumferential waves, waves that travel in both directions around the circumference, and by interference, they create standing waves. So, and we're not touching the surface. The idea is to use a pulse generating laser directed here that generates from the laser pulse, generates ultrasonic waves. These waves coalesce into circumferential resonances, And the surface displacement is measured with this probe and sent to a detection system. And by the way, we can do this 180-degree orientation or with overlapped beams. This is another way that we can do it. So I mentioned that standing waves are created, forming a series of resonances, and I'll show you exactly what they look like in a few slides. So what we want to do is to correlate the internal pressure, and we know it. We have a series of surrogate rods with a known pressure, and we're going to use them to generate a calibration. So we're going to correlate the internal pressure to the shifts in the resonant frequencies with pressure. And each of the peaks, each of the resonant peaks could shift in different ways, and we have to accommodate that. So the benefits of laser ultrasonic testing: small laser spots, high bandwidth, fiber delivery, and the measurement head has nothing in it but glass and metal. Same for the fibers. So it is expected to have high thermal and radioactivity resistance. Well, the project background: we now have funding from DOE for a phase 2 SBIR, and we're now in the second quarter of the 2-year project. The participants, of course, is my company, and I'm the PI. We have a consultant, Peter Nagy, who is a world expert in ultrasonics and is doing the simulations. We have also these advisors who've given us a lot of guidance. Okay, so this is the way we see it. There are experts in the audience who may have a different interpretation, but as we see it, the pressure measurement in the cooling pool enables safety, improved safety for rods, and not only that, it allows comparison with simulation results. Going back here, if, for example, a rod with overpressure is found, it could be removed from usage. Or if there's a leak, likewise, it could be removed. So that's the idea for safety. And then we also offer the ability to compare with simulation results. So again, as we see it, the interest spans both the service companies and the fuel vendors, and the stakeholders are the service companies, who are really the customers, and the end users, who are the nuclear utilities. So here's the setup for our proof of concept test. We have a sample rod with a known internal pressure immersed in a cuvette filled with water. And the generation, the pulsed generation laser, is focused onto the wall right here. It generates ultrasonic waves. As they say, they travel around the circumference, and the detection occurs on the other side. This is our detection system. Focused down, it collects light back and demodulates that very small phase difference from the surface displacement to generate an output, electrical signal, directly proportional to the surface displacement. So the laser beams in this case are free space beams. This is not a fiberized setup. The generation beam is infrared. The detection beam is visible. So once again, as I said, we're exciting standing waves in the wall. And there is a whole series of resonances depending on how many wavelengths are included or induced into the circumference. And it can go from two wavelengths up to as many 15 or 20. This is an example when we have the 10th order resonance, and the dashed lines show the unperturbed wall profile. It's just a circle. And these wiggly lines are the actual profile for the 10th order, and the amounts of these deformations are greatly amplified. In fact, they're quite small. So this is what you excite for the 10th order. Now, here is the frequency spectrum. And you can see that we go all the way from order 2 up to, it says here 17, I counted about 15, no matter. We have these very strong peaks. And for every one of these peaks, because they're so narrow, we get very accurate data on their shift with pressure. And we use that data to develop a calibration for future measurements. So here are the results of measurements in both PWR and BWR rods. Again, a series of rods with different pressure loaned to us by EPRI. So we are processing the shift of every one of those peaks. And by careful processing, we're able to produce a linear dependence of the, it's called a shift parameter or a percentage shift on internal pressure. So this is sort of a process value measured on the percentage of deformation, of frequency shift, excuse me. And of course, here's pressure. So we have these two different lines. You can see that our measurements agree very well, fit to a straight line. Likewise here. So by processing and using this parameter, we're able to produce a straight line, which easily can be used now for calibration. So you measure a shift of say 2.5%, you go over here and then come down and you get the internal pressure. I haven't done it, but it's something like 170 PSI. And it's different for the two rods just because there's a small dimensional difference in the rods. So that's our technique. Again, we measure this frequency shift metric, and now it can be used here to determine the pressure. So that's the goal of how we would like to do measurements in the pool without removing the rods. Okay, so our proof of concept experiment, as you saw, leads a linear plot of this calibration metric, percentage shift versus pressure. And as an addition, we can also measure the wall thickness with this very high accuracy. Now, the other important thing is we've done a lot of work on simulations, and they've helped us understand how to process the data. This has turned out to be very useful for us. And furthermore, by comparing to the measurements, we can improve the accuracy of the model so as to generate a curve like you saw before that is the same as the experimental curve. So future results, we'd like to make measurements on a surrogate rod with controllable internal pressure and variable fill gases. Anybody in the audience who has an idea of where we might find that, I'd appreciate if you'd let me know. We want to extend our simulations and our measurements to include fission gases. We need to be able to detect overpressure from fission gases, and to do that, we need to do this calibration process. Equally important, we want to design and test an ultra miniature underwater probe. This probe can be no longer than about 2 or 3 millimeters to fit inside the assembly. So again, access between the rods in the assembly, in the array. And finally, pursue commercialization, and we actually have some interesting connections already to start. So that's my presentation, and I welcome your comments and questions, and thank you very much.
Thank you for the presentation. That was excellent. I've actually got a handful of questions myself. I'm thinking about if we should just have a couple minutes here, if we should table those in the discussion after our final presentation. Would that be okay with you?
Yes, yes. Yes.
Okay. So I think we'll do that because they're kind of related, similar applications. So I mean, I think the discussion will be centered on the ultrasonic measurement techniques and capabilities and applications, which is a pretty interesting area in general. So I think it'll be a good discussion. So with that, I'd like to introduce the next and final presentation today, Kiyo Fujimoto from Idaho National Laboratory and Boise State University. And she'll be discussing the design optimization for printed melt wire array encapsulation. And we can see your slides here, Kiyo.
Cool. Can you hear me?
And yep, but I can hear you also.
Perfect.
So you can take it away whenever you're ready.
Okay, thank you. So hello, everyone. Thank you for taking the time to attend this presentation. As Austin said, my name is Kiyo Fujimoto. I'm a graduate fellow Idaho National Laboratory in the Chemical Systems Group and a PhD student at Boise State University. And also, as Austin mentioned, I will be presenting on design optimization for printed melt wire array encapsulation. So this project focuses on introducing additive or advanced manufacturing techniques to develop and optimize advanced manufactured melt wires as we are trying to expand the range of melt wire capability. So the incorporation of advanced manufacturing for melt wire fabrication introduces the ability to produce geometries that wouldn't otherwise be achievable with classical fabrication methods. And it also provides a pathway for device miniaturization that also wouldn't otherwise be possible with classical fabrication techniques. And from this point forward, I will try to refer to the additive manufacturing, advanced manufacturing as AM. So AM melt wire development is ongoing work, and the activities this year build upon efforts from previous years. So in future slides, I will give a brief overview of those efforts just to give better context and clarity, and hopefully for the motivation of the work performed in FY21. So this year we focused on packaging method, or the packaging method for AM melt wires, with activities geared towards the development and optimization of the substrate or encapsulation design for the welding process, and also to enhance X-ray computed tomography resolution of encapsulated designs, or encapsulated melt wires, sorry about that. So with regards to schedule, we submitted a technical report in FY21. We did experience some delays just due to equipment availability, but we were able to complete the report, and I have included an image of that title page just in case anyone is interested in reading it. And for FY22, there will be a continuation on the focus on encapsulation design, but it will shift more towards material optimization with welding and XCT processes, again, guiding those efforts. So we have started our initial planning and material down selection and have scheduled milestone reports for December 2022. So there is a collection of us working on this activity, and those include Corey Manning, Kurt Davis, Malvina Wilding, who is the PI of this project, James Milloway, Lance Hone, Richard Skifton, Robert Seifert, Austin Fleming, who served as the TPOC for this work, and then me, and we are all from the Idaho National Laboratory. So temperature is a fundamental property that is measured during an irradiation experiment, as you all are probably aware of. And this work supports irradiation experiments by advancing melt wire technology, by expanding the temperature monitoring range of melt wires, and also by providing finer temperature resolution for peak temperature detection. And with that, direct support to the nuclear energy community is then afforded through the current customer base, which includes any of those looking to conduct irradiation experiments in MTRs where real-time temperature monitoring is not required. Additionally, there is potential to expand outside of the NE industry to include passive temperature monitoring of processes or methods where peak temperature detection is desired and a miniature or compact package is required. So previous studies have looked at encapsulation and miniaturization of AM melt wire packages, and we also conducted a benchmark study in FY20 of AM melt wires versus their classically fabricated counterparts. The initial AM melt wire encapsulation design was a result of a customer design requirement, and that work produced a melt wire chip that is shown in the figures on the right of the screen. So these right here. And this device was 5 millimeters in diameter and 2 millimeters thick. So this is a significantly smaller profile than what can be produced with classical encapsulation methods and materials. This design included 2 stainless steel discs that were 5 millimeters in diameter and 1 millimeter thick. Then we went ahead and printed the wires within one of those 5 millimeter discs that had a dimple previously etched into it. Once those wires were sintered, a second stainless steel disc was welded in onto it to encapsulate that printed melt wire. So currently for classical melt wires, quartz is used as the encapsulation material, and this facilitates visual observation of the melt wires before and after experiment in order to identify any indications of melting. And also using the quartz requires the use of glass blowing techniques to fabricate the encapsulation. And with current designs, we are pushing the limits of that technique in terms of miniaturization. So moving on to this first iteration of the AM melt wire encapsulation, using stainless steel as the material, we had to transition away or transition to a different analysis technique. Because stainless steel is opaque. So this took away our ability to visually observe the melt wire response, like with the traditional wires or traditional packaging method to observe their response. So with this, we introduced X-ray computed tomography methods to image the melt wires within the opaque capsule. We did have some very promising results from that work, and we were able to image the melt wire material before and after testing through the new encapsulation material, and we were able to identify distinct signs of melting seen as material separation for this specific metal. So that's displayed right here. Which is for the panel labeled C. But we did identify some shortcomings of that first encapsulation design, and we did aim to address those in the FY21 work. So for the following year, a benchmark study of AM melt wires was completed by evaluating the temperature response of AM melt wires and classical melt wires of similar bulk composition. We used tin, zinc, and aluminum, and they had expected melting points around 230 C for tin. We had 420 C for zinc, and then 660 C for aluminum. And for us to eliminate any variables, or as many variables as possible, we chose to use the classical quartz encapsulation method for both sets of melt wires. So through differential scanning calorimetry and furnace testing, we were able to determine that the performance, or we determined that the performance of the AM melt wire capsule was consistent with that of the standard melt wire capsule. We also observed something really interesting that the melt wire, or the melt behavior of the classical wires, varied with each material. And one very promising aspect of the printed melt wires is that they all seem to demonstrate similar melt behavior with the formation of beads or bubbles on the surface of each print, and those have been highlighted with those blue arrows in the figure. So to move on to our FY21 work and building off of previous activities, feedstock development or ink synthesis activities were required, just as the materials that we were interested in printing just are not available commercially in an ink form compatible with the AM technique of interest, which was aerosol jet printing for this project. So the materials that were used were the same as before with the benchmark study that I mentioned previously. We had tin, zinc, and aluminum, and the melt wires of interest were then obtained in nanopowder form from a commercial vendor. They were then combined or dispersed within a co-solvent system that we have previously had success with AJP. So the as-received powders were then characterized for composition with XRD and EDS, and then the particle size and morphology was confirmed through TEM. Now, final characterization step for the melt wire feedstock or ink includes taking the as formulated inks and subjecting them to differential scanning calorimetry or DSC to evaluate them for their expected melting point. So this is an important characterization step that occurs with classical melt wires as well. And obviously we don't formulate those into inks for testing, but we do test each material batch that is intended for melt wire use to validate melting point. So we do purchase our materials from reliable vendors, and these materials come with material certifications, but melting points always need to be evaluated empirically. So from DSC analysis, we have expected melting points of the AM melt wires of 228.3 C for tin, 415 C for zinc, and 656.2 C for aluminum. And similar to the first iteration of the AM meltwire encapsulation, stainless steel was chosen for its machinability and weldability. This second iteration, though, addressed two critical features of the first design. First was the overall thickness of the encapsulation material, where a thinner capsule would really help to reduce attenuation during XCT imaging that's caused by the excess amount of material surrounding the melt wires. And this ultimately enhances our ability to evaluate melt wire performance with XCT. So in order for us to do that, we moved away from using that stainless steel disc with a small dimple for printing the wires into and worked towards developing something as shown in the bottom of the slide, where we had an overall sidewall thickness reduced to 0.6 millimeters and then the floor thickness of 0.2 millimeters. So it's shown in this drawing right here. The second design change that included a complete feature overhaul of the capsule to allow for a new sealing process that would introduce the ability to seal the melt wires within an inert atmosphere. And this is critical for performance of oxygen-sensitive melt wire materials, and it really just minimizes any extra variables that could come into play and affect device performance. So also included within these design considerations was the need to minimize premature melting of the wires during the sealing process. And so this was accomplished by printing the wires in a location opposite to the laser welding, to where the laser welding would occur, which you can probably see from the first iteration wasn't necessarily the case. So you can see right here that the printed wires were printed onto the floor of the base that was created, and then the weld would occur on the opposite end of that. And on that first iteration, we have the base disc right here with the dimple etched into it with our printed melt wires. And then if you can see the seam from the weld, we just moved that a little bit further from the melt wires to minimize the premature welding or premature melting. So, and then premature melting and then overheating of the capsule during the welding process was also addressed through another method. We introduced the use of a fitted copper heat sink during the welding process, which wasn't used in the first iteration. And I don't have an image of that, unfortunately, but with this and by attaching a thermocouple to the surface of the capsule and by monitoring temperatures of the capsule during welding, we were able to maintain a relatively low processing temperature for the entire capsule, as we noticed that the temperature didn't exceed 135 C during that welding process. Now for the sealing process, the design features that we introduced are highlighted in the bottom right figure. So first we introduced a true lid designed to be attached to the base using a precision welder, which is similar process to the first iteration. So this is that designed lid that we had. Now to aid in the laser welding process, a shoulder was then built into the wall of the base. So that's highlighted right here, and it might not be as easy to see. It's more defined in the drawing right here. So this allows the lid to sit recessed in the container to create a flush surface to weld onto. And then in the center of the lid, a small extrusion was added as a feature to assist with handling, and this is extremely helpful, especially when you're dealing or handling small pieces. And I can tell you from experience that these melt wire discs or capsules are extremely hard to find when they fall into the floor. So moving on towards actually creating an inert atmosphere capsule for the melt wires, a weep hole was created on the top lid, shown right here. And the sealed lid and base container with the weep hole still present was then placed into a vacuum system. And then we removed the air within the capsule, and then it was backfilled with high purity helium. The final seal to eliminate that weep hole was completed by shooting the laser through the quartz window, so this image right here, while the melt wire container was within view of the vacuum system, and this within the vacuum system. So, and then finally, just to make sure that our seal was a good one, a helium leak check was performed for confirmation. So as mentioned before, the use of stainless steel for the encapsulation material eliminated the traditional method of visualization, visual observation for evaluating melt behavior of AM melt wires. And so we transitioned to the use of XCT to produce detailed images of the melt wires before and after furnace tests. And here's I've provided a representative image of that capability. So the initial XCT images obtained from experiments were able to provide accurate measurements of details as low as 4 microns, which is awesome for identifying some of those more subtle melting behaviors or characteristics of materials. This also provides a much needed improvement in identifying unique melting characteristics that each material might have. And it's probably important for us to note that the melt wire evaluation method, XCT, used for these experiments is the same method that would be used to evaluate capsules post-irradiation, for post-irradiation examination. So for a typical experiment, images are collected pre-test to serve as a reference. Our first experiment was our attempt to really demonstrate or investigate the need for an inert atmosphere within the melt wire capsule. So for the image on the right of the screen, we have the pre-test melt wire images, which were maintained in gray, and then the post-melt wire images where we superimpose them onto the pre-test melt wires, and then we went ahead and had them colored. So the sample contained an air encapsulation and the melt wires did not show any distinguishable signs of melting even after exceeding expected melting temperatures more than 50 C. So you'll probably notice that the aluminum line colored green did exhibit some unexpected behavior, in that when it was exposed to temperatures beyond its expected melting point, the line detached from the stainless steel substrate and started bending upwards, and we're still not entirely sure why this phenomenon occurred. So next we went on to test the melt wires in an inert atmosphere. We took the same printed materials in an identical container to the one used for the capsule containing air. We then took an open container, meaning just the base and the printed melt wires without the top lid sealed, and placed it within a quartz tube. We evacuated the air within it and then refilled it with helium. And then the melt wires were exposed to a temperature above the melting point of tin. So from the micrograph of the open container, we can see the typical bead formation that was previously identified as a melting characteristic of tin. If you recall, the behavior of that bead formation of the AM melt materials refers to that benchmark study that I mentioned at the beginning of this presentation. So then XCT images were taken of the open container to confirm bead formations were recognizable with both viewing methods, and performing this comparison of air to inert gas environments showed the significance of really having that inert atmosphere encapsulation, especially if we do want to rely on material displaying expected melt behavior. So the third part of this study involved the fabrication of an inert atmosphere capsule. Like the air encapsulation, a reference XCT image was collected before the melt wires were subjected to temperatures above their expected melting points. But due to time constraints, this assembly was only exposed to a temperature exceeding the melting point of all the materials, which we chose 680 C. So then XCT images were taken to evaluate the changes that should have occurred from melting, and to make the results more clear, Some software magic does need to be performed on the XCT images just to adjust contrast levels to really highlight the different metals or materials that are used, and this allows us to really maximize the details of each image. So the pre and post melt images are provided, and in the subsequent slides, I will provide more zoomed in view of each of these sets. But just to provide a really brief overview, after being exposed to a temperature of 680 C, the tin melt wire pooled in the center of the capsule. We had zinc show signs of material separation, which we've indicated as indicator of melt, and then aluminum was unidentifiable after furnace testing. So as promised, here is the more close-up view of tin after undergoing furnace testing at 680 C, which has the lowest melting point of all of the 3 tested melt wire materials. And so you can see that in the pre-test, we have very clearly the printed melt wire line. And then post-test, and we've colored this to make it easier to see, but you can see the melt pool that formed after being exposed to temperatures beyond its melting point. So then moving on to zinc, material separation is seen similar to the previous study. So if you recall that very first iteration or the first set of images where you saw the melt or the material separation after being exposed to its melting point, we saw similar behavior with the zinc material, and this phenomenon is highlighted in that post-test image in yellow, which might be a little bit difficult to see, but hopefully you can make that out. And then finally, we moved to aluminum, which decided to pull a disappearing act on us after furnace testing, and the cause of that, and also determining if it's actually disappeared or maybe if it's just hiding from us during XCT, still needs to be addressed. But one thing that we realized during these experiments is that for materials having similar densities, the contrast between them and XCT results in significant difficulty in obtaining good images, and that is the case with aluminum and stainless steel. So this has prompted efforts in FY22 to look at other encapsulation methods to hopefully minimize this issue. So then some challenges that needed to be overcome have been mentioned sort of throughout this presentation, but to summarize though, that low contrast between melt wire and encapsulation material really makes it difficult to evaluate melt wire performance, and that's really critical in this monitoring technique. And then the welding process did experience some challenges just in the optimization, especially for these small devices. And this was with regards to temperature control, just to avoid premature melting of our melt wires. Just some of those materials did have relatively low melting points. And then in summary, to improve the performance reliability of AM melt wires, a process was developed and tested for us to identify the importance of encapsulating melt wires within an inert atmosphere when packaging melt wire arrays. For the initial wires that were not sealed with air encapsulation, they did not show distinguishable signs of melting, even after having been exposed to temperatures upwards of 50 degrees C beyond their melting points. We were also able to introduce some design changes and a new sealing process that allows for inert gas encapsulation for melt wires. We were able to evaluate encapsulated melt wires pre and post test with XCT with this new design. And then finally, the results from the inert encapsulation testing further confirmed the importance of inert atmosphere within the capsule and gave us promising pathway for AM melt wire development and hopefully in the future deployment in irradiation experiments. So we have submitted a manuscript to MDPI Sensors, and we were told today that it's been accepted, and we're really excited about that. The title of the work is Additive Manufacturing of Miniaturized Peak Temperature Monitors for In-Pile Applications, and it includes the benchmark testing and encapsulation efforts presented today. So we anticipate that this manuscript will be available shortly. For future work, we plan to broaden the material selection and geometries for AM melt wire encapsulation. And along those same lines, we aim to broaden the material selection and geometries for AM melt wires. So this would include feedstock development for AM melt wires that target very specific melting ranges. And then we're also looking to design some specific print patterns that would be advantageous to specific material melting characteristics. And hopefully through these efforts, we can enhance the sensitivity of melt wires and the range of melt wire capabilities. And with that, I'll conclude my presentation, and I welcome any questions or comments that you might have. Thank you.
Thank you, Kio, and congratulations on the very recently accepted paper.
Thanks.
We do have a question here.
Sure.
Any thoughts about printing electrical conductors and monitoring melt wire status online?
Yes, there has been discussion on those sorts of activities. It definitely makes it more complex, right, to do the real-time monitoring. So yeah, we have been sticking with that passive monitoring sort of technique for now, but in the future, I think it would be really awesome if we could pursue those efforts.
Okay. I think that's all the questions regarding this. So I think we can, well, thank you for your presentation again.
Thank you.
And probably move on to the discussion. So I see we've got Uday back on, and I think is Marvin still connected?
Yes, I am.
Perfect. So if it's okay with you, Patrick, I'd like to probably circle back and get the questions answered that were originally meant for Uday.
Of course, you're driving, Austin.
So the questions here are, how is the PZT coupled? I don't think we have your audio, Uday.
Hello, can you hear me now? It's unmuted now.
Yep, now we can.
There we go.
Okay, so we don't use PZT because it's a low temperature piezoelectric material. So lithium niobate and aluminum nitride. So the coupling means like when you're talking about piezoelectric to structural ultrasound transfer. So we right now using a very means like thin gold, like close to 500 nanometer gold film layer. But that is not necessary because we have tested it. Gold layer has its advantage because it keeps the piezoelectric from breaking, because piezoelectrics are mostly brittle. So having gold helps. If you do not have it, then still it works because the zinc oxide result I showed you, that was not with any conducting layer on the top.
There's issue with lithium niobate in terms of oxidation. Those were discussed yesterday too.
Yes,
so another reason for gold is to passivate the oxidation, but
no, because we have tested is that if you clamp the piezoelectric under two metals firmly, then oxidation or anything effect does not affect. Even we can work with acid. We have dipped it into a boric acid for 200 hours at conditions provided by Orano. After that, even the transducer works, so there is no effect. On SAW sensor, it does. There is a reason is that the oxygen starts evaporating from the surface, and because the surface wave is based on the surface acoustic wave is based on the surface. So if the surface is changing, even though the piezo may not be changing that much, the surface acoustic wave sensors needs to be protected, but piezoelectric sensor doesn't require that much.
So I think you've answered this question, but I'll present it here anyways. But does that mean it is dry coupling?
It's like it again depends upon. So you can use dry coupling if you need. Your signal may not be that much great, but yes, of course you can use it. But if you use gold or aluminum, perfect.
Yeah. So the next question was, do you have any concerns with the transmutation of gold?
So because we are using 500 nanometer of gold, means it will not be a problem, because even if there is a gold, it will be clamped between metals, so it will not pass. It will not get out. But there are always options, as I'm saying, that we can coat it with aluminum, and we can use the soft metal as aluminum. We can use indium, or we can use it's like aluminum and indium, because once you have a eutectic mixture of aluminum, gold and indium, then gold it becomes a less liquid. Once it's frozen, it remains there for a long time.
Yeah, I think their question is in regards to gold transmuting into mercury under neutron irradiation.
Of course,
but I don't know. I don't know if it's
denial.
a big concern or not. I'm not sure on the cross sections and things.
So yes, it will. Means like there is a potential for that because the cross section is high, but the amount of gold we have is very small. And of course, we have a different options, like we can use silver, we can use aluminum. So gold is not necessary.
Then the next question was, how do you cut your wafers?
So we used to take it to NIST first, Gaithersburg. Later on that closed, so we now taking it to University of Maryland. There we coat first chromium and then gold, and then there is a saw cutter. We just cut it into a square. So that's the one reason that we cannot have it in a circle or any other shape.
I think I saw another one down lower. What is the application that you envision for the high temperature transducer?
So temperature monitoring, pressure monitoring, liquid level sensing, structure health monitoring, combining acoustic emission, guided wave, and then viscosity is one, and then above that, anything else ultrasonic can do. So means like for us, there is a difference here. We are trying to build a better transducer. That's the part of this project. The application, we are leaving it for people who knows more about the system, because it's a very system dependent. We do not know that what is the thickness people want to measure, what is the temperature range they want to measure, and how they want to validate it.
Yeah, that's exactly right. It's if you define some temperature range, somebody will blow it out of the water and ask for double that. Has been my experience.
So even this, the temperature sensor we are providing it, I don't know, it may be used for gas sensing. Definitely it can be used for the transducer can stay out of the gas. It can stay inside the gas, it will not be a problem. It can use for water temperature sensing. Of course, dip the whole sensor inside it, or you can keep the sensor head outside. Is it going to be in a pipe, or it is going to be in a water, it's like swimming pool? I have no idea, but it's just a temperature sensor.
Yeah, perfect. You guys see any other questions for Day?
I think that was it.
Okay, then we'll move on to questions for Marvin. So Marvin, you there?
Yes, I am.
Okay, perfect. So the question that I had was, you showed your plot of the resonant frequency shift versus pressure in the pin. What are the, you said you've processed that and you got to that from like an algorithm. What are the inputs to that? I guess what do you need to know to extract that pressure is my question.
We process the frequency shift of all the peaks, and they all have a different dependence on pressure, but the processing enables us to develop this metric that's linear with pressure. So we're using the frequency shifts to do that.
But do you need the wall thickness of the cladding, or the gas composition on the inside, or material of the cladding? What like those type of, or the temperature?
We use the nominal dimensions as given by whoever made the rods, and we are working to be sure that our metric is resistant to errors from variances in the dimensions. Our goal is to make it insensitive to changes in the physical dimensions due to temperature or whatever. So that's part of our signal processing.
Okay, perfect. And then I was curious on the detection. So you've got a pulse laser generating, and then you had your 532 detecting. Is that like a Michelson interferometer that you run into, something like that, to get those displacements?
Yes, it's an interferometer for sure. It's a Mach-Zehnder, although that's not important. The important thing about any interferometer is that if you're going to use coherent detection, which is necessary, you have to overlap the two beams very carefully on the surface of the detector. And that's a problem, even with single spatial modes. Uniform Gaussian beam, it's a problem. But in our case, we actually have speckled beams, because when we collect light back from the surface, it's rough, and the light is by no means anymore a single spatial mode. It's highly multimode, or equivalently, there's a lot of speckles. So now what do? You're trying to interfere two speckled beams. That goes against normal orthodoxy about a interferometer. And the answer is we have, as a beam combiner inside, we have actually what we call an adaptive beam combiner. It's a crystal. And the crystal basically responds to the waves in such a way as to perfectly overlap the signal and the scattered reference beam. And that's a critical part of this receiver. And I can tell you more if you'd like.
I'm super interested in that. I'm not sure if everybody else was, but I do have one follow-on question there. Is how do you anticipate challenges coupling that with into a fiber optic based system? It seems straightforward to you based on your experience, or is there just technical challenges there?
We've done a lot of fiber delivered probes, these probes can be the size of your fist, and they're entirely fiber delivered. So you're able to deliver both the generation laser and the detection laser, separate fibers, into this small head, and they're overlapped on the surface, and you collect light back. And it's all because you have multi-mode fibers that you can do that.
Yeah, because I know your application there was for spent fuel cask monitoring, I believe is the application you'd mentioned, but I think fuels programs for fission gas release in pile is of high interest also. That's why I was kind of asking about the temperature and those other types of inputs for real time.
Yeah, so our goal, as mentioned on the slides, is ideally to detect both under pressure from a leak and over pressure from fission gas. That's what we're hoping to do.
Perfect. Yeah.
Maybe we can go back on the acoustic side. I saw Josh has also joined. So I have, before the question I have for Uday, which maybe then refers also to Daniel in terms of how do we use, let's say, SBIRs and how do we move forward towards commercialization. But first, let me just address the question or comment I had before, Uday, whether your interest or your company is interested into the multi-point, because that's so far has been our main selling point. Let's say whenever experiment designers and so forth, we have convinced them to use our ultrasonic transducer, which essentially is the same product that you're commercializing. It's a different transducer, but so the multi-point has been the key. So I wonder whether there's any interest on your side on commercializing.
So yeah, so recently when we are trying to collaborate with Sacit, and he talked about that INL has been in INL is known, so you guys have developed a liquid level sensor, temperature sensor, even with the gratings on for multi-point measurements. So what the idea is that since our sensor head is easier to adopt and use it for different application, like magnet, you don't need an electromagnet such a big unit. You can attach a waveguide here, and then all the techniques and algorithms you guys have developed, you can adopt it on these transducers for further application, and then we can jointly work on product development and commercialization.
Yeah, I mean, you know, with SBIRs, we definitely don't see each other as competing, right? It's just a matter of complementing. So far, in many other applications, the way that we have seen the most useful, at least from our side, and this is from the lab side, so it's purely serves our interest. It's really the fabrication of the sensor, and so what our difficult, or you know, like we lose interest when we need to start selling or fabricate single units, even in the number like 10 or so forth, right? And so, for example, for thermocouples, for SPNDs, that is where we have worked with small industries in terms of fabricating. So that is something that it seems like your business case, let's say, it's slightly different though, because you know what I'm saying is that if we would propose to work on a waveguide that now has 10 measuring points, is something you would be willing to include in your fabrication process and come up with a unit that can do it, and then say, okay, this will cost you, you know, $30,000 for the first, and maybe, you know, each of the next 10 will cost you 15,000. I don't know. So is that something that you'd be willing to explore?
Yes, we are willing to explore those all sensor designs. So, but let me narrow down the problem what we are facing. The problem we are facing is that the nuclear testing. So the nuclear reactor, this community is so reserved that they are not telling us that what exactly the problem is or what their design needs are. And means like, okay, what is the waveguide length you want? I started with 110 millimeter waveguide. If somebody tells me that I needed a 1 kilometer waveguide, I would have started there. But the question is, again, it goes is that we are good at sensor making, but what people really need, and we are looking forward to the national lab to know more about it.
Yes, this is definitely a common interest on our side, and if they don't tell you, it's because they don't know. I mean, they're not at the point. So there are two typical communities, and you know, they're probably listening right now as we speak.
Another thing, means like we have come, means like our company has come through the research, is that there is a need of sensors, but it is not required. This word means like eliminates like why people will buy it, because they are functioning fine. So it is like, for us, we are telling them and trying to miss like many companies. I'm not gonna name any one of them. What we hear from the people is that no, we don't like transducers. Done.
Yeah, I understand. This is a common interest from the program side to facilitate that type of conversation between industry that are vending, that are selling instruments, essentially designing them, and the industry that would be using them. Now, you know, this program has been focusing now on advanced reactors, which offer opportunity in terms of needing to measure more things, mainly because of the different way they tend to operate their reactor. So you have eliminated the need for or the focus on safety instrumentation, which I think so far has been a problem, the problem you were referring to. But then introduces the need for different type of sensors driven towards performance assessment, predictive maintenance, and all. So that opens up, say, more opportunities. And the problem right now is that these advanced reactors haven't yet been designed, or they are under design, and that's where they don't have the type of design specifications that you're looking for. The 110
so right now, means like we are looking for collaboration. So means like our business model is that the sensors being developed, if the developer uses our technology, then it means that we are commercializing our sensors too, and we are going into that motto.
So, you know, I've been opening with that statement. I believe that the path forward here is to start using sensors in irradiation experiments. That's how we have, let's say, removed this catch-22 type situations on what to do first. The irradiation experiments are a venue to make this happen, because you start fabricating, you start selling them, and at the same time the user starts using them. And we as lab can facilitate that by, again, including them in our irradiation experiments. So that is the model that has worked for a few technologies, and so hopefully we can apply it also to this. And it's a good thing also that DOE hears this as we speak, because I think that ultimately convincing them that it's worth using these irradiation experiments as the venue, and the demonstration plans that are coming afterwards. So it's not only about the rigs, but about the component level testing that we are now setting up. So I think that all of this will improve dramatically, Uday, and I will encourage you to stick with it.
Sure.
Okay, so that's that was my question or reference. So is there anyone else that has comments related to anything we discussed today, Daniel?
There was a question that came in. Well, I think Nicholas Hillen is now offline. Was that one that you addressed, Austin?
Was that earlier today or it was recent?
Looks like he added some more down below. I think we addressed that it was a foil, the gold.
And then there was is the transducer clamped for coupling and not a solid state bond?
It is pressure coupled, yes.
It's pressure coupled. Thanks, Josh.
Okay, so we did address that. Okay.
Yeah, I think we're good with the questions.
Yeah,
I think.
Yes.
Go ahead, Austin.
I was just gonna say, I think that concludes it. And any final comments from Patrick or Dan?
No, so Dan can close the meeting as usual, which will reconvene tomorrow at 8. Tomorrow there'll be an interesting discussion. We will move on to basically the use, if you want, of sensors. So again, maybe it goes back to what I was referring to. Tomorrow we'll make the case of why do we need sensors, why do we need new capabilities in sensing, in terms of then using them, assigning them a function, and using them for control. So I encourage everyone to join. The time is the same. Maybe tomorrow we will end a little bit sooner, but for now, Dan, you can close today's meetings and any remarks that you would like to make. Thanks for everyone.
Thank you.
Kind of building off what Patrick said, and then kind of your comments, Uday, was that we are keenly aware here at DOE that there's kind of this disconnect between what industry is searching for and what developers of sensors are building, and understanding what the needs are and how to facilitate that relationship is something that we're trying to address. Part of this program is to start to streamline to commercialization products, and then to connect the developers with the end users or stakeholders, as we like to call them. So don't be discouraged. We can talk about this a little bit more offline as well. But to the general audience, I appreciate your attendance on this day 3 of the webinar. We have just one more day tomorrow, of course, for the Advanced Sensors and Instrumentation Annual Review webinar. Tomorrow's session topic will be digital technology. So we'll hear from various different projects in relation to analyzing data from sensors and applying that to automation, or approaches for determining how to apply an array of, or a set of sensors to a system so that it's adequately instrumented. So I encourage you to return tomorrow starting at 10 a.m. and we will go to, it's slated right now for 5 p.m. And maybe we might break a little bit earlier. But again, appreciate your time and attention today and look forward to facilitating those conversations tomorrow.